One of your first project tasks will be to create containment features. Here's the equation for calculating containment. Let's go over each term one by one. You'll first see a few of this word, n-gram. An n-gram is a sequential word grouping of length n words. For example, in a phrase like, I like to read books, a 1-gram or unigram is just one word, like to or read. A 2-gram might be like to or read books, and a 3-gram might be like to read. In this project, you'll be comparing a source text S and an answer text A, trying to see if the answer text is plagiarized from the source or not. Thinking about n-grams, you might intuitively say that the more n-grams that the two texts have in common, the more likely it is that the given answer text was plagiarized from the source. Containment is a mathematical way of representing this idea, and it's easiest to see in an example. Consider these example sentences. The answer, this is an answer text, and the source, this is a source text. Say we have an n of 1, which means we're going to look at every word in an answer text and every word in a source text. We'll count up the occurrences of each word in each text. This gives us the n-gram counts. Then we'll take the intersection of those n-gram counts. The intersection is the set of n-grams that both of the texts have in common. Here we see that both of the texts contain the words this, is, and text. This is the intersection. To get a numerical value that represents this intersection, we just sum up these occurrences to get the value 3. Finally, we'll normalize this value by dividing by the sum of all n-gram counts in the answer text. For an n equal to 1, this is 5 for the 5 words. And we get the final containment value, 0.6. So, to summarize, we calculated the number of n-grams that the source and answer text have in common, then divided that value by the number of n-grams in the answer text. A value of 0.6 is quite high, but maybe it's just because these texts are short or they use the same kind of filler words. Now, if we selected an n equal to 2, we would look at which pairs of words these texts have in common. With an n of 1, the order of words didn't matter, but with a larger n, the order of words in each n-gram does matter. Consider a longer text. You can imagine that if you have a high containment value for matching 2 grams or 3 grams or longer, then this might be a good indicator of cut and paste style plagiarism. This will be one of the features that you calculate for our corpus of text data, and you'll get more practice calculating containment next. In text classification, it's often useful to include multiple features in your final classification model. Containment is just one measure of text similarity, and in this project, you'll also be expected to calculate the longest common subsequence, or LCS, between a source and answer text. Given two texts, an answer A and a source S, your goal is to find the value for the longest common subsequence of words. This is the longest sequence of words that appear left to right in both texts. It's important to note that the words don't have to be exactly continuous, just in left to right order. Consider these sentences. A. Machine learning is all about finding patterns in data and forming predictions. And S. Deep learning uses neural networks to find patterns in data. To find the LCS, we can go along word by word in each sentence. The first words, machine and deep, are different. Then learning is a match. Then the texts diverge again, so we continue moving left to right along both texts until we see the next common words. In this case, the words patterns in data. That's the end of our source text, and so we can stop here and say that the LCS is 4 words total. There's one more normalization step, which is to divide this value by the length of the answer text, which has 12 words in it. So we get our final value, 4 over 12, or about 0.333. You could approach this problem recursively, keeping track of your location in each text and counting up when you find a common word. But a recursive approach, especially for longer texts, can be very computationally intensive. Instead, I recommend a dynamic programming approach, which I'll go over next. The method I recommend for implementing an efficient LCS algorithm is using a matrix and dynamic programming. Dynamic programming is all about breaking a larger problem into a smaller set of subproblems and building up a complete solution without having to repeat any subproblems. This approach assumes that you can split up a large LCS task into a combination of smaller tasks. Let's look at a simple example that compares letters. The answer, A, B, C, D, and the source, B, D. We can see right away that the longest subsequence of letters here is 2. B and D are in sequence in both strings. and we can calculate this by looking at relationships between each letter in the two strings. This technique can be applied to individual words as well, not just individual letters. Here I have a matrix with the answer letters on top and the source letters on the left side. This starts out as a matrix that has as many columns and rows as letters in the strings, plus one additional row and column, filled with zeros on the top and left sides. So in this case, instead of a 2x4 matrix, it's a 3x5 matrix. Now we can fill this matrix up by breaking it into smaller LCS problems. For example, let's first look at the shortest substrings, the starting letter of A and S. We'll first ask, what is the longest common subsequence between these two letters, A and B? Since these letters don't match, the answer is 0, and I'll fill in the corresponding grid cell with that value. Then we ask the next question. What is the LCS between AB and B? Here we have a match, B and B, and we can fill in the appropriate value, 1. Notice that I'm only looking at if there's a matching letter between one column and one row at a time to get this one match. If we continue along this row, we can actually see that B only matches this one time, and any further questions, such as what is the LCS between A, B, C, D, and B, will have that same value, 1, due to the initial BB match. In fact, this 1 will propagate to the right, filling up the rest of this row. So let's move on to the second row. A and BD have 0 matches. Then AB and BD do have a match, but this B row and D column do not match exactly. The match actually comes from the same BB match that we recorded before, which we noted in the cell above this one. So we can take that value, 1, and pull it down into this cell. Then it stays 1 in this row until another match is finally reached, the letter D. With this additional match, we add 1 to our previous highest LCS value to get a longest common subsequence of 2 at the corner of this filled matrix. So to get our final value, we then just have to normalize by dividing by the length of the answer text, which has 4 letters. So we get a final value of 0.5. A few interesting patterns emerge from this matrix. We notice that the LCS is always going to be in the bottom right of our complete matrix, because this corner indicates that we've reached the end of both of our texts. We've considered all possible matches. Now, we started with a row and column of zeros. Then, to fill up this matrix, we looked at one cell at a time. I'll call this our cell of interest. And we only had to handle 2 cases. 1, if we do not find a match, as in the case of the letters A and B, we can take a look at the values in the cells directly to the left and top of our cell of interest. Then fill our cell by looking at the maximum of those 2 values. In this case, the maximum is 0. 2, our second case is if we do find a match, as in the case of B and B and D and D at the end. In this case, we can take the value in the cell that is to the top left of our cell of interest and add 1 to fill our cell of interest. These 2 cases, for no match and match, allow us to fill in the matrix dynamically. To calculate each new cell value, we only have to look at 1 or 2 existing values in our matrix, basically taking earlier solutions to LCS tasks and using them to build up a final solution.
Welcome to our lesson on creating a professional GitHub profile. I'm Matt Leonard, a course developer at UDACITY. In this lesson, you'll create or update your GitHub profile for use as a portfolio of your work. You'll also learn how to impress recruiters by contributing to open source projects. If you don't have experience with Git and GitHub, please take Udacity's course on version control with Git. Just follow the link in the instructor notes, then come back here when you're done, and we'll work on your profile. Artists use a portfolio to hold examples of their work. For instance, here's a couple paintings in my portfolio. I call this Octopus on a Swing, and this is 2 cellos and a baby. Similarly, my GitHub profile is a portfolio of my programming work. You can use GitHub the same way to show off your work to potential employers. Your profile will also show how you work. Don't worry, we'll go through various ways to make your GitHub profile into a professional portfolio. Now, let's look at an excellent GitHub profile through the eyes of a recruiter. This is Scott Moss's profile. He's a software engineer here at Udacity. Over on the left is the personal information. A picture with a friendly smile can help recruiters make a connection with you, but it isn't mandatory. If you aren't using a picture of yourself, be sure to include a picture that somehow captures your personality, but nothing crude. Below is some general information and a link to Scott's Twitter account. Recruiters can look through Scott's tweets to get a sense of the things he's interested in. Similarly, I have a link to my personal blog. Also, make sure your username is something professional, like your name. It's not a good idea to name yourself after your favorite pop star. Okay, back to Scott's profile. Over here, we see a list of Scott's most popular repositories. These are ranked by the number of stars, which are given by other GitHub users that like the repository. The descriptions are nice so that we know what these repositories are for. To the right is a list of other repositories that Scott has contributed to. This is a clear indication that he is involved in collaborating with others on open source software. Employers can look through Scott's contributions to judge how well he works on a team. We can see that NGFX is really popular. We'll take a look at it later. Down here is the contribution chart. This is one of the first things a hiring manager is going to look at. Each square is a day. The darkness of the green indicates how many contributions were made on that day. You can see that Scott is very active, making at least one contribution most days. It's pretty clear that Scott spends a lot of time working with code, a good sign to a recruiter. Now we can check out one of Scott's repositories to get a sense of his work. Let's check out NGFX over here, the most popular repository he's worked on. We can see here that Scott made the most recent commit. If we click through to the contributors, it's clear that Scott has written most of the code. Going back to the repository, firstly we see a short description of the code. This is a library for making animations with Angular. He's also included a link to a GitHub page for the library. These GitHub pages are easy to create and very impressive. Here's the README, one of the most important parts of a repository. Its main purpose is to help others understand and use the code. A repository without a README has no starting point for someone to understand it. We'll come back to the README, it deserves special attention. Now we can scroll back up to look at the most recent commits Scott has made. Most of the recent commits are updating the version number and other chores, but there are some features and other additions too. We could look through some of these commits to understand how Scott writes code, but I'm not going to get into that now. Next, we'll hear from a hiring manager at Udacity about what he looks for in a GitHub profile. I'm here with Art Gillespie, an engineer and hiring manager here at Udacity. Thanks for coming.
Oh, thanks for having me, Matt.
Of course. So what I asked you here for is that I'm trying to teach students how to use their GitHub profile as a portfolio to show off their work. So I want them to get a sense of what a hiring manager or a recruiter actually looks for from their GitHub profile.
Oh, okay, yeah.
Yeah. So just start out. What is your role as a hiring manager?
Well, as a hiring manager, really, it's a collaborative role where I work with engineers on the team and leadership, and we sort of figure out, what attributes do we value in engineers, and then we work closely with, we have amazing recruiters and HR people here. We work closely with them to sort of figure out how do we best screen for those attributes. And then, of course, I spend a lot of time actually, doing interviews, screening people, looking at people's GitHub repos, at their LinkedIns and whatnot, and just trying to get a sense of the candidates and then making hiring decisions.
Cool. So when you're looking at a GitHub profile, what's the first thing you look at, and then why is it important?
Well, yeah, the first thing I look at is that sort of heat map at the bottom with the activity, the different shades of green, because that just gives me a really good sense of, does this person, are they passionate about coding?
Yeah.
And do they contribute often? And it doesn't have to be like all the time, but you see like sort of steady patterns. And I found that that just correlates with success in the workplace, people that love to code.
Awesome. And so when after your initial impressions, like looking at this activity chart, so what's the next thing you look at? Like what else do you look at to get a sense of the candidate?
Well, for me, the next step is just to say, okay, well, here are the repos they've created, here are the repos they've contributed to, where have they done the meatiest work, and like pick one of those and just dig in. And I'll just spend, sometimes an hour just reading their code and trying to get a sense for the kind of, engineer they are. I'll also sometimes just dig into, have they contributed to other GitHub repos issues? How do they interact with other people in those discussions and whatnot? Are they a good collaborator? Are they patient? That sort of thing.
Welcome back. In the instructor's notes, you'll find a link to a GitHub profile. Imagine yourself as a recruiter looking at this profile. Identify parts that could be improved and mark them with the checkboxes. Now I'll go through the profile and give you my thoughts. The profile picture seems a little juvenile and you can't see the face clearly. It would be better to have a normal picture without a crazy filter. We also don't know what this user's real name is. Their username, acorn47, could be better, something based off the real name. There isn't any other personal information either. If I was a recruiter, I wouldn't know how to contact this person or anything about this person really. Descriptions of the repositories would be very useful here, so I can tell what kind of projects this person has worked on. And finally, we can look at the contribution chart. There's a bunch of commits here, then a couple commits later. This person appears to not have spent much time writing code. It's possible they made a lot of changes, but packed everything into one large commit. That's not a good sign. Now, let's go through a few quick fixes to spiff up your own profile. You can follow along as I fix mine. This guy here, if you don't know, is Andre the Giant, professional wrestler, actor, and all-around good dude. However, I'm going to need a better picture, preferably of myself, if I want to connect with recruiters. Also, I'm missing a bunch of other information like my name and where I'm located. GitHub has given me a prompt to flesh out my profile to help other GitHub users get to know me. Let's follow their advice. I can edit my profile by clicking through here. Here's where I can upload a new picture. Then I'll fill out my information, my name, the URL of my blog, my company, and finally my location. Now that I'm done with that, I can also change the names of my repositories if any need a better name. My repository names look fine. If I did want to change the name, I'd click the repository, then go to Settings. Here's where you can change the name. Also, don't forget to comment your code. You'll probably end up showing off a couple sections of your code to an interviewer. Make sure it's commented and working. Go ahead and make any changes to your profile that you need to. I've provided a checklist that you can use to keep track of any improvements that you need to make. When you're done, mark this checkbox over here, and we can continue on to READMEs. A well-written README is one of the most important parts of a good repository. The README is necessary for others because it tells people what the code is for, how to build or install the code, and how to contribute. To teach you how to write a good README, I'm going to hand you off to my friend Walter.
Hey,
Oh, hey, nice to see you.
for sure. Thanks for having me.
Thanks for coming. So I have some students who need to learn how to write READMEs.
Well, that's perfect because I teach a course on just that. It's less than an hour long, and it'll teach you everything you need to know about writing documentation for humans.
Thanks. So you'll find a link to Walter's lesson in the instructor notes. When you're finished with it, head back here and we'll continue. Hi, I'm back with Art. And now I'd like to get into commits and commit messages. So commits are one of the main reasons we use Git as a version control system. So you can make these incremental changes and you can see what changed every time you make a commit. And a very important part of this is the commit message. So why is the formatting of the commit message so important?
Well, I think a well-formatted commit message is, and probably the most important reason is git blame, right? Because as you go sort of digging through people's code or your own code, trying to figure out what's wrong, especially if you're looking for a bug. But sometimes you just want to know why a line of code is the way that it is.
Yeah.
The first thing you're going to do is run git blame. It's an awesome tool, and it's going to show you the committer, but also the commit message. And if that message is just like added stuff, it gives you no context for why the code changed or why it's there in the first place. And that's super important. It's super important for you as you maintain your code down the line. It's super important for people that follow after you and maintain your code. And so, yeah, it's funny. I definitely, when I look at candidates, when I dig through their GitHub, I check out to see, sort of how thorough and well they communicate in their commit messages. It's really important.
Hi again. Look through your recent commit messages and think about the formatting. How can you make the messages more clear and helpful? Think about how you would format them using the guide in the previous reading section. Just mark this checkbox when you're ready to move on. As a programmer, you're often going to be working with others on shared code, so employers want to see that you can collaborate. By contributing to open source projects, you can demonstrate how well you work with others. It also shows that you're helpful and love working with code. Hi, we're back. So I've been wondering how you know if somebody is a good collaborator, right? Because these candidates, when they get their job, and they have to work with other people on shared code bases. So how do you know from a GitHub profile if somebody's going to be a good collaborator?
So one thing I do to screen people for like how they'll work well on a team or how well they'll work on our team is to sort of branch out from the GitHub profile and maybe start with the issues on a repo that they've participated in and see how they participate in those threads and if they've commented on pull requests and whatnot, and just get a sense for how they interact with other engineers in the repo. Particularly, one thing that I think is really interesting is how, whether they're patient with kind of people that may be newer to the community. And then from there, like I said, you branch out and maybe find if there's an internet relay chat channel that they may have been in related to a repo, and look at the logs and just see how they, are they helpful? Are they, are they kind? Or are they patient? And it's such an important signal, because at the end of the day, you really want to hire people that are going to work well on a team, be a good fit for your team. And so yeah, I spent a lot of time doing that, just kind of digging in and seeing how they interact with other engineers publicly.
Yeah. So when you're talking about interacting with other engineers publicly, you mean on like open source projects, right? I know, personally, it's very daunting to start, working on this big library that all these other, really intelligent people are working on. So how would you start, or like what's your advice for, a beginner, a new programmer, to actually start contributing to these open source projects?
Yeah, it's a great point, Matt. I mean, it's really daunting, and I mean, even for me, and I know one thing that I do and that I recommend people do to just sort of, break the ice with a new project is like find some documentation, even the README. One thing I love to do is actually go through the README, clone the project, try to build it, try to get it running, following the steps in the README, and then like try to clarify it based on the sort of problems that I had. Maybe it just needs to be updated a little bit. Submit a pull request with a few changes to the README. Those almost always get accepted. And it's just a great way to break the ice. I mean, you're going to move on to actually like fixing bugs and then maybe actually contributing features, but just to sort of get into that community and get over that initial hump of feeling intimidated and there's just so much code and not knowing where to start.
Yeah.
I find just contributing some documentation is a great way to start.
Cool. Let's go over how you can start contributing to open source projects. This is one of my favorite libraries, Pandas. Here we can see a list of issues that users have created. Contributing to the project can be as simple as helping a user with one of these issues. Of course, you can also create your own issues. These can be feature requests, bugs you've run into, or things in the documentation that you find unclear or incorrect. Be sure to be nice, this is all public. As Art said, one of the best ways to start contributing is by improving the documentation. Here's an issue related to the documentation. If you were working on this library, you could take on this issue, fix the documentation, and make a pull request. Finally, you can create a list of repositories you like by starring them. Also, if you watch a repository, you'll be notified of any changes. This is a great way to keep up with a library you're interested in working on. Welcome back. Go out and find an interesting repository you'd like to follow. For example, most of the popular programming languages have GitHub repositories, like Python and Node.js. Mark this checkbox here when you're done. As you are working on the rest of your Nanodegree, keep in mind that it's a good idea to contribute somehow to an open source project. If you don't know where to start, look through the documentation and fix a typo. Or if there is something in the documentation that isn't clear, create an issue about it and ask for help. Then you can rewrite that part and make a pull request.
Hi, I'm excited to work with you on using networking to find more work opportunities. The more people you know, or the more presence you have online, the more likely you'll be able to find opportunities or have opportunities find you. I want to share a story with you. The first time I networked was when I was 13 years old and wanted to find an after-school job as a babysitter. I asked my parents for advice. They told me to look at the classified ads of the newspaper to see who was looking, to post flyers at my school to advertise, and to also ask my parents' coworkers if they knew anyone looking for a babysitter. I actually had a few people reach out after seeing my flyers, but I got my first babysitting gig from a friend of my mom's coworker. I have always used the same networking system whenever I search for a new job. Nowadays, instead of using the classified section of the newspaper, I search for openings on job boards like Indeed and Dice. Networking gave me access to more job boards. I joined a lot of local professional groups which have their own job boards not open to the general public. After college, I moved across the country, unemployed, and I got a job from a posting in a local group listserv. For most of my career, I would say my LinkedIn profile was pretty bad because I didn't take it seriously. However, one day I took the advice from UDACITY's LinkedIn course and rebranded myself on my page. I got 3 emails from recruiters that week. Those recruiters found me because I optimized my LinkedIn profile for searches. And instead of asking my parents' coworkers for job leads, I attended meetups and mixers to connect with people in the industry and have found job opportunities that way. I found my current job at UDACITY through a conversation with someone in the tech industry who I actually didn't know all that well at the time. You don't know where opportunity will come from, and the best way to make sure you don't miss out on an opening is to have a great online presence and network. In this lesson, we'll review how to network and spend some time on personal branding, which will make sure your networking attempts lead to job opportunities. Hey Chris.
Hi Trin.
Over the past year that we've been working together on the careers team at UDACITY, you've developed so much, so many of our web apps, so many of our data backend, and I was really surprised when I learned that you've actually only been a software engineer for a year. And so I'm just really curious to see how you got here.
Yeah, that's right. I've been a software engineer at UDACITY for a year, and my career, I guess, started a little bit more than 10 years ago. I was originally an admission counselor, and I got into tutoring and teaching. I even did a stint as an administrator working at a psychiatrist's office learning about medicine and health insurance.
Well, that's a really diverse background. How did you end up from a psychiatrist's office to being a software engineer?
So it was definitely a long, winding road. I think for me, I first got curious about software engineering through teaching. I made some courses at UDACITY in math and data analysis and product design. And along the way, I picked up coding skills. So I learned a little bit about Python, I learned JavaScript, I learned how to think computationally, how to think kind of more like a computer scientist. And I've just been learning ever since. For me, I think the biggest thing was trying to acquire all those skills and then convince people that I had enough skills to build something and to contribute to a larger organization.
Mm-hmm. It's great that you brought that up. I speak with a lot of people about their career development, and so many of them took the initiative like you to learn on their own time, some while they're working full-time, but they still kind of face a barrier in that it's hard for them to convince people that, yes, I am qualified, and yes, even though I don't have background in this job, I can still do it. How did you approach that problem?
Yeah, I mean, it's certainly a hard one, and I think it's easy to feel like you're an imposter or you don't have enough skills. And I think the biggest thing you can do is, one, practice, but also two, tell yourself that you are a software engineer. Talk about your projects, talk about them technically with other people. That will build your confidence in your own abilities and your ability to communicate that you can do this work. So I think for me, I know one of the things that I had to do was just kind of turn off that voice in my head that says, oh, you're not good enough, or oh, you don't know enough things. Just turn off that imposter syndrome entirely and talk about what I can do and what I have done. And that's what can really help you get an interview and succeed in those interviews.
A lot of people, when they're transitioning to a new career for the first time, it's really hard for them to introduce themselves and package everything that you just said about yourself into kind of a short introduction to other people. So do you have any strategies on how people can approach talking to other people about their career change?
Yeah, I think one of the best things that you can do is to use an elevator pitch.
Regardless of which type of networking event you attend, the number one thing that will help you navigate all of them is having a great elevator pitch. Elevator pitches were originally known as sales pitches and lived solely in the business world. However, they soon became popular across all industries because it was a way for people to quickly communicate the purpose and value of something. Having an elevator pitch is invaluable in your career development. These short sentences will find their way in your LinkedIn summaries, in talking to a recruiter, in small talk with friends, or in requesting a promotion. Elevator pitches also help outside of networking, such as in a job interview, when the employer asks you why you're applying or what you're interested in. I have to admit that I did not like my first experience with elevator pitches. I was at a professional development event and was put in with a group of strangers, and we all had to respond to the prompt, "Tell me about yourself." I was first. I rambled. I blocked a lot of that experience from my memory, but I'm sure I sounded like this. "Hi, I'm Trin. I grew up in the San Francisco Bay Area, and I go to school, and I'm interested in education, but I've never worked in education, and yeah, that's why I'm here today, to help me make that transition." I was really embarrassed, especially when everyone else gave their answers and sounded like they had their life together. But it was also a great learning experience because after hearing myself, I kept thinking, why did I need to tell people where I grew up? Is that really important for my career? Why did they need to know that I was transitioning careers or that I was new to this industry? I was at the event. Doesn't that mean I was already interested? This experience taught me that if I wanted to sound confident and communicate well, I needed a concise elevator pitch that showed what I wanted and why I wanted it. My elevator pitch now is, I'm a project manager passionate about personalized education. After working in nonprofits and public policy, I believe lifelong learning is the solution to many societal issues. I'm excited to apply my teaching and management skills at UDACITY. So let's dive into how to develop an elevator pitch with personal branding in mind.
As I was coming up with my elevator pitch during my career change, I kept thinking about two things. One, what did I want employers to know about me? And two, what was I most proud of? I wanted employers to know that I'm passionate about education, but I wanted to be a software engineer. I wanted them to know I worked hard to get where I was then and that I was worth taking a chance on, because if I got the job, I would give it everything I had. So my elevator pitch ended up being something like this. Hi, I'm Chris, a full-stack software engineer who loves building education products. I recently developed a web app using AngularJS that lets teachers share student writing samples anonymously. I'd love to combine my passion for teaching and learning with my software development skills to continue building personalized learning products for people. My elevator pitch isn't something I recite when I meet someone. That would be weird to say hi and then just dive into the pitch. However, I could write this pitch as my LinkedIn summary. When I'm talking to someone, I communicate the points in my pitch throughout the conversation. Let me show you what that looks like. Pretend in the next video that Tren is a recruiter and I'm a job seeker meeting her at a mixer for education startups. Hi, I'm Chris.
Hi, I'm Tren. Nice to meet you.
Nice to meet you too. Are you a software engineer?
No, actually, I'm a technical recruiter at UDACITY.
Oh, cool. I actually really like Udacity. I've taken a number of Udacity's online courses. You guys have really helped me, learn at my own pace, and I love that I have a flexible, learning time.
That's really awesome to hear. Which projects have you been working on?
So I actually recently was building an application that lets teachers share student responses anonymously, and it's been going really well. I am trying to actually add in GraphQL, which is a fairly recent technology, so that way I can query the data a little bit easier.
It's actually pretty funny that you mentioned working on an app like that, because Udacity is looking into developing something similar.
Oh, very cool. Can I get your card?
Yeah, of course. I'd really love to hear from you, so send me an email after this mixer.
Great, thanks so much. Nice to meet you.
Nice to meet you too.
So I'm here with Timo from Arvado, and you saw him actually in the first term of this program. But you're back again for another project where we're working with the same data, but we actually sort of left a lot of the complexity this time that we removed the first time. Can you talk about the third data set that's introduced, as well as what's the ending goal that Arvado uses this data for?
Sure. So firstly, welcome back, and thank you for working on another project with our data. I hope you liked the initial one. Now we are introducing a third data set that you can use to actually evaluate your model and test your recommendations you would be giving to our client with that model. So the project you have been working on is a real-life project. It's a project you would be working on as a data scientist at Bertelsmann Arvado. We have similar projects like this where you would be analyzing attributes, customers, for example, to recommend credit scores. We are looking at similar of these attributes you have been working on to identify payment behavior, predict payment behavior, recommend credit scores, calculate credit scores.
Can you talk a little bit about what you want as an ending goal from sort of a business perspective? So this whole new third data set that's come into play now opens up sort of a world of different questions and how we might be able to answer them.
Absolutely. The underlying business question or the kind of problem statement is, how can our client, how can the mail order company acquire new clients more efficiently? And what we're asking you to do is essentially, so you have the attributes and the demographic information of the existing clients. We would like you to analyze the attributes of these existing clients, match them against a bigger data set that includes attributes for people in Germany, and essentially figure out which people in Germany are most likely new customers for our clients, the mail order company selling organic products. And it's from our kind of view, it's a real life project. So essentially what it helps to do is increase efficiency in the customer acquisition process. So instead of the mail order company reaching out to all people in Germany and targeting them with a marketing campaign, we would just then be reaching out to the people we identified as becoming most likely new customer, and can then essentially do targeted advertising. That's what it is.
Right. Right now, they have a culture where they make decisions based on, maybe like past experiences, intuition, but and a lot of that is okay. But if they can infuse those decisions by also backing them up with data, or even showing like we can go even further with this decision in X direction or Y direction, that's sort of like where you guys come in. Is that true?
Absolutely. So that's what we are doing. So the mission of our engagement is make decisions based on data instead of gut feel. Of course, we're dealing with senior finance managers, and they do have a lot of experience. But our client is really conscious that they are using data points to kind of, prove and show the rationale behind their decisions. So we'd like to have them use more reports, use reports more often, request more reports, and actually use the data we are providing.
Timo, thanks so much for some insight into the data set.
Sure. And thank you very much for participating in this project. I hope you find it insightful. It is, as I mentioned, it's data we are using. It's a real data science project, so thank you very much for that.
The capstone project represents an experiment, and the project itself is really to decide what next. How do we take this experimental data that's been rolling for about a month and turn that into discover which are the groups in there and what are the offers that really excite people. So the capstone project is about discovering what is the best offer in there, not just for the population as a whole, but at an individual personalized level. This is simulated data for the sake of testing the algorithms, not simulated data for the sake of mimicking real people. Certain kinds of people will respond to certain offers in different ways. Some people may respond negatively. That's another thing to watch out for in some of these experiments, is that sometimes people really don't want to see what you have to send them, and the best thing to do is to not send something. What you'll want to know is that you understand the cause and effect, and that largely the way you're framing and thinking about the problem is consistent with what the data is telling you.
Natural language processing is one of the fastest growing fields in the world. NLP is making its way into a number of products and services that we use every day. Let's begin with an overview of how to design an end-to-end NLP pipeline. Not that kind of pipeline, a natural language processing pipeline. You know, where you start with raw text in whatever form it is available, process it, extract relevant features, and build models to accomplish various NLP tasks. Now that I think about it, that is kind of like refining crude oil. Anyways, you'll learn how these different stages in the pipeline depend on each other. You'll also learn how to make design decisions, how to choose existing libraries and tools to perform each step. Let's look at a common NLP pipeline. It consists of 3 stages: text processing, feature extraction, and modeling. Each stage transforms text in some way and produces a result that the next stage needs. For example, the goal of text processing is to take raw input text, clean it, normalize it, and convert it into a form that is suitable for feature extraction. Similarly, the next stage needs to extract and produce feature representations that are appropriate for the type of model you're planning to use and the NLP task you're trying to accomplish. When you're building such a pipeline, your workflow may not be perfectly linear. Let's say you spend some time implementing text processing functions, then make some simple feature extractors, and then design a baseline statistical model. But then maybe you're not happy with the results, so you go back and rethink what features you need, and that in turn can make you change your processing routines. Keep in mind that this is a very simplified view of natural language processing. Your application may require additional steps. Let's take a closer look at text processing. The first question that comes to mind is, why do we need to process text? Why can we not feed it in directly? To understand that, think about where we get this text to begin with. Websites are a common source of textual information. Here's a portion of a sample web page from Wikipedia, and the corresponding HTML markup, which serves as our raw input. For the purpose of natural language processing, you would typically want to get rid of all or most of the HTML tags and retain only plain text. You can also remove or set aside any URLs or other items not relevant to your task. The web is probably the most common and fastest growing source of textual content, but you may also need to consume PDFs, Word documents, or other file formats. Or your raw input may even come from a speech recognition system, or from a book scanned using OCR. Some knowledge of the source medium can help you properly handle the input. In the end, your goal is to extract plain text that is free of any source-specific markers or constructs that are not relevant to your task. Once you have obtained plain text, some further processing may be necessary. For instance, capitalization doesn't usually change the meaning of a word. We can convert all words to the same case so that they are not treated differently. Punctuation marks that we use to indicate pauses, etc., can also be removed. Some common words in a language often help provide structure, but don't add much meaning. For example, a, and, the, of, are, and so on. Sometimes it's best to remove them if that helps reduce the complexity of the procedures you want to apply later. Once we have our text ready in a clean and normalized form, we need to transform it into features that can be used for modeling. For instance, treating each document like a bag of words allows us to compute some simple statistics that characterize it. These statistics can be improved by assigning appropriate weights to words using a TF-IDF scheme. This enables a more accurate comparison between documents. For certain applications, we may need to find numerical representations of individual words, and for that we can use word embeddings, which are a very efficient and powerful method. In this lesson, you will learn all these techniques for extracting relevant features from text data. The first feature representation we'll look at is called bag of words. The bag of words model treats each document as an unordered collection or bag of words. Here, a document is the unit of text that you want to analyze. For instance, if you want to compare essays submitted by students to check for plagiarism, each essay would be a document. If you want to analyze the sentiment conveyed by tweets, then each tweet would be a document. To obtain a bag of words from a piece of raw text, you need to simply apply appropriate text processing steps: cleaning, normalizing, splitting into words, stemming, lemmatization, etc., and then treat the resulting tokens as an unordered collection or set. So, each document in your dataset will produce a set of words. But keeping these as separate sets is very inefficient. They're of different sizes, may contain different words, and are hard to compare. Also, what if a word occurs multiple times in a document? Is there a better representation you can think of? A more useful approach is to turn each document into a vector of numbers, representing how many times each word occurs in a document. A set of documents is known as a corpus, and this gives the context for the vectors to be calculated. First, collect all the unique words present in your corpus to form your vocabulary. Arrange these words in some order and let them form the vector element positions or columns of a table, and assume each document is a row. Then count the number of occurrences of each word in each document and enter the value in the respective column. At this stage, it is easier to think of this as a document term matrix, illustrating the relationship between documents in rows and words or terms in columns. Each element can be interpreted as a term frequency. How frequently does that term occur in this document? Now consider what you can do with this representation. One possibility is to compare two documents based on how many words they have in common or how similar their term frequencies are. A more mathematical way of expressing that is to compute the dot product between the two row vectors, which is the sum of the products of corresponding elements. Greater the dot product, more similar the two vectors are. The dot product has one flaw. It only captures the portions of overlap. It is not affected by other values that are not in common. So, pairs that are very different can end up with the same product as ones that are identical. A better measure is cosine similarity, where we divide the dot product of two vectors by the product of their magnitudes, or Euclidean norms. If you think of these vectors as arrows in some n-dimensional space, then this is equal to the cosine of the angle, theta, between them. Identical vectors have cosine equals 1, orthogonal vectors have cosine equals 0, and for vectors that are exactly opposite, it is minus 1. So the values always range nicely between 1 for most similar to minus 1, most dissimilar. One limitation of the bag of words approach is that it treats every word as being equally important. Whereas intuitively, we know that some words occur frequently within a corpus. For example, when looking at financial documents, cost or price may be a pretty common term. We can compensate for this by counting the number of documents in which each word occurs. This can be called document frequency, and then dividing the term frequencies by the document frequency of that term. This gives us a metric that is proportional to the frequency of occurrence of a term in a document, but inversely proportional to the number of documents it appears in. It highlights the words that are more unique to a document and thus better for characterizing it. You may have heard of or used the TF-IDF transform before. It's simply the product of two weights, very similar to what we've seen so far, a term frequency and an inverse document frequency. The most commonly used form of TF-IDF defines term frequency as the raw count of a term T in a document D divided by the total number of terms in D, and inverse document frequency as the logarithm of the total number of documents in the collection D divided by the number of documents where T is present. Several variations exist that try to normalize or smooth the resulting values or prevent edge cases such as divide by zero errors. Overall, TF-IDF is an innovative approach to assigning weights to words that signify their relevance in documents. So far, we've looked at representations that try to characterize an entire document or collection of words as one unit. As a result, the kinds of inferences we can make are also typically at a document level. Mixture of topics in a document, document similarity, document sentiment, etc. For a deeper analysis of text, we need to come up with a numerical representation for each word. If you've dealt with categorical variables for data analysis or tried to perform multi-class classification, you may have come across this term, one-hot encoding. That is one way of representing words. Treat each word like a class. Assign it a vector that has 1 in a single predetermined position for that word and 0 everywhere else. Looks familiar? Yeah, it's just like the bag of words idea, only that we keep a single word in each bag and build a vector for it. One-hot encoding usually works in some situations, but breaks down when we have a large vocabulary to deal with, because the size of our word representation grows with the number of words. What we need is a way to control the size of our word representation by limiting it to a fixed size vector. In other words, we want to find an embedding for each word in some vector space, and we want it to exhibit some desired properties. For example, if two words are similar in meaning, they should be closer to each other compared to words that are not. And if two pairs of words have a similar difference in their meanings, they should be approximately equally separated in the embedded space. We could use such a representation for a variety of purposes, like finding synonyms and analogies, identifying concepts around which words are clustered, classifying words as positive, negative, neutral, etc. By combining word vectors, we can come up with another way of representing documents as well. Word2Vec is perhaps one of the most popular examples of word embeddings used in practice. As the name Word2Vec indicates, it transforms words to vectors. But what the name doesn't give away is how that transformation is performed. The core idea behind Word2Vec is this: a model that is able to predict a given word given neighboring words, or vice versa, predict neighboring words for a given word is likely to capture the contextual meanings of words very well. And these are in fact two flavors of word-to-vec models. One where you are given neighboring words called continuous bag of words, and the other where you are given the middle word called skipgram. In the skipgram model, you pick any word from a sentence, convert it into a one-hot encoded vector, and feed it into a neural network or some other probabilistic model that is designed to predict a few surrounding words, its context. Using a suitable loss function, optimize the weights or parameters of the model and repeat this till it learns to predict context words as best as it can. Now take an intermediate representation like a hidden layer in a neural network. The outputs of that layer for a given word become the corresponding word vector. The continuous bag of words variation also uses a similar strategy. This yields a very robust representation of words because the meaning of each word is distributed throughout the vector. The size of the word vector is up to you, how you want to tune performance versus complexity. It remains constant no matter how many words you train on, unlike bag of words, for instance, where the size grows with the number of unique words. And once you pre-train a large set of word vectors, you can use them efficiently without having to transform again and again. Just store them in a lookup table. Finally, it is ready to be used in deep learning architectures. For example, it can be used as the input vector for recurrent neural nets. It is also possible to use RNNs to learn even better word embeddings. Some other optimizations are possible that further reduce the model and training complexity, such as representing the output words using hierarchical softmax, computing loss using sparse cross-entropy, etc. Word2Vec is just one type of word embedding. Recently, several other related approaches have been proposed that are really promising. GLOVE, or Global Vectors for Word Representation, is one such approach that tries to directly optimize the vector representation of each word, just using co-occurrence statistics, unlike Word2Vec, which sets up an auxiliary prediction task. First, the probability that word J appears in the context of word I is computed, Pj given I, for all word pairs ij in a given corpus. What do we mean by J appears in context of I? Simply that word J is present in the vicinity of word I, either right next to it or a few words away. We count all such occurrences of I and J in our text collection and then normalize the count to get a probability. Then, a random vector is initialized for each word, actually two vectors, one for the word when it is acting as a context, and one when it is acting as the target. So far so good. Now, for any pair of words ij, we want the dot product of their word vectors, wi times wj, to be equal to their co-occurrence probability. Using this as our goal and a suitable loss function, we can iteratively optimize these word vectors. The result should be a set of vectors that capture the similarities and differences between individual words. If you look at it from another point of view, we are essentially factorizing the co-occurrence probability matrix into two smaller matrices. This is the basic idea behind GLOVE. All this sounds good, but why co-occurrence probabilities? Consider two context words, say ice and steam, and two target words, solid and water. You would come across solid more often in the context of ice than steam, right? But water could occur in either context with roughly equal probability. At least that's what we would expect. Surprise! That's exactly what co-occurrence probabilities reflect. Given a large corpus, you'll find that the ratio of P solid given ice to P solid given steam is much greater than 1, while the ratio of P water given ice and P water given steam is close to 1. Thus we see that co-occurrence probabilities already exhibit some of the properties we want to capture. In fact, one refinement over using raw probability values is to optimize for the ratio of probabilities. Now, there are a lot of subtleties here, not the least of which is the fact that the co-occurrence probability matrix is huge. At the same time, co-occurrence probability values are typically very low, so it makes sense to work with the log of these values. I encourage you to read the original paper that introduced GLOVE to get a better understanding of this technique.
Word embeddings are fast becoming the de facto choice for representing words, especially for use in deep neural networks. But why do these techniques work so well? Doesn't it seem almost magical that you can actually do arithmetic with words, like woman minus man plus king equals queen? The answer might lie in the distributional hypothesis, which states that words that occur in the same contexts tend to have similar meanings. For example, consider this sentence. Would you like to have a cup of blank? Okay, how about I like my blank black? One more. I need my morning blank before I can do anything. What are you thinking? Tea? Coffee? What gave you the hint? Cup, black, morning? But it could be either of the two, right? And that's the point. In these contexts, tea and coffee are actually similar. Therefore, when a large collection of sentences is used to learn an embedding, words with common context words tend to get pulled closer and closer together. Of course, there could also be contexts in which tea and coffee are dissimilar. For example, blank grounds are great for composting. Or, I prefer loose leaf blank. Here we are clearly talking about coffee grounds and loose leaf tea. How do we capture these similarities and differences in the same embedding? By adding another dimension. Let's see how. Words can be close along one dimension. Here, tea and coffee are both beverages, but separated along some other dimension. Maybe this dimension captures all the variability among beverages. In a human language, there are many more dimensions along which word meanings can vary, and the more dimensions you can capture in your word vector, the more expressive that representation will be. But how many dimensions do you really need? Consider a typical neural network architecture designed for an NLP task, say word prediction. It's common to use a word embedding layer that produces a vector with a few hundred dimensions. But that's significantly small compared to using one-hot encodings directly, which are as large as the size of the vocabulary, sometimes in tens of thousands of words. Also, if you learn the embedding as part of the model training process, you can obtain a representation that captures the dimensions that are most relevant for your task. This often adds complexity. So unless you're building a model for a very narrow application like one that deals with medical terminology, you can use a pre-trained embedding as a lookup, for example, word2vec or glove. Then you only need to train the layer specific to your task. Compare this with a network architecture for a computer vision task, say image classification. The raw input here is also very high dimensional. For example, even a 128 by 128 image contains over 16,000 pixels. We typically use convolutional layers to exploit the spatial relationships in image data and reduce this dimensionality. Early stages in visual processing are often transferable across tasks, so it is common to use some pre-trained layers from an existing network like AlexNet or VTG16 and only learn the later layers. Come to think of it, using an embedding lookup for NLP is not unlike using pre-trained layers for computer vision. Both are great examples of transfer learning. The final stage in this process is what I like to call modeling. This includes designing a model, usually a statistical or machine learning model, fitting its parameters to training data using an optimization procedure, and then using it to make predictions about unseen data. The nice thing about working with numerical features is that it allows you to utilize pretty much any machine learning model. This includes support vector machines, decision trees, neural networks, or any custom model of your choice. You could even combine multiple models to get better performance. How you utilize the model is up to you. You can deploy it as a web-based application, package it up into a handy mobile app, integrate it with other products, services, and so on. The possibilities are endless.
Hi again. So in the last couple lessons, Ortal and Luis introduce you to recurrent neural networks and LSTMs. In this lesson, Matt and I will be going over some implementations of these networks. Because RNNs have a kind of built-in memory, they're really useful for tasks that are time or sequence dependent. For example, RNNs are used in tasks like time series prediction, as in predicting the weather over time. or in text generation, for which the order of words and characters in a sentence is really important. The challenges in designing and implementing any kind of RNN are really twofold. First, how can we pre-process sequential data, such as a series of sentences, and convert it into numerical data that can be understood by a neural network? Second, how can we represent memory in code? I'll address these challenges in a couple of code examples, and by the end of the lesson, you'll have learned to build and train a character-level RNN, specifically an LSTM that's trained on the text of Tolstoy's Anna Karenina. The LSTM will take in one character as input and produce a predicted next character as output. You can train such an LSTM on any body of text, such as a publicly available book or television script, and generate some really interesting results. So next, let's talk more about how we can build RNNs that learn from sequential data. Okay, to introduce you to RNNs in PyTorch, I've created a notebook that will show you how to do simple time series prediction with an RNN. Specifically, we'll look at some data and see if we can create an RNN to accurately predict the next data point given a current data point. And this is really easiest to see in an example, so let's get started. I'm importing our usual resources, and then I'm actually going to create some simple input and target training data. A classic example is to use a sine wave as input because it has enough variance and shape to be an interesting task, but it's also very predictable. So I want to create a sample input and target sequence of data points of length 20, which I specify here as sequence length. Recall that RNNs are meant to work with sequential data, and so this sequence length is just the length of a sequence that it will look at as input. Often the sequence length will indicate the number of words in a sentence, or just some length of numerical data, as is the case here. So in these two lines, I'm just going to generate the start of a sine wave in a range from 0 to pi time steps. And at first, I'm going to create a number of points that's sequence length 20 plus 1. Then I'm going to reshape my sine wave data to give it one extra dimension, the input size, which is just going to be 1. Then to create an input and target sequence of the length I want, I'm going to say an input x is equal to all but the last point in data, and the target y is equal to all but the first point. So x and y should contain 20 data points and have an input size of 1. Finally, I'm going to display this data using the same x-axis. You can see the input x is in red, and the target y is shifted over by 1 in blue. So if we look at this point as an example, at the same time step, y is basically x shifted one time step in the future. And that's exactly what we want. So now we have our training data, and the next step is defining an RNN to learn from this data. We can define an RNN as usual, which is to say as a class using PyTorch's NN library. The syntax will look similar to how we've defined CNNs in the past. Let's actually click on the RNN documentation to read about the parameters that a recurrent layer takes in as input. Okay, so here's the documentation for an RNN layer. We can see that this layer is responsible for calculating a hidden state based on its inputs. Now to define a layer like this, we have these parameters: an input size, a hidden size, a number of layers, and a few other arguments. The input size is just the number of input features. And in our specific case, we're going to have inputs that are 20 values in sequence and 1 in input size features. This is sort of like when we thought about the depth of an input image when we made CNNs. Next, we have a hidden size that defines how many features the output of an RNN will have and its hidden state. We also have a number of layers, which if it's greater than 1, just means we're going to stack 2 RNNs on top of each other. Lastly, I want you to pay attention to this batch first parameter. If it's true, that means the input and output tensors that we provide are going to have the batch size as the first dimension, which in most cases that we go through will be true. Okay, so this is how you define an RNN layer, and later in the forward function, we'll see that it takes in an input and an initial hidden state, and it produces an output and a new hidden state. Okay, back to our notebook. Here I'm defining an RNN layer, self.rnn. This RNN is taking in an input size and a hidden dimension that defines how many features the output of this RNN will have. Then it takes in a number of layers, which allows you to create a stacked RNN if you want, and this is typically a value kept between 1 and 3 layers. Finally, I'm setting batch first to true because I'm shaping the input such that the batch size will be the first dimension. Okay, then to complete this model, I have to add one more layer, which is a final fully connected layer. This layer is responsible for producing the number of outputs, output size, that I want, given the output of the RNN. So all of these parameters are just going to be passed into our RNN when we create it. You'll also note that I'm storing the value of our hidden dimension so I can use it later in our forward function. In the forward function, I'm going to specify how a batch of input sequences will pass through this model. Note that this forward takes in an input x and a hidden state. The first thing I'm doing is grabbing the batch size of our input, calling x.size of 0. Then I'm passing my initial input and hidden state into the RNN layer. This produces the RNN output and a new hidden state. Then I'm going to call view on the RNN output to shape it into the size I want. In this case, that's going to be batch size times sequence length rows and the hidden dimension number of columns. This is sort of like a flattening step where I'm preparing the output to be fed into a fully connected layer. So I'll pass this shaped output to the final fully connected layer and return my final output here and my hidden state generated from the RNN. Now, as a last step here, I'm going to actually create some text data and a test RNN and see if it's working as I expect. The most common error I get when programming RNNs is that I've messed up the data dimensions somewhere. So I'm just going to check that they're as I expect. So here I'm just creating a test RNN with an input and output size of 1, a hidden dimension of 10, and a number of layers equal to 2. And you can change the hidden dimension and number of layers. I basically just want to see that this is making the shape of outputs I expect. So here I'm creating some test data that's our sequence length long. I'm converting that data into a tensor data type and unsqueezing the first dimension to give it a batch size of 1 as a first dimension. Then I'm going to print out this input size, and I'll pass it into our test RNN as input. Recall that this takes an initial hidden state, and an initial one here is just going to be none. Then this should return an output and a hidden state, and I'm going to print out those sizes as well. Okay, so our input size is a 3D tensor, which is exactly what I expect. Its first dimension is 1, our batch size, then 20, our sequence length, and finally our input number of features, which is just 1, as we specified here. The output size is a 2D tensor. And this is because in the forward function of our model definition, I actually smushed the batch size and sequence length into one parameter. So batch size times sequence length is 20, and then we have an output size of 1. Finally, we have our hidden state. Now, the first dimension here is our number of layers that I specified in the model definition, 2. Next, we have the value 1, which is just the batch size of our input here. And finally, the last dimension here is 10, which is just our hidden dimension. So all of these look pretty good and as I expect, and I can proceed. Next, I'll show you how to train a model like this. Last time, we defined a model, and next I want to actually instantiate it and train it using our training data. First, I'll specify my model hyperparameters. The input and output will just be 1. It's just one sequence at a time that we're processing and outputting. Then I'll specify a hidden dimension, which is just the number of features I expect to generate with the RNN layer. I'll set this to 32, but for a small dataset like this, I may even be able to go smaller. And I'll set n layers to 1 for now, so I'm not stacking any RNN layers. I'll create this RNN and print it out. I should see the variables that I expect, my RNN layer with an input size and hidden dimension, and a linear layer with an input number of features and output number. Before training, I'm defining my loss and optimization functions. Now in this case, we're training our model to generate data points that are going to be basically coordinate values. So to compare a predicted and ground truth point like this, we'll use a regression loss because this is just a quantity rather than something like a class probability. So for the loss function, I'm going to use mean squared error loss, which will just measure the distance between 2 points. And I'll use an atom optimizer, which is standard for recurrent models, passing in my parameters and a learning rate. Next, I have a function train that's going to take in an RNN, a number of steps to train for, and a parameter that will determine when it will print out loss statistics. Now, at the very start of this function, I'm initializing my hidden state. At first, this is going to be nothing, and it will default to a hidden state of all zeros. Then let's take a look at our batch loop. Now, this is a little unconventional, but I'm just generating data on the fly here according to how many steps we'll train for. So in these lines, I'm just generating a sequence of 20 sine wave values at a time, as we saw when I generated data at the start. Here I'm getting my input x and a target y that's just shifted by one time step in the future. Here I'm converting this data into tensors, unsqueezing the first dimension of our x tensor to give it a batch size of 1. Then I can pass my input tensor into my RNN model. So this is taking in my x input tensor and my initial hidden state at first, and it produces a predicted output and a new hidden state. And next is an important part. I want to feed this new hidden state into the RNN as input at the next time step when we loop around once more. And so I'm just copying the values from this produced hidden state into a new variable. This essentially detaches the hidden state from its history, and I will not have to backpropagate through a series of accumulated hidden states. So this is what's going to be passed as input to the RNN at the next time step, our next point in our sequence. So then I have the usual training commands. I zero out any accumulated gradients, calculate the loss and perform a backpropagation and optimization step. And down here, I have some code to print out the loss and show what our input and predicted outputs are. Finally, this function returns a trained RNN, which will be useful if you want to save a model, for example. So let's run this code. I'll choose to train our RNN that we defined above for 75 steps. And I'll print out the result every 15 steps. We can see the mean squared error loss here, and the difference between our red input and our blue output values. Recall that we want the blue output values to be one time step in the future when compared to the red ones, so it starts out pretty incorrect. Then we can see the loss decreases quite a lot after the first 15 steps, and our blue line is getting closer to our red one. And as we train, the blue predicted line gets closer to what we know our target is. At the end of 75 steps, our loss is pretty low, and our blue line looks very similar to what we know our output should be. If we look at the same time step for a red input dot and a blue input dot, we should see that the blue input is one time step shifted in the future, and it's pretty close. You could imagine getting even better performance after training for more steps, or if you wanted to add more layers to your RNN. So in this video, I wanted to demonstrate the basic structure of a simple RNN, and show you how to keep track of the hidden state and represent memory over time as you train. You could imagine doing something very similar with data about world temperature or stock prices, which are a little bit more complicated than this, but it would be really interesting to see if you could predict the future given that kind of data. Okay, so this was just an example. You can check out this code in our program GitHub, which is linked below. And I encourage you to play around with these model parameters until you have a good handle on the dimensions of an RNN input and output, and how hyperparameters might change how this model trains. Next, Matt and I will go over an exercise in generating text.
Coming up in this lesson, you'll implement a character-wise RNN. That is, the network will learn about some text one character at a time, and then generate new text one character at a time. Let's say we want to generate new Shakespeare plays. As an example, to be or not to be. We'd pass the sequence into our RNN one character at a time. Once trained, the network will generate new text by predicting the next character based on the characters it's already seen. So then, to train this network, we want it to predict the next character in the input sequence. In this way, the network will learn to produce a sequence of characters that look like the original text. Let's consider what the architecture of this network will look like. First, let's unroll the RNN so we can see how this all works as a sequence. Here we have our input layer, where we'll pass in the characters as one-hot encoded vectors. These vectors go to the hidden layer. The hidden layer is built with LSTM cells, where the hidden state and cell state pass from one cell to the next in the sequence. In practice, we'll actually use multiple layers of LSTM cells. You just stack them up like this. The output of these cells go to the output layer. The output layer is used to predict the next character. We want the probabilities for each character, the same way you did image classification with the CovNet. That means that we want a softmax activation on the output. Our targets here will be the input sequence, but shifted over one, so that each character is predicting the next character in the sequence. Again, we'll use cross-entropy loss for training with gradient descent. When this network is trained up, we can pass in one character and get out a probability distribution for the likely next character. Then we can sample from that distribution to get the next character. Then we can take that character, pass it in, and get another one. We keep doing this, and eventually we'll build up some completely new text. We'll be training this network on the text from Anna Karenina, one of my favorite books. It's in the public domain, so it's free to use however you want. Also, it's an amazing novel. One of the most difficult parts of building networks for me is getting the batches right. It's more of a programming challenge than anything deep learning specific. So here I'm going to walk you through how batching works for RNNs. With RNNs, we're training on sequences of data like text, stock values, audio, etc. By taking a sequence and splitting it into multiple shorter sequences, we can take advantage of matrix operations to make training more efficient. In effect, the RNN is training on multiple sequences in parallel. Let's look at a simple example, a sequence of numbers from 1 to 12. We can pass these into an RNN as one sequence, but what's better, we could split it in half and pass in two sequences. The batch size corresponds to the number of sequences we're using, so here we'd say the batch size is 2. Along with the batch size, we also choose the length of the sequences we feed to the network. For example, let's consider using a sequence length of 3. Then the first batch of data we pass into the network are the first 3 values in each mini-sequence. The next batch contains the next 3 values, and so on until we run out of data. We can retain the hidden state from one batch and use it at the start of the next batch. This way, the sequence information is transferred across batches for each mini-sequence. Next up, you'll see how to actually build a recurrent network. Cheers!
This is a notebook where you'll be building a character-wise RNN. You're going to train this on the text of Anna Karenina, which is a really great but also quite sad book. The general idea behind this is that we're going to be passing one character at a time into a recurrent neural network. We're going to do this for a whole bunch of text, and at the end what's going to happen is that our network is going to be able to generate new text one character at a time. And this is the general structure. We have our input characters, and we want to one-hot encode them. This one-hot vector will be fed into a hidden recurrent layer, and then the hidden layer has 2 outputs. First, it produces some RNN output, and it produces a hidden state, which will continue to change and be fed to this hidden layer at the next time step in a sequence. And we saw something similar in the last code example. So our recurrent layer keeps track of our hidden state, and its output goes to a final fully connected output layer. Our linear output layer will produce a series of character class scores. So this output will be as long as our input vector, and we can apply a softmax function to get a probability distribution for the most likely next character. So this network is based off of Andrei Karpathy's post on RNNs, which you can find here. It's a really good post, and so you can check out these links to read more about RNNs. Now this notebook is broken into a small series of exercises that you can implement yourself. And for each exercise, I'm also going to provide a solution to consult. I recommend that you open the exercise notebook in one window and watch videos in another. That way you can work alongside me. Okay, so first things first, I'm loading in and taking a look at our text data. Here I'm loading in the Anna Karenina text file, and I'm printing out the first 100 characters. The characters are everything from letters to spaces to new line characters. And we can see the classic first line. Happy families are all alike. Every unhappy family is unhappy in its own way. Then I'll actually want to turn our text into numerical tokens. This is because our network can only learn from numerical data, and so we want to map every character in the text to a unique index. So first off, with the text, we can just create our unique vocabulary as a set. Sets are a built-in Python data structure, and what this will do is look at every character in the past in text, separate it out as a string, and get rid of any duplicates. So cars is going to be a set of all our unique characters. This is also sometimes referred to as a vocabulary. Then I'm creating a dictionary from our vocabulary of all our characters that maps the actual character to a unique integer. So it's just giving a numerical value to each of our unique characters and putting it in a dictionary int2char. Then I'm doing this the other way, where we have a dictionary that goes from integers to characters. Recall that any dictionary is made of a set of key and value pairs. In the int2char case, the keys are going to be integers and the values are going to be string characters. In the char to int case, our keys are going to be the characters and our values are going to be their unique integers. So these basically give us a way to encode text as numbers. And here I'm doing just that. I'm encoding each character in the text as an integer. This creates an encoded text, and just like I printed the first 100 characters before, I can print the first 100 encoded values. If you look at the length of our unique characters, you'll see that we have 83 unique characters in the text, and so our encoded values will fall in this range. You can also see some repeating values here, like 82, 82, 82, and 19, 19. And if we scroll back up to our actual text, we can surmise that the repeated 82s are probably this new line character, and 19 is maybe a P. Okay, so our encodings are working, and now what we want to do is turn these encodings into one-hot vectors that our RNN can take in as input, just like in our initial diagram. And here I've actually written a function that takes in an encoded array and turns it into a one-hot vector of some specified length. And I can show you what this does with an example below. I've made a short test sequence, 351, and a vector length that I specify, 8. So I'm passing this test sequence and the number of labels that I expect into our one-hot function. And I can see that the result is an array of 3 one-hot vectors. All of these vectors are of length 8, and the index 3, 5, and 1 are on for their respective encodings. Now for our vocabulary of 83 characters, these are just going to be much longer vectors. Cool, okay, so we have our pre-processing functions and data in place, And now your first task will be to take our encoded characters and actually turn them into mini batches that we can feed into our network. So as Matt mentioned before, the idea is that we actually want to run multiple sequences through our network at a time, where one mini batch of data contains multiple sequences. So here's an example starting sequence. If we say we want a batch size of 2, we're going to split this data into 2 batches. Then we'll have these sequence length windows that specify how big we want our sequences to be. In this case, we have a sequence length of 3, and so our window will be 3 in width. And for a batch size of 2 and sequence length of 3, these values will make up our first mini batch. And we'll just slide this window over by 3 to get the next mini batch. So each mini batch is going to have the dimensions batch size by sequence length. In this case, we have a 2 by 3 kind of window on our encoded array that we pass into our network. And if you scroll down, I have more specific instructions. The first thing you're going to be doing is taking in an encoded array, and you'll want to discard any values that don't fit into completely full mini batches. Then you'll want to reshape this array into batch size number of rows. Finally, once you have that batch data, you're going to want to create a window that iterates over the batches a sequence length at a time to get your mini batches. So here's the skeleton code. Your array is going to be some encoded data, then you have a batch size and sequence length. And basically, you want to create an input x that should be a sequence length or a number of time steps wide and a batch size tall. This will make up our input data, and you'll also want to provide targets. The targets y for this network are going to be just like the input characters x, only shifted over by 1. And that's because we want our network to predict the most likely next character or some input sequence. So you'll have your input sequence x and our targets y shifted over by 1. Then finally, when we call getBatches, we're going to create a generator that iterates through our array and returns x and y with this yield command. Okay, I'll leave implementing this batching function up to you. You can find more information about how you can do this in the notebook. And there's some code for testing out your implementation below. In fact, this is what your batches should look like when you run this code. And if you need any help or just want to see my solution, go ahead and check out the solution video next. So this is my complete getBatches code that generates mini batches of data. So the first thing I wanted to do here is get the total number of complete batches that we can make, n batches. And to do that, I first calculated how many characters were in a complete mini batch. So in one mini batch, there's going to be batch size times sequence length number of characters. Then the number of complete batches that we can make is just the length of the array divided by the total number of characters in a mini batch. This double slash is an integer division, which will just round down any decimal left over from this division. And with that, we have the number of completely full batches that we can make. Then we get our array, and we take all the characters in the array up to n batches times this total character size for a mini batch. So here we're making sure that we're keeping only enough characters to make full batches. And we may lose some characters here, but in general, you're going to have enough data that getting rid of a last unfull batch is not really going to matter. Next, with reshaping, we can take our array and we can make the number of rows equal to our batch size. And that's just how many sequences we want to include in a mini batch. So we just say we want the number of rows to be batch size, and then we put this -1. -1 here is kind of a dimension placeholder, and it'll just automatically fill up the second dimension to whatever size it needs to be to accommodate all the data. Then finally, I'm iterating over my batch data using a window of length sequence length. So here I'm taking in our reshaped complete array and then looking at all our rows, all our batches, and the columns are in a range from n to n plus sequence length, which makes our sequence length window. This completes x, our input mini batch. Then what I did here for the targets, y, is I just initialized an array of all zeros that's the same shape as x, and I just kind of filled it up with values from our x array shifted by 1. From the start to the end, I've just shifted over x by 1. And then in the case of reaching the very end of our array, I'm going to make the last element of y equal to the first element in our array. I'm not super sure why most people do it this way, wrapping our array around so that the last element of y is the first element of x. But I've seen this many times, and so I did it in this cyclical way, and it seems like the network trains perfectly fine doing this, so it does not seem to be a problem. The main thing is we want x and y to be the same size. Okay, so if you did this right, and you went to test your implementation, you should have gotten batches that look something like this. Right here we have a batch size of 8, so we have 8 rows here. And then we're just printing out the first 10 items in a sequence, so you should see 10 items here. And the important thing to note here is that you want to make sure that the elements in X, like the actual encoded values, are shifted over by 1 in Y. So we have 51 as the first item here and as the 0th item here, then 23 and 23. Likewise, 55 is here and 55 is here in Y. I basically want to make sure that everything is shifted over correctly, and this looks good. So now that we have our batch data, the next step we'll talk about is actually building the network. Alright, so we have our mini batches of data, and now it's time to define our model. This is a little diagram of what the model will look like. We'll have our characters put into our input layer and then a stack of LSTM cells. These LSTM cells make up our hidden recurrent layer, and when they look at a mini batch of data as input, they'll look at one character at a time and produce an output and a hidden state. So we'll pass an input character into our first LSTM cell, which produces a hidden state. Then at the next time step, we'll look at the next character in our sequence and pass that into this LSTM cell, which will see the previous hidden state as input. You've so far seen this behavior in a one-layer RNN, but in this case we'll plan on using a two-layer model that has stacked LSTM layers. And that means that the output of this LSTM layer is going to go to the next one as input. And each of these cells is sharing its hidden state with the next cell in the unrolled series. Finally, the output of the last LSTM layer will include some character class scores that will be the length of our vocabulary. We'll put this through a softmax activation function, which we'll use to get the probability distribution for predicting the most likely next character. So to start you off on this task, you've been given some skeleton code for creating a model. First, we're going to check to see if a GPU is available for training. Then you'll see this class, character RNN. You can see that this character RNN class has our usual init and forward functions. And later, you've been given some code to initialize the hidden state of an LSTM layer. And I'll go over this in a moment. You can definitely take a look at this given code and how we're creating our initial character dictionaries, but you won't need to change it. We also have several parameters that are going to be passed in when a character RNN is instantiated, and I've saved some of these as class variables. So using these input parameters and variables, it will be up to you to create our model layers and complete the forward function. You'll first create an LSTM layer, which you can read about in the documentation here. We can see that an LSTM layer is created using our usual parameters: an input size, hidden size, number of layers, and a batch first parameter. We'll also add a dropout value. This introduces a dropout layer in between the outputs of LSTM layers if you've decided to stack multiple layers. So after you define an LSTM layer, I'll ask you to define two more layers, one dropout layer and a final fully connected layer for getting our desired output size. Once you've defined these layers, you'll move on to define the forward function. This takes in an input X and a hidden state. You'll pass this input through the layers of the model and return a final output and hidden state. You'll have to make sure to shape the LSTM output so that it can be fed into the last fully connected layer. Okay, then at the bottom here, you'll see this function for initializing the hidden state of an LSTM. An LSTM has a hidden and a cell state that are saved as a tuple, hidden. The shape of the hidden and cell state is defined first by the number of layers in our model, the batch size of our input, and then the hidden dimension that we specified in model creation. And in this function, we're initializing the hidden weights all to 0 and moving them to GPU if it's available. Okay, so all the code that you see, you don't need to change. You just need to define the model layers and feedforward behavior. If you've implemented this correctly, you should be able to set your model hyperparameters and proceed with training and generating some sample text. Try this out on your own, then next, check out my solution. Okay, so we wanted to define a character RNN with a two-layer LSTM. Here in my solution, I am running this code on GPU. And here's my code for defining our character level RNN. First, I've defined an LSTM layer, self.lstm. This takes in an input size, which is going to be the length of a one-hot encoded input character, and that's just the length of all of my unique characters. Then it takes a hidden dimension, a number of layers, and a dropout probability that we've specified. Remember that this will create a dropout layer in between multiple LSTM layers. And all of these are parameters that are going to be passed in as input to our RNN when it's constructed. Then I've set batch first to true because when we created our batch data, the first dimension is the batch size rather than the sequence length. Okay, next I've defined a dropout layer to go in between my LSTM and a final linear layer. Then I have FC, my final fully connected linear layer. This takes in our LSTM outputs, which are going to be dimension and hidden. and it's going to output our character class scores for the most likely next character. So these are the class scores for each possible next character. So this output size is the same size as our input, the length of our character vocabulary. Then I move to the forward function. I'm passing my input x and a hidden state to my LSTM layer here. This produces my LSTM output and a new hidden state. I'm going to pass the LSTM output through the dropout layer that I defined here to get a new output. Then I'm making sure to reshape this output so that the last dimension is our hidden dim. This -1 basically means I'm going to be stacking up the outputs of the LSTM. And finally, I'm passing this reshaped output to the final fully connected layer. Then I'm returning this final output and the hidden state that was generated by our LSTM. These two functions, in addition to the init hidden function, complete my model. Next, it's time to train. And let's take a look at the training loop that was provided. So this function takes in a model to train, some data and the number of epochs to train for, and a batch size and sequence length that define our mini batch size. It also takes in a few more training parameters. So first in here, I've defined my optimizer and my loss function. The optimizer is a standard atom optimizer with a learning rate set to the passed in learning rate up here. And the loss function is cross entropy loss, which is useful for when we're outputting character class scores. Here you'll see some details about creating some validation data and moving our model to GPU if it's available. And here you can see the start of our epoch loop. At the start of each epoch, I'm initializing the hidden state of our LSTM. Recall that this takes in the batch size of our data to define the size of the hidden state, and it returns a hidden in cell state that are all zeros. Then inside this epoch loop, I have my batch loop. This is getting our x and y mini batches from our getBatches generator. Remember that this function basically iterates through our encoded data and returns batches of inputs x and targets y. I'm then converting the input into a one-hot encoded representation. And I'm converting both x and y, our inputs and targets, into tensors that can be seen by our model. If GPU is available, I'm moving those inputs and targets to our GPU device. The next line that you see is making sure that we detach any passed-in hidden state from its history. Recall that the hidden state of an LSTM layer is a tuple, and so here we're getting the data as a tuple. Then we proceed with backpropagation as usual. We zero out any accumulated gradients and pass in our input tensors to our model. We also pass in the latest hidden state here, and this returns a final output and a new hidden state. Then we calculate the loss by looking at the predicted output and the targets. Recall that in the forward function of our model, I smushed the batch size and sequence length of our LSTM outputs into one dimension, and so I'm doing the same thing for our targets here. Then we're performing backpropagation and moving one step in the right direction, updating the weights of our network. Now before the optimization step, I've added one line of code that may look unfamiliar. I'm calling clip_grad_norm. Now this kind of LSTM model has one main problem with gradients. They can explode and get really, really big. So what we do is we can clip the gradients. We just set some clip threshold, and then if the gradient is larger than that threshold, we set it to that clip threshold. And in code we do this by just passing in the parameters and the value that we want to clip the gradients at. In this case, this value is passed in our train function as a value 5. Okay, so we take a backward step, then we clip our gradients, and we perform an optimization step. At the end here, I'm doing something very similar for processing our validation data, except not performing the backpropagation step. Then I'm printing out some statistics about our loss. Now with this train function defined, I can go about instantiating and training a model. In the exercise notebook, I've left these hyperparameters for you to define. I've set our hidden dimension to the value of 512 and our number of layers of 2, which we talked about before. Then I've instantiated our model and printed it out, and we can see that we have 83 unique characters as input, 512 as a hidden dimension, and 2 layers in our LSTM. For our dropout layer, we have the default dropout value of 0.5, and for our last fully connected layer, we have our input features, which is the same as this hidden dimension, and our output features, the number of characters. Then there are more hyperparameters that define our batch size, sequence length, and number of epochs to train for. Here I've set the sequence length to 100, which is a lot of characters, but it gives our model a great deal of context to learn from. I also want to note that the hidden dimension is basically the number of features that your model can detect, and larger values basically allow a network to learn more text features. There's some more information below in this notebook about defining hyperparameters. And in general, I'll try to start out with a pretty big model like this, multiple LSTM layers and a large hidden dimension. Then I'll basically take a look at the loss as this model trains, and if it's decreasing, I'll keep going. But if it's not decreasing as I expect, then I'll probably change some hyperparameters. So our text data is pretty large, and here I've trained our entire model for 20 epochs on GPU. I can see the training and validation loss over time decreasing. And around epoch 15, I'm seeing the loss sort of slow down a bit, but it actually looks like the validation and training loss are still decreasing even after epoch 20. So I could have stood to train for an even longer amount of time. So I encourage you to read this information about setting the hyperparameters of a model and really getting the best model. Then after you've trained a model, like I've just done, you can save it by name, and then there's one last step, which is using that model to make predictions and generate some new text, which I'll go over next. Now the goal of this model is to train it so that it can take in one character and produce a next character. And that's what this next step, making predictions, is all about. We basically want to create functions that can take in a character and have our network predict the next character. Then we want to take that character, pass it back in, and get more and more predicted next characters. We'll keep doing this until we generate a bunch of text. So you've been given this predict function, which will help with this. This function takes in a model and a current character, and its job is to basically give us back the encoded value of the predicted next character and the hidden state that's produced by our model. Okay, so let's see what it's actually doing step by step. It's taking in our input character and converting it into its encoded integer value. Then, as part of pre-processing, we're turning that into a one-hot encoded representation and then converting these inputs into a tensor. These inputs we can then pass to our model. And then you'll see a couple steps that are really similar to what we saw in our training loop. We put our inputs on a GPU if it's available, and we detach our hidden state from its history here. Then we pass in the inputs and the hidden state to our model, which returns an output and a new hidden state. And next, we're processing that output a little more. We're applying a softmax function to get p probabilities for the likely next character. So p is a probability distribution over all the possible next characters given the input character x. Now we can generate more sensible characters by only considering the k most probable characters. And so here we're giving you a couple lines of code to use top k sampling, which finds us the k most likely next characters. Then here we're adding an element of randomness, something that selects from among those top likely next characters. So then we have a most likely next character, and we're actually returning the encoded value of that character and the hidden state produced by our model. But we'll basically want to call the predict function several times, generating one character as output, then passing that in as input, and predicting the next and next characters. That brings me to our next function, sample. Sample will take in our trained model and the size of text that we want to generate. It will also take in prime, which is going to be a set of characters that we want to start our model off with. Lastly, it will take in a value for top k, which will just return our k most probable characters in our predict function. Okay, so in here, we're starting off by moving our model to GPU if it's available. And here we're also initializing the hidden state with a batch size of 1, because for one character that we're inputting at a time, the batch size will be 1. In this way, prediction is quite different than training a model. Then you'll see that we're getting each character in our prime word. The prime word basically helps us answer the question, how do we start to generate text? We shouldn't just start out randomly, so what is usually done is to provide a prime word or a set of characters. Here the default prime set is just the, THE. But you can pass in any set of characters that you want as the prime. The sample function first processes these characters in sequence, adding them to a list of characters. It then calls predict on these characters, passing in our model, each character, and hidden state, and this returns the next character after our prime sequence and a hidden state. So here we have all our prime characters. In the default case, this is going to be T, H, and E, and then we're going to append the next most likely character. So we're basically building up a list of characters here. Then we're going to generate more and more characters. In this loop, we're passing in our model and the last character in our character list. This returns the next character and a hidden state. This character is appended to our list and the cycle starts all over again. So predict is generating a next likely character, which is appended to our list, and then that goes back as input into our predict function. The effect is that we're getting next and next and next characters and adding them to our characters list. That is until we reach our desired text length. Finally, we join all these characters together to return a sample text. And here I've generated a couple samples. You can see that I've passed in my model that was trained for 20 epochs, and I've said generate a text that's 1,000 characters long, starting with the prime word Anna. I've also passed in a value for top k equal to 5. And you can see that this starts with the prime word and generates what might be thought of as a paragraph of text in a book. And even with just a few prime characters, our model is definitely making complete and real words that make sense, you know? The structure and spelling looks pretty good, even if the content itself is a little confusing. And here's another example where I've loaded in a model by name, and I'm using this loaded model to generate a longer piece of text, starting with the prime words "and Leven said." So this is pretty cool. A well-trained model can actually generate some text that makes some sense. It learned just from looking at long sequences of characters what characters were likely to come next. And then in our sampling and prediction code, we used top k sampling and some randomness in selecting the best likely next character. And you can train a model like this on any other text data. For example, you could try it on generating Shakespeare sonnets or another text of your choice. And great job on getting this far. You've really learned a lot about implementing RNNs in PyTorch. Welcome to this lesson on sentiment analysis with an RNN. Alright, so in this notebook, I want to give you one more LSTM example. And in this case, we'll actually be training an RNN to solve our sentiment analysis task from a few lessons ago. Sentiment analysis is all about taking in some text, in this case movie reviews, and predicting the sentiment of that review, so whether it's positive or negative. Recall that Andrew Trask showed you how to build a sentiment analysis model from scratch, and he also did some really cool visualizations with this data. And what I want to do now is use this as an opportunity to show you how well an RNN versus just a feed-forward network performs on this task. My thinking is that an RNN should work really well because we can include information about the sequence of words in a movie review. I've broken this notebook up into a series of exercises, and I'll leave them pretty open-ended. You'll be tasked with pre-processing some text data and building a model that includes both an embedding and LSTM layer. I'll also be showing you a few more things that are useful to know about batching data and making predictions. Next, you'll be able to access this notebook, and I'd suggest that you keep the exercise notebook open. You can have it open in one tab and watch my exercise and solution videos in another, moving back and forth between absorbing information and practicing what you've learned. So let's get started with sentiment analysis. First, I'm going to load in data from our data directory. In here, there are two files, reviews.txt and labels.txt. These are just the text files for our movie reviews data and their corresponding labels, positive or negative. So I'm going to load these in and print out some of their contents. Here you can see some example review text that's talking about a comedy called Bromwell High. And here you see some of the text in the labels file, which just has lines positive and negative. And actually this looks like just one review, and I want to see if I can print out more than one. Alright, so here I've started printing out a second review here, and you can see that these two are separated by new line characters, much like positive and negative are separated by new lines. Now we already know that we need to pre-process this data and tokenize all of the words in our vocabulary so that we have numerical data to feed to our model later. Since we're using an embedding layer, we'll need to encode each word as an integer, and we'll also want to clean up our data a bit. The first pre-processing steps I'll want to take are turning our text to lowercase and getting rid of extraneous punctuation. Punctuation that, in this case, will not really have any bearing on whether our review is classified as positive or negative. Okay, so in this cell, I'm converting all of my review text to lowercase, and I'm getting rid of everything that is punctuation. And I'm using a built-in Python list here, which is from string import punctuation, and I'm going to print out what all is in there. So punctuation is just a list of all of these punctuation characters. Then for our reviews, I'm looking at every character, and if it's not in the punctuation list, I'm keeping it. This gives me a version of the review text that is all text, no punctuation. So I'm storing that in this variable, all text. Next, I know that my reviews are separated by new line characters, /n. So to separate out our reviews, I'm going to split the text into each review using /n as the delimiter here. Then I can combine all the reviews back together as one big string. And finally, I get to my end goal, which is splitting that text into individual words. So I'll run this cell and print out the first 30 words. And it looks just as I expect. Essentially the original text that I printed out, only all the punctuation is removed, and we've separated everything into individual words. So our data is in good shape, and by now you should know what's coming next. We have to take our word data and our label text data and convert this into numerical data. Your first couple of exercises will be to create a dictionary, vocab to int, that can convert any unique word into an integer token. Then using this dictionary, I want you to create a new list of tokenized words. All the words in our data, but converted into their integer values. I'd also like it so that our dictionary maps more frequent words to lower integer tokens. One important thing to note here is that later we're going to pad our input vectors with zeros, so I actually do not want 0 as a word token. I want the tokenized values to start at 1. And so the most common word in our vocabulary should be mapped to the integer value 1. So create that dictionary, use it to tokenize our words, and then store those tokens in a list reviews ints. Below this, I provided some code that lets you sort of test your implementation. It'll print the length of your vocabulary, and it will print the first review in your tokenized review list. Your next and similar task is going to be to encode our label text into numerical values. We saw that this text was just lines of positive or negative, and I want you to create an array, encoded labels, that converts the word positive to 1 and negative to 0. I'm not providing any testing code here, but I encourage you to get in the habit of testing out your own code, piece by piece as you build. It's good practice and can be as simple as a few print statements to check that your data is converted as you expect, or that it's the correct size, and so on. These checks can really save some time later on, because these code blocks really build on one another, and it's good to debug early and often. Okay, so try encoding all of our words and labels on your own. And if you get stuck or want to check your solution, feel free to look at the solution video next. First, here's how I went about creating a vocab to int dictionary and encoding our word data, and there are a few ways to do this. I chose to use this imported counter to create a dictionary that maps the most common words in our reviews text to the smallest integers. So the first thing I'm doing is to get a count of how many times each of our words actually appears in our word data, using counter and passing in our words. Then with these counts, I'm creating a sorted vocabulary. This sorts each unique word by its frequency of occurrence. So this vocab should hold all of the unique words that make up our word data, without any repeats, and it will be sorted by commonality. I also know that I want to start encoding my words with the integer value of 1 rather than 0. So the most common word, like the or of, should actually be encoded as 1. And I'm making sure that we start our indexing at 1 by using enumerate and passing in our vocab and our starting index, 1. Enumerate is going to return a numerical value, II, and a word in our vocabulary. And it will do this in order, so our first index is going to be 1, and the first word is going to be the most common word in our sorted vocabulary. So to create the dictionary vocab to int, I'm taking each unique word in our vocab and mapping it to an index starting at the value 1. Great. Next, I'm using this dictionary to tokenize all of our word data. So here I'm looking at each individual review. Each of these is one item in review split from before when I separated reviews by the new line character. Then for each word in a review, I'm using my dictionary to convert that word into its integer value. And I'm appending the tokenized review to reviews ints. So the end result will be a list of tokenized reviews. And here in the cells below, I'm printing out the length of my dictionary and my first sample encoded review. I can see that my dictionary is a bit over 74,000 words long, which means that we have this many unique words that make up our reviews data. And let's take a look at this tokenized review. I'm not seeing any 0 values, which is good, and these encoded values look as I might expect. So I've successfully encoded the review words, and I'll move on to the next task, which is encoding our labels. So in this case, I want to look at my labels text data and turn the word positive into 1 and negative into 0. Now we haven't much processed our labels data, and I know, much like the reviews text, that a new label is on every new line in this file. So I can get a list of labels, labels split, by splitting our loaded in data using the new line character as a delimiter. Then I just have a statement that says, for every label in this label split list, I'm going to add 1 to my array if it reads as positive, and a 0 otherwise. And I'm wrapping this in mp.array. And that's all I need to do to create an array of encoded labels. All right, this is a good start. There are still a few data cleanup and formatting steps that I'll want to take before we get to defining our model. So let's address those tasks next. After encoding all our word and label data, as an additional preprocessing step, we want to make sure that our reviews are in good shape for standard processing. That is, our network will expect a standard input text size, and so we'll want to shape our reviews into a consistent specific length. There are 2 things we'll need to do to approach this task. First, I'm going to take a look at the review data and see, do we have any especially short or long reviews that might mess with our training process? I'll especially look to see if we have any reviews of length 0, which will not provide any text information and will just act as noisy data. If I find any of those 0 length reviews, I'll want to remove them from our data entirely. Then second, I'll look at the remaining reviews, and for really long reviews, I'll actually truncate them at a specific length. I'll do something similar for shortish reviews and make sure that I'm creating a set of reviews that are all the same length. This will be our padding and truncation step, where we basically pad our data with columns of zeros or remove columns until we get our desired input shape. Okay, before we pad our review text, we should check for reviews of length 0. And the way I'm going to do this is to use a counter. For each review length that's currently in our data, whether that's a length of 0 or thousands of words, I'll look at how many reviews are of that length. So this returns a dictionary of review lengths and account for how many of our reviews fall into those lengths. So here I'm looking at how many of our reviews are 0 length, and I'll also print out the longest review length just to see. So when I run the cell, I can see that I have one review that is 0 length, and that my longest review has over 2,000 words in it. This 0 length review is just going to add noise into our data set. And so next, your task will be to create a new list of reviews ints and an array of encoded labels where any reviews of 0 length will be removed from this data. So remove any 0 length reviews from reviews ints and remove that corresponding label as well. In this particular case, after running this cell, I expect to see that one of our reviews was removed. Try to solve this task on your own, and next I'll present my solution and introduce you to your next exercise. So last time, we noticed that we had one review with 0 length in our dataset. This review will not contribute any meaningful training information, and so here I'm removing any reviews of 0 length from our reviews ints list. And I'll do the same thing with their corresponding label. The way I went about this task was, I thought, okay, I'm going to want to find any reviews of 0 length and remove that data from my existing reviews ints and encoded labels data. So I first identified the indices in our data that I want to keep, which I'll call my non-zero indices. I'm checking the length of each review in our reviews ints data. If the length is not equal to 0, that means I want to keep it, and I'm recording its index in our list of non-zero indices. Then I'm just getting those indices from my existing reviews ints list and encoded labels array. And I'm storing the new clean data in these variables of the same name. And when I do my length check, I can see that this has effectively removed one review from our data. In this case, there was only one review of 0 length, so this looks good. Now the next thing I want to deal with is very long review text data, and standardizing the length of our reviews in general. We saw that the maximum review length was about 2,500 words, and that's going to be too many steps for our RNN. In cases like this, I'll want to truncate this data to a reasonable size and number of steps. This brings me to the next exercise. To deal with both short and very long reviews, we'll either pad or truncate all our reviews to a specific sequence length. For reviews that are shorter than some sequence length, we'll pad it on the left with zeros. For reviews longer than the sequence length, we can truncate them to the first sequence length worth of words. So here's a padding example. Say we have a short sequence of words, and we specify that we want a sequence length equal to 10. The resultant padded sequence should be this, padded on the left with 7 zeros, and the original 3 word tokens are at the end. Now, in the case of a long review, it would just be cut at the sequence length of 10. This is just a small example, and for our movie review data, a good sequence length is going to be around 200. So as an exercise, I want you to complete this function pad features. This takes in our list of reviews ints and a sequence length, and it should either pad or truncate every review in the past in list. It should return an array of transformed reviews, which I'll call our features, which are our tokenized reviews of the same sequence length. And you'll often hear transformed data like this referred to as the features or input features for a model. So at the end, each of the rows in the features array will be a transformed review of a standard sequence length that we can then feed into a model as input. So try to solve this, and in the next cell I've included some print statements and assertions that act as tests on the shape of your features array. This will help you check your work, and next I'll go over one solution. So here's my solution for creating an array of features, reviews that have either been padded on the left with zeros until they're sequence length long, or truncated at that length. First, I'm actually creating an array of zeros that's just the final shape that I know I want. That is, it should have as many rows as I have reviews in the input reviews ints data. And it has as many columns as the specified sequence length. And this will just hold all the 0 integers for now. Then for each review in my list, I'll put it as a row in my features array. The first review is going to go in the first row, and the second in the second, and so on. And I started out thinking of my short review case. I want to keep a left padding of zeros up until I reach where that review can fill the remaining values. So I'm looking at filling my features, starting at the index that's at the end of the features row, minus the length of the input review. So if a review is short, this means our features are going to keep the zeros, which are padding, on the left, and the review tokens will be on the right side. It turns out that I only have to add one more piece to this line to make this work for long reviews too. Here, for any review, including those longer than the given sequence length, I'm truncating them at that sequence length, and this should fill the corresponding features row. So this loop will do this for every review in reviews ints, and then it returns these features. Below, I'm running my test code. Here, I'm creating features, passing in my list of reviews ints, and a sequence length equal to 200. I don't trigger any of these error messages, so I know my dimensions are correct, and I'm printing out the first 10 values of the first 30 rows here. And here's what these rows look like. A lot of these start with zeros, which is what I expect for left padding, and others have filled up these rows with various token values. So this is great, and I'll also add that, in this step, we've actually introduced a new token into our review features. Remember that before, all words in our vocabulary had an associated integer value, and we started tokenizing with the value 1. So in our vocab to int dictionary, we had integers from 1 up to 74,000 or so. And here, by adding 0 as padding, I've effectively inserted the 0 token into our vocabulary. Okay, now for your next and last data transformation exercise, with our data in nice shape, next, I want you to split the features and encoded labels into 3 different data sets: training, validation, and test sets. You'll need to create data sets for grouping our features and labels, like train X and train Y, for example. And we'll use these different sets to train and test our model. So I've defined a split fraction, split frac, as the fraction of data to keep in the training set. This is set to 0.8 or 80% of data. The 20% of the data that's left should be split in half to create the validation and testing data respectively. So I'll leave this as an exercise, and next I'll go over how I split the data, and I'll show you some PyTorch resources we can use to effectively batch and iterate through these different data sets. In this cell, I've split our features and encoded labels into training, test, and validation sets. I started by splitting our features and label data according to their split frac. So I'm reserving 80% of my data for training, and I'm basically getting the index at which I should split my features and label data based on this value 0.8. And actually, I could have just put in this variable here. Then I'm splitting my features first, getting the features up until my 80% split index. This makes up my training features, train X. Then I'm getting the remaining data, so after the split index. And that makes up my remaining X. Then I'm doing the exact same thing, but for my labels data, splitting it at the 80% index to get my training labels and my remaining data. Then I'm doing something similar all over again, only with the remaining data. I'm getting an index to split this data in half, so at the 0.5 mark. Then each half of our remaining X will make up our validation and test sets of features, and each half of remaining Y will make up our validation and test set of labels. And that's it. The last step I'm doing is checking my work and printing out the shapes of my features data. I can see that I have the largest number of reviews in my training set with a sequence length of 200, and my validation and test sets are of the same size. If you want, you can do the same thing for your labels data, and you should see the same number of rows here. So this is 80% of my data, 10%, and 10%. After creating training, test, and validation data, we want to batch this data so that we can train on batches at a time. Typically, you've seen this done with a generator function, which we could definitely do here, but I want to show you a really nice way to batch our datasets when we've split up our input features and labels like this. We can actually create data loaders for our data by following a couple of steps. First, we can use PyTorch's tensor dataset to wrap tensor data into a known format. And I can look at the documentation for this here. This dataset basically takes in any amount of tensors with the same first dimension, so the same number of rows, and in our case, this is our input features and label tensors. And it creates a dataset that can be processed and batched by PyTorch's data loader class. So once we create our data, wrapping it in a tensor dataset, we can then pass that to a data loader as usual. Data loader just takes in some data and a batch size. And it returns a data loader that batches our data as we typically might. This is a great alternative to creating a generator function for batching our data into full batches. The data loader class is going to take care of a lot of behind the scenes work for us. And here's what this looks like in code. First, I'm creating my tensor datasets. To create my training data, I'm passing in the tensor version of my train X and train Y that I created above. And torch.from NumPy just takes in NumPy arrays and converts them into tensors. So I'm doing that for my training, validation, and test data. And if you named your data differently above, you'll have to change those names here. In fact, I could have actually done these steps the other way around, creating a tensor dataset for all my data, and then splitting the data into different sets. Both approaches work. Then for each tensor dataset that I just created, I'm passing it into PyTorch's data loader, where I can specify a batch size parameter, equal to 50 in this case. So without the messiness of loops and yield commands, this defines training, validation, and test data loaders that I can use in my training loop to batch my data into the size I want. So this gives me 3 different iterators. And I just want to show you what a sample of data from this data loader looks like. I'm looking at our train loader and getting an iterator, then grabbing one batch of data using a call to next. So this should return some sample input features and some sample labels. Then I'm printing out the size of my input, which I can see is the batch size 50 and the sequence length 200. And the output label size, which is just 50, one label for each review in the input batch. And I see my tokens and the encoded labels as well. So this is looking really great. And next, we can proceed with defining and training a model on this data. By now, you've had a lot of practice with data processing and with defining RNNs, so I'm not going to give you too much guidance here when it comes to defining this model. Here's what it should look like generally. The model should be able to take in our word tokens, and the first thing that these go through will be an embedding layer. You know, we have about 74,000 different words, and so this layer is going to be responsible for converting our word tokens, our integers, into embeddings of a specific size. Now you could train a word-to-vec model separately and actually just use the learned word embeddings as input to an LSTM. But it turns out that these embedding layers are still useful even if they haven't been trained to learn the semantic relationships between words. So in this case, what we're mainly using this embedding layer for is dimensionality reduction. It will learn to look at our large vocabulary and map each word into a vector of a specified embedding dimension. Then after our embedding layer, we have an LSTM layer. This is defined by a hidden state size and number of layers, as you know. And at each step, these LSTM cells will produce an output and a new hidden state. The hidden state will be passed to the next cell as input, and this is how we represent a kind of memory in this model. The output is going to be fed into a sigmoid-activated, fully connected output layer. This layer will be responsible for mapping the LSTM layer outputs to a desired output size. And in this case, this should be the number of our sentiment classes, positive or negative. Then the sigmoid activation function is responsible for turning all of those outputs into a value between 0 and 1. This is the range we expect for our encoded sentiment labels. 0 is a negative and 1 is a positive review. So this model is going to look at a sequence of words that make up a review. And here we're interested in only the last sigmoid output, because this will produce the one label we're looking for at the end of processing a sequence of words in a review. So here's a little more explanation and some links to documentation if you need it. Then below, in this first cell, I'm going to check if a GPU is available for training. Then here, I want you to complete this model. It should take in all these parameters, our vocab size, output size, embedding dimension, hidden dimension, number of layers, and an optional dropout probability, and create an entire sentiment RNN model. You'll be responsible for completing the init and forward functions for this model. And remember that the output should just be the last value from our sigmoid output layer. I'll also ask you to complete the init hidden function for the LSTM layer. This should initialize the hidden and cell state to be all zeros and move them to GPU if available. I'd encourage you to look at the documentation when helpful or your other code examples. You should have all the information you need to complete this model on your own. If you're confident in your model definition, later in this code, you'll be able to define your model hyperparameters and train it. Next, I'll show you one solution for defining the sentiment RNN model. But I do think this is a fun task to try out on your own, in earnest too. I think it's a great exercise in thinking about how data is shaped as it moves through a model. So good luck.
Now that you have a solid foundation in neural networks, we are excited to teach you about convolutional neural networks. I'm happy to introduce you to Alexis Cook, an expert in the subject.
Hi everyone, I'm Alexis. Over the next several videos, I'll help you learn more about convolutional neural networks, which we'll also refer to as CNNs. For now, let's investigate some of their fascinating applications. CNNs achieve state-of-the-art results in a variety of problem areas, including voice user interfaces, natural language processing, and computer vision. In the field of voice user interfaces, Google made use of CNNs in its recently released WaveNet model, which we've linked to below. WaveNet takes any piece of text as input and does an excellent job of returning computer-generated audio of a human reading the text. What's really cool is that if you supply the algorithm with enough samples of your voice, it's possible to train it to sound just like you. As for the field of natural language processing, you'll see later that recurrent neural networks are used more frequently than convolutional neural networks. CNNs, however, can be used in this area too. We provide a link below that shows you how CNNs are used to extract information from sentences. This information can be used to classify sentiment. For example, is the writer happy or sad? If they're talking about a movie, did they like or dislike it? In this program, we'll focus on applications in computer vision and specifically work towards applying CNNs to image classification tasks. Given an image, your CNN will assign a corresponding label, which it believes summarizes the content of the image. This is a core problem in computer vision and has applications in a wide range of problem areas. For instance, CNNs are used to teach artificially intelligent agents to play video games, such as Atari Breakout. These CNN-based models are able to learn to play games without being given any prior knowledge of what a ball is, and without even being told precisely what the controls do. The agent only sees the screen and its score, but it does have access to all of the controls that you'd give a human user. With this limited knowledge, CNNs can extract crucial information that allows them to develop a useful strategy. CNNs have even been trained to play Pictionary. There's currently an app called Quick Draw that guesses what you're drawing based on your finger-drawn picture. The applications of CNNs are almost limitless. Go, for example, is an ancient Chinese board game, considered one of the most complex games in existence. It's said that there are more configurations in the game than there are atoms in the universe. Recently, researchers from Google's DeepMind used CNNs to train an artificially intelligent agent to beat human professional Go players. CNNs also allow drones to navigate unfamiliar territory. Drones are now used to deliver medical supplies to remote areas, and CNNs give the drone the ability to see or to determine what's happening in streaming video data. But for now, we'll consider algorithms that can decode images of text. Maybe you'd like to digitize a historical book or your handwritten notes. Then you could start with developing an algorithm that can identify images of letters or numbers or punctuation. Similarly, you could develop an algorithm to aid self-driving cars with reading road signs. Likewise, Google has built better, more accurate street maps of the world by training an algorithm that can read house number signs from street view images. CNNs achieve state-of-the-art performance in all of these problem domains. We mentioned that while it's possible to use the neural networks from the previous section for image classification, you can almost always, if not always, get better results with the CNN. In the next few videos, we will explore why this is the case.
I'll be teaching this lesson in tandem with Alexis, and as she already mentioned, this lesson is all about convolutional neural networks and how they improve our ability to classify images. In general, CNNs can look at images as a whole and learn to identify spatial patterns, such as prominent colors and shapes, or whether a texture is fuzzy or smooth, and so on. The shapes and colors that define any image and any object in an image are often called features. I'll cover how a CNN can learn to identify these features and how a CNN can be used for image classification. And Alexis will talk about the various layers that make up a complete convolutional neural network. By the end of this lesson, you should have all the skills you need to define and train an image classifier of your own. Let's begin by investigating how deep learning can be used to recognize a single object in an image. In this example, we want to design an image classifier that takes in an image of a handwritten number and produces a predicted class for that number. This class, ideally, correctly identifies the given image. To build this, we'll use the MNIST database, which contains thousands of small grayscale images of handwritten digits. Each image depicts one of the numbers 0 through 9. This database is perhaps one of the most famous databases in the field of machine and deep learning. It was one of the first databases used to prove the usefulness of neural networks and has continued to inform the development of new architectures over time. If you look over this small sample of data, you might notice that some digits are more legible than others. For instance, if you squint just right, this 3 could pass for an 8. And you can imagine that the dataset contains some 4s that could pass for 9s or 1s as 7s. Even with these subtleties, for us, the task of identifying these numbers is pretty easy. And we also want to design an appropriate model such that it too can accurately distinguish between each of these numbers. Using deep learning, we can take a data-driven approach to training an algorithm that can examine these images and discover patterns that distinguish one number from another. Our algorithm will need to attain some level of understanding of what makes a hand-drawn 1 look like a 1, and how images of 1s differ from images of, say, 2s or 3s. The first step in recognizing patterns in images is learning how images are seen by computers. So, before we start to design an algorithm, let's first visualize this data and take a closer look at these images. Any grayscale image is interpreted by a computer as an array, a grid of values where each grid cell is called a pixel, and each pixel has a numerical value. Each image in the MNIST database is 28 pixels high and wide, and so it's understood by a computer as a 28 by 28 array. In a typical grayscale image, white pixels are encoded as the value 255, and black pixels are encoded as 0. Gray pixels fall somewhere in between, with light gray being closer to 255. We'll soon see that color images have similar numerical representations for each pixel color. These MNIST images have actually gone through a quick pre-processing step. They've been rescaled so that each image has pixel values in a range from 0 to 1, as opposed to from 0 to 255. To go from a range of 0 to 255 to 0 to 1, you just have to divide every pixel value by 255. This step is called normalization, and it's common practice in many deep learning techniques. Normalization will help our algorithm to train better. The reason we typically want normalized pixel values is because neural networks rely on gradient calculations. These networks are trying to learn how important or how weighty a certain pixel should be in determining the class of an image, and normalizing the pixel values helps these gradient calculations stay consistent and not get so large that they slow down or prevent a network from training. So now we have our normalized data, how might we approach the task of classifying these images? Well, you already learned one method for classification, using a multi-layer perceptron. How might we input this image data into an MLP? Recall that MLPs only take vectors as input. So in order to use an MLP with images, we have to first convert any image array into a vector. This process is so common that it has a name, flattening. I'll illustrate this flattening conversion process on a small example here. In the case of a 4x4 image, we have a matrix with 16 pixel values. Instead of representing this as a 4x4 matrix, we can construct a vector with 16 entries, where the first 4 entries of our vector correspond to the first row of our old array. The second 4 entries correspond to the second row, and so on. After converting our images into vectors, they can then be fed into the input layer of an MLP. We'll see how this works and see how to produce a class prediction for any given image in the next few videos. After looking at and normalizing our image data, we'll then create a neural network for discovering the patterns in our training data. After training, our network should be able to look at totally new images that it hasn't trained on and classify the digits contained in those images. This previously unseen data is often called test data. At this point, our images have been converted into vectors with 784 entries. So the first input layer in our MLP should have 784 nodes. We also know that we want the output layer to distinguish between 10 different digit types, 0 through 9, and so we'll want the last layer to have 10 nodes. So our model will take in a flattened image and produce 10 output values, one for each possible class 0 through 9. These output values are often called class scores. A high class score indicates that a network is very certain that a given input image falls into a certain class. You can imagine that the class score for a handwritten 3, for example, will have a high score for the class 3 and a low score for the classes 0, 1, and so on. But it may also have a small score for an 8 or any other class that looks kind of similar in shape to a 3. The class scores are often represented as a vector of values or even as a bar graph indicating the relative strengths of the scores. Now, the part of this MLP architecture that's up to you to define is really in between the input and output layers. How many hidden layers do you want to include, and how many nodes should be in each one? This is a question you'll come across a lot as you define neural networks to approach a variety of tasks. I usually start by looking at any papers or related work I can find that may act as a good guide. In this case, I would search for MLP for MNIST, or even more generally, MLP for classifying small grayscale images. Next, I'm going to ask you to perform a search like this and see if you can find a good place to start when it comes to defining the hidden layers of an MLP for image classification. When I type in MLP for MNIST into Google, a few things pop up, including a couple code implementations. This first one from the official Keras GitHub repository looks like a reputable source. Scrolling through this code, I can see that they've imported the MNIST dataset and that they've flattened each input image into a vector of size 784. Here, it looks like they're using one hidden layer to convert that input to be 512 nodes. We can also see an activation function being applied, a ReLU function. And we have one more hidden layer, also with 512 nodes. We can also see some dropout layers in between. This 0.2 means they have a 20% probability of dropout, or of a node being turned off during a training cycle. And as you've learned, dropout layers are used to avoid overfitting data. Lastly, I see one more fully connected layer that's producing an output vector of length 10 for our number of classes. When I look at a source like this, I first try to think about whether it makes sense. I know that the more hidden layers I include in a network, the more complex patterns this network will be able to detect. But I don't want to add unnecessary complexity either. My intuition is telling me that for small images, 2 hidden layers sounds very reasonable. Now, this is just one solution to the task of handwritten digit classification, and the next step in approaching a problem like this is to either 1, keep looking and see if you can find another structure that appeals to you, then 2, when you do find a model or two that look interesting, try them out in code and see how well they perform. This model that I found is good enough for me, so I think I'm going to proceed with defining an MLP with 2 hidden layers based on this structure. Now that we've decided on the structure of our MLP, let's talk a bit about how this entire thing will actually learn from the MNIST data. What happens when it actually sees an input image? Take this input image of a 2, for instance. Say we feed this image into the network, and when we do so, we get these 10 class scores from our output layer. And again, a higher score means that the network is more certain that the input image is of that particular class. 4 is the largest value here, and -2 is the smallest. So the network believes that the image input is least likely to be a handwritten 3, and most likely to be an 8. But this is incorrect. We can see that the correct label is 2. So what we can do is tell our network to learn from this mistake. As a network trains, we measure any mistakes that it makes using a loss function, whose job is to measure the difference between the predicted and true class labels. Then, using backpropagation, we can compute the gradient of the loss with respect to the model's weights. In this way, we quantify how bad a particular weight is and find out which weights in the network are responsible for any errors. Finally, using that calculation, we can choose an optimization function, like gradient descent, to give us a way to calculate a better weight value. Towards this goal, the first thing we'll need to do is make this output layer a bit more interpretable. What's commonly done is to apply a softmax activation function to convert these scores into probabilities. To apply a softmax function to this output layer, we begin by evaluating the exponential function at each of the scores. Then we add up all of the values. Let's denote this sum with a capital S. Then we divide each of these values by the sum. When you plug in all of the math, you get these 10 values. Now each value yields the probability that the image depicts its corresponding image class. For instance, the network believes that the image shows an 8 with 44.1% probability. Remember that the input to the network was an image of a handwritten 2, and yet the network incorrectly predicts that the image shows a 2 with only 16.2% probability. Now, our goal is to update the weights of the network in response to this mistake, so that next time it sees this image, it predicts that 2 is the most likely label. In a perfect world, the network would predict that the image is 100% likely to be the true class. In order to get the model's prediction closer to the ground truth, we'll need to define some measure of exactly how far off the model currently is from perfection. We can use a loss function to find any errors between the true image classes and our predicted classes. Then backpropagation will find out which model parameters are responsible for those errors. Since we're constructing a multi-class classifier, we'll use categorical cross-entropy loss. To calculate the loss in this example, we begin by looking at the model's predicted probability of the true class, which is 16.2%. Cross-entropy loss looks at this probability value, which in decimal form is 0.162, and takes the negative log loss of that value. In this case, we get negative log 0.162, or 1.82. And now, for argument's sake, say instead that the weights of the network were slightly different, and the model instead returned these predicted probabilities. This prediction is much better than the one above, and when we calculate the cross-entropy loss, we get a much smaller value. In general, it's possible to show that the categorical cross-entropy loss is defined in such a way that the loss is lower when the model's prediction agrees more with the true class label, and it's higher when the prediction and the true class label disagree. As a model trains, its goal will be to find the weights that minimize this loss function, and therefore give us the most accurate predictions. So a loss function and backpropagation give us a way to quantify how bad a particular network weight is, based on how close a predicted and a true class label are from one another. Next, we need a way to calculate a better weight value. In the previous lesson, you were encouraged to think of the loss function as a surface that resembles a mountain range. Then to minimize this function, we need only find a way to descend to the lowest valley. This is the role of an optimizer. The standard method for minimizing the loss and optimizing for the best weight values is called gradient descent. You've been introduced to a number of ways to perform gradient descent, and each method has a corresponding optimizer. The surface depicted here is an example of a loss function, and all of the optimizers are racing towards the minimum of the function. As you can see, some do better than others, and you're encouraged to experiment with all of them in your code. You've learned a lot about how to approach the task of image classification. In this notebook, I'll go over how to load in image data, define a model, and train it. You may already be familiar with this process from the earlier lesson on deep learning with PyTorch, but I'd encourage you to stay tuned just so you can see another example in detail. I'll present this code as an exercise. Then you'll get a chance to change this code, define your own model, and try it out on your own in a Jupyter notebook, much like this one. So the first thing I've done in this notebook is to load in the necessary Torch and NumPy libraries. Next, I'm going to import the Torch Vision datasets and transformation libraries. I'll use these to actually load in the MNIST dataset and transform it into a tensor data type. And here, transforms.toTensor is where I define that transformation. The tensor data type is just a data type that's very similar to a NumPy array, only it can be moved onto a GPU for faster calculation, which you'll learn more about later. You'll also see that I've set some parameters for loading in the image data. I can define the batch size, which is the number of training images that will be seen in one training iteration, where one training iteration means one time that a network makes some mistakes and learns from them using backpropagation. The number of workers is if you want to load data in parallel. For most cases, 0 will work fine here. Now I'm going to load in training and test data using datasets.mnist. I'm going to download each set and I'm going to transform it into a tensor data type, which I defined here. I'll put the downloaded data into a directory named data. Finally, I'm going to create training and test loaders. These loaders take in our data that we defined above, our batch size, and number of workers. And the train and test loaders give us a way to iterate through this data one batch at a time. Downloading the data may take a minute or two. After I've downloaded my data, I do the first step in any image analysis task. I visualize the data. Here I'm grabbing one batch of images and their correct labels, and I'm plotting 20 of them. Here you can see a variety of MNIST images and their labels. This step allows me to check and make sure that these images look how I expect them to look. I can even look at an image in more detail. Here I'm just looking at one image in our set, and I'm displaying the grayscale values. You can see that these values are normalized and the brightest pixels are close to a value of 1. The black pixels have a value of 0. Next comes the really interesting part, which is defining the MLP model. We've talked about defining the input, hidden, and output layers, and so I'll leave most of this section for you to fill out. I do want to point out a couple of things here. First, the init function. To define any neural network in PyTorch, you have to define and name any layers that have learned weight values in the init function. So in this case, any fully connected linear layers that you define. And I've defined a sample first input layer, which I've named FC1 for you. This has 784 or 28 by 28 inputs and a number of hidden nodes. This is the number of outputs that this layer will produce. For now, I've left this as 1, and this will have to be changed to create a working solution. Next, you have to define the feed-forward behavior of your network. This is just how an input x will be passed through various layers and transformed. I'm assuming the passed in x will be a grayscale image, like an MNIST image, and I've provided some starting code in here for you. First, I've made sure to flatten the input image x by using the view function. View takes in a number of rows and columns and then squishes an input into that desired shape. In this case, the number of columns will be 28 by 28 or 784. And by putting a -1 here, this function will automatically fit all of the x values into this column shape. The end result is that this x will be a vector of 784 values. Then I'm passing this flattened vector to our first fully connected layer defined up here. I just call this layer by name, pass in our input, and apply a ReLU activation function. A ReLU should be applied generally to the output of every hidden layer so that those outputs are consistent positive values. And finally, I return the transformed x. Now, to complete this model, you should add to the init and forward functions so that the final returned x is a list of class scores. Next, I'm going to describe how you might go about training your defined model and complete this task on your own. After loading in data and defining a model, the next task is to define your loss and optimization functions. For a simple classification problem like this one, I recommend starting with cross-entropy loss and a method of gradient descent, but you may also find it useful to read the documentation on the various types of loss functions and optimizers. In fact, let's check out the loss documentation. You can see a few different types of loss here, and we can read about cross-entropy loss. The documentation says that the cross-entropy function is actually performing a softmax function on an output layer and then doing negative log loss. This means that you only need your model to produce class scores, and then this loss function will turn those into probabilities using a softmax function and calculate the loss. It even details how these calculations are performed. You'll also notice that this loss is calculated as an average value over a batch of images. So if a batch of 20 images is seen by our model during training, the returned loss will be the average loss over those 20 images. Now back to our notebook, the loss and optimization functions will really define how the network updates its weights as it trains. Next, we'll get to the actual training loop. This has the number of epochs we will train for. Epochs are how many times we want the model to iterate through the entire training dataset. One epoch, for example, means it sees every training image just once. And I suggest starting with at least 20 epochs for this dataset. It's good practice to start kind of small if you're testing out different model architectures, and then increase the number of epochs when you're trying to train your final model. Then we loop over each epoch, and I'm going to keep track of the training loss as I go. Inside this epoch loop is the batch loop. Here, the train loader will load a batch of training data, and we can look at the images and the true labels for every image in that batch. At the start of the batch loop, we clear out any gradient calculations that PyTorch has accumulated using optimizer.0grad. Then we call on our model and perform a forward pass. Our model takes in the input images, the data from our train loader, and then this returns the predicted class scores, which I'll call output. Next, we use our defined loss function to compare these predicted outputs and the true labels, the target. These were, again, gotten from our train loader. So we compare a batch of outputs and target labels and calculate the cross-entropy loss. To complete the backpropagation steps, we then perform a backward pass to compute the gradient of the loss, and we perform a single optimization step. This step is actually responsible for updating the values of the weights in our network. Finally, we compute a running training loss. This loss.item is a loss value that's averaged over the batch, and in this case, we actually want to record the accumulated loss over the batch, not the average quite yet. so I'm going to multiply it by the batch size, data.size 0. Then, after this loop has completed and we've gone through one whole epoch, I'll calculate the average loss over that epoch. To do this, I'm going to divide the accumulated loss by the total number of images in our training set. This returns an average training loss, and I'll print it out after each epoch. I should note that this is just one way to calculate the average loss, and as you look at example code, you may see a different calculation. For example, you could calculate the average loss at any point in this batch loop, as long as you add up the loss for every input image and then divide the accumulated loss by the number of images seen by the network. Now, after you run this training loop for some time, after a number of epochs, you'll be able to test your model on previously unseen test data. And I've provided some code that iterates through the test data from our test loader and applies our trained model to that data. This code will allow you to see how well your model performs on each class in our dataset. Next, you'll have a chance to take a look at this exercise code and a solution to creating an MLP for image classification. I encourage you to look at the solution after you've attempted to build a network of your own. I'm going to quickly show you how I went about defining and training an MLP for image classification. So first, I just loaded in and looked at my normalized image data. Then I started to define the classification model. I started with the fully connected layer, FC1, that sees the 784 entry long vector that represents a flattened image as input. Then I proceeded based on the resource that I found, which had 2 hidden layers with 512 inputs and outputs. I've actually stored those values here as 2 variables, hidden 1 and hidden 2. This is an extra step, but it makes it easy should I want to change these values later on for testing or something else. So to complete my first fully connected layer, I put hidden 1 as the number of outputs I want this to produce. Then I create a second fully connected layer, FC2, which takes in that number of outputs and produces 512 outputs again. I also want to be clear that the outputs of one layer feed into the inputs of the next. Then I've defined the last fully connected layer, FC3, such that it sees 512 inputs and produces 10 outputs. The 10 outputs correspond to the number of digit classes 0 through 9. So this layer will produce our class scores. Finally, still in the init function, I've also defined a dropout layer with a dropout probability of 0.2 or 20%. Now that I've defined all the layers that I need to make up this classification MLP, I have to explicitly define the feed-forward behavior of the network. With the forward function, I basically want to answer how will an input vector proceed through these layers. So the input x starts out as a 28 by 28 image tensor, and my first step is to flatten it into a 784 length vector. Once the input is flattened, I'm passing it through the first fully connected layer, FC1, and applying an activation function. Next, I'm going to do the exact same thing with our second fully connected layer, FC2, only in between these 2 layers, I'm actually adding a dropout layer, which should help prevent overfitting. After x passes through our second hidden layer, we're going to add one more dropout layer and reach our final fully connected layer. You'll notice that I'm not applying an activation function to this final layer, and that's because later it will have a softmax activation function applied to it. So right now I'm leaving it as is and returning the final transformed x. Because FC3 produces 10 outputs, this x should represent our 10 class scores. Okay, then I'm instantiating and printing out the net to make sure it has the layers that I want. I should see our 3 linear layers and our dropout. The next step is defining the loss and optimization functions. Here I'm defining the loss criterion as cross-entropy loss, and this is just a pretty standard loss for any classification task. Then I'm going to use stochastic gradient descent, SGD, from the Torch optimization library. This takes in our model parameters and a learning rate. I've set a learning rate of 0.01. If you find that your loss is decreasing too slowly or sporadically, you can change this value. Next, I spent some time training this model for 50 epochs. This took some time because I'm just using my CPU for now, and later I'll show you how to use a GPU for faster training. At the end of each of these epochs, I printed out the training loss and watched how it decreased over time. You can see that it decreased fairly quickly at first, and then later on sort of slows down, especially around the 40 epoch mark. But it is still decreasing up to epoch 50. Then, to actually see how well my trained model generalizes to new data, I test it on our test data that we loaded in at the start. Here I've iterated through all the data in our test loader. I applied the model and recorded the test loss. Recall that our model is actually returning a list of class scores. And to isolate our predicted class, I'm going to take the maximum value of these scores and return it as our prediction. Then I compare this prediction to our target label. This creates a list whether a certain prediction was correct or not. Then I actually separate these into the 10 classes and I print out the accuracy for each class. I have our overall test loss and our overall accuracy, which is 97%. This is pretty good, and you can see among all the digit classes, this value is pretty consistent. The model seems to do the worst on images of the number 7 or 8, but an even distribution indicates that your model was trained pretty evenly on each type of data. I've also included a cell where you can display test images and their predicted and true labels side by side. This makes it easy to see if you've gotten any specific image wrong. But going back up to the test accuracy overall, I actually wonder if I could do even better. If I could improve this model by adding, say, another layer to find more patterns in the data. I even wonder if I chose the right point to stop training this model. In fact, one thing to note is that I stopped training at 50 epochs based on only how I expected the loss to decrease over time. But it's more of an art than a science at this point. So next, I'll talk about one more concrete method of knowing when to stop training, a technique called model validation. So far, we've checked how well our models are performing based on how the loss changes over each epoch. But the exact number of epochs to train for is often hard to determine. How many epochs should you train for so that your network is accurate but it's not overfitting the training data? One method that's used in practice involves breaking the dataset into 3 sets, called training, validation, and test sets. Each is treated separately by the model. The model looks only at the training set when it's actively training and deciding how to modify its weights. After every training epoch, we check how the model is doing by looking at the training loss and the loss on the validation set. But it's important to note that the model does not use any part of the validation set for the backpropagation step. We use the training set to find all the patterns we can and to update and determine the weights of our model. The validation set only tells us if that model is doing well on the validation set. And in this way, gives us an idea of how well the model generalizes to a set of data that is separate from the training set. The idea is, since the model doesn't use the validation set for deciding its weights, that it can tell us if we're overfitting the training set of data. Finally, the test set of data is saved for checking the accuracy of a model after it's trained. This may be easiest to see in an example. Say you set the model to train for 200 epochs, and around epoch 100 you notice that the training loss starts decreasing, but the validation loss is actually starting to increase. This actually indicates that the model is overfitting the training data because it's not generalizing well enough to also perform well on the validation set. So if you see this kind of divide in how the training and validation losses decrease, you'll want to stop changing the weights of your network around epoch 100, and ignore or throw away the weights from later epochs where there's evidence of overfitting. This kind of process can also prove useful if we have multiple potential architectures to choose from. For example, if you're deciding on the number of layers to put in the model, then you'll want to save the weights from each potential architecture for later comparison, and can choose to pick the model that gets the lowest validation loss. You might be wondering, why must we create a third dataset? Couldn't we just use the test set for this purpose? Well, the idea is that when we go to test the model, it looks at data that it has truly never seen before. Even though the model doesn't use the validation set to update its weights, our model selection process is based on how the model performs on both the training and validation sets. And so, in the end, the model is biased in favor of the validation set. Thus, we need a separate test set of data to truly see how our selected model generalizes and performs when given data it really has not seen before. In the next video, I'll show you how to use these ideas to fine-tune your network architecture. So in our last example, I got pretty good classification accuracy just by looking at how, during training, the cross-entropy loss that measured the difference between predicted and true classes got smaller and smaller. I sort of estimated when a good time to stop training would be, when the training loss had kind of plateaued its decreasing. But as you've just learned, there's a way to use a validation dataset to programmatically know when to stop training, and so I'm going to show you how to add that in code. So the first thing I'm going to do is to create a validation dataset, much like we created training and test sets. In fact, I'm actually going to take a percentage of data from the training set. I'll set a variable, valid size, to take 20% of the training set data and turn it into validation data. This should be a good enough size since the MNIST dataset is very large. Then I'm going to use something called subset random sampler to help me do the work of splitting the training data. First, I'll record how many training images there are, and I'll determine which indices in the training set I'll access to create both sets training and validation. I'll list out all the possible indices by grabbing the length of the entire training set. So these indices are going to be the values that point to each of the 70,000 images in the training set. Then I'm going to shuffle these indices so that any index I select out of this list will reference a random piece of data. Then I'm defining a split boundary, and this is just going to be the number of examples that I want to include in the validation set. So it's going to be 20% of our training data. Then I'll use this to get an 80-20 split between training and validation data. Finally, I'm using subset random sampler to create data samplers for this training and validation data. This adds one more argument to our train loader and validation loaders. So previously I had only training and test data loaders, and now I've split the training data into two sets by essentially shuffling it and selecting 20% for a validation set using a specific data sampler. So now we officially have a validation set loader, and I'm going to scroll down to my training loop to actually use this validation set. Okay, here's our training loop, and this time, in addition to keeping track of the training loss, I'm also going to track the validation loss. I'll actually want to stop training whenever I reach an epoch for which the training loss decreases, but the validation loss does not. So I'm going to track the change in the validation loss, and specifically I'll track the minimum validation loss over time so that I can compare it to the current validation loss and see if it's increased or decreased from the minimum over a given epoch. So within our epoch loop, we have our usual training batch loop, and we also have a validation batch loop. This is looping through all the data and labels in the validation set. It's applying our model to that data and recording the loss as usual. Notice we are not performing the back propagation step here. That is reserved only for our training data. Then I've added a little bit to my print statement, and I'm printing out the average validation loss after each epoch as well. Also at the end of each epoch, I'm going to check the validation loss and see if it's less than the currently recorded minimum. If it is, I'm going to save the model because that means the validation loss has decreased, and I'll store that as the new minimum value. You may have noticed that I set the initial minimum to infinity. This high value guarantees that this loss will update after the first epoch. Also take note of this line, which allows me to save the model and its current parameters by name, model.pt. Okay, then I've run this for 50 epochs, and I can see both the training loss and the validation loss after each epoch. We can see that both the training and validation loss are decreasing for the first 30 or so epochs. And so the model is being saved after each of these points where the validation loss decreases. We can also see this decrease sort of slowing down right around here. In fact, our last model was saved after epoch number 37. By saving the model at the point where the validation and training loss diverge, I'm preventing my model from overfitting the training data. This is also an issue of efficiency. We should see that our validation loss sort of stays the same for the last 10-15 epochs here. And so the lack of decrease here is actually indicating to me that the best model is really reached even around epoch 30, but definitely by epoch 37. So next step is to see how this model performs on our test data. Here I'm actually loading the model that we saved earlier by name into our instantiated model. And I'm testing it as usual, passing our test data into our model and recording the class accuracies. You can see we get 97% overall accuracy. This is really about the same as our last model, the one without validation. So even though we trained that model for 15 more epochs, the results are about the same. This makes sense because this validation loss really isn't changing much, so whether we save the model after epoch 37 or 50, the model should be pretty similar. This kind of behavior is also occurring because most of these images are very similar. The images are very pre-processed and all of the digits look kind of the same. So in our non-validation case, it didn't matter so much that our model trained for much longer. But in some cases, you will get overfitting, and choosing a model based on validation loss will be even more important. So, model validation can be a really helpful way to select the best model and decide when to stop training. So far, you've learned a lot about approaching the task of image classification. In fact, now is a good time to review the pipeline we've developed for such a task. First, load and visualize the data you're working with. Then, pre-process that data by normalizing it and converting it into a tensor so that it's prepped for further processing by the layers of a neural network. Then, do your research. Has anyone approached this or a similar task before? What kind of deep learning models have already been tried and tested? Use this research to help you decide on a model architecture and define it. Then decide on loss and optimization functions and proceed with training your model. Here, you may choose to use a validation dataset to select and save the best model during training. Finally, test your model on previously unseen data. At this point, feel free to take a break from working and learning. Take time to absorb what you've learned so far. Then when you're ready, you can keep going. Next, I'll go over a new kind of architecture for image classification, a convolutional neural network, which can help us build even better image classification models. So far, we've investigated how to train an MLP to classify handwritten digits in the MNIST dataset, and we got a really high test accuracy. MLPs are a nice solution in this case. Some other solutions for the MNIST classification task and their errors on the test dataset can be explored at the link provided below. You'll find that the best algorithms, or the ones with the least test error, are the approaches that use convolutional neural networks, or CNNs. In fact, for most image classification tasks, CNNs and MLPs do not even compare. CNNs do much better. The MNIST database is an exception in that it's very clean and preprocessed. All images of digits are roughly the same size and are centered in a 28 by 28 pixel grid. You can imagine that if, instead of having to classify the digit within these very clean images, you had to work with images where the digit could appear anywhere within the grid, and sometimes appear quite small or quite large. It would be a more challenging task for an MLP. In the case of real-world, messy image data, CNNs will truly shine over MLPs. For some intuition for why this might be the case, we saw that in order to feed an image to an MLP, you must first convert the image to a vector. The MLP then treats this converted image as a simple vector of numbers with no special structure. It has no knowledge of the fact that these numbers were originally spatially arranged in a grid. CNNs, in contrast, are built for the exact purpose of working with or elucidating the patterns in multidimensional data. Unlike MLPs, CNNs understand the fact that image pixels that are closer in proximity to each other are more heavily related than pixels that are far apart. In this section, Alexis and I will discuss the math behind this kind of understanding. We'll present different types of layers that make up a CNN and provide some intuition about each of their roles in processing an input and forming a complete neural network.
In the previous video, we used MLPs to decode images of handwritten numerical digits. Before feeding a grayscale image to an MLP, we had to first convert its matrix to a vector. This vector was then fed as input to an MLP with 2 hidden layers. We saw that it was a perfectly valid model for classifying images in the MNIST dataset. In fact, we got less than 2% error on our held-out test images. But for other image classification problems, where we might need to analyze more sophisticated, real-world images with more complicated patterns, we'll need a different technique. In this video, towards motivating and defining CNNs, we specify a few improvements that eliminate some of the drawbacks and limitations that we encounter when performing image classification with MLPs. Specifically, we'll address 2 important issues. First, we've seen that MLPs use a lot of parameters. The MLP from the previous video for our very small 28 by 28 images already contained over 500,000 parameters. You can imagine that the computational complexity for even moderately sized images could get out of control pretty fast. Another issue is that we throw away all of the 2D information contained in an image when we flatten its matrix to a vector. This spatial information, or knowledge of where the pixels are located in reference to each other, is relevant to understanding the image and could aid significantly towards elucidating the patterns contained in the pixel values. This suggests that we need an entirely new way of processing image input where the 2D information is not entirely lost. CNNs will address these problems by using layers that are more sparsely connected, where the connections between layers are informed by the 2D structure of the image matrix. Furthermore, CNNs will accept our matrix as input. For illustration, consider a toy example with 4x4 images of handwritten digits. Our goal remains the same. We'd like to classify the digit that's depicted in the image. After converting the 4x4 matrix to a 16-dimensional vector, we can supply the vector as input to an MLP. We construct an MLP with a single hidden layer with 4 nodes. The output layer has 10 nodes. As in the MLP in the previous video, the output has a softmax activation function and returns a 10-dimensional vector containing the probability that the image depicts each of the possible digits 0 through 9. If we've trained our model well, the vector will predict that a 7 is depicted in the image with high probability. But let's clean up this figure by replacing this detailed depiction with a suggestive output layer. Here, the box annotated with "it's a 7" is just shorthand notation for an output layer which predicts a 7. Just looking at this MLP, it becomes apparent that there may be some redundancy. Does every hidden node need to be connected to every pixel in the original image? Perhaps not. Consider breaking the image into 4 regions, here color-coded as red, green, yellow, and blue. Then each hidden node could be connected to only the pixels in one of these 4 regions. Here, each hidden node sees only a quarter of the original image. In the case of the previous fully connected layer, every hidden node was responsible for gaining an understanding of the entire image all at once. With this new regional breakdown and assignment of small local groups of pixels to different hidden nodes, every hidden node finds patterns in only one of the 4 regions in the image. Then each hidden node still reports to the output layer, where the output layer combines the findings for the discovered patterns learned separately in each region. This so-called locally connected layer uses far fewer parameters than a densely connected layer. It's less prone to overfitting and truly understands how to tease out the patterns contained in image data. We can rearrange each of these vectors as a matrix, where now the relationships between the nodes in each layer are more obvious. We could expand the number of patterns that we're able to detect, while still making use of the 2D structure to selectively and conservatively add weights to the model by introducing more hidden nodes, where each is still confined to analyzing a single small region within the image. The red nodes in the hidden layer are still only connected to the red nodes in the input layer, with the same color coding for all other colors. After all, we saw in the previous videos on neural networks that by expanding the number of nodes in the hidden layer, we can discover more complex patterns in our data. We now have 2 collections of hidden nodes, where each collection contains nodes responsible for examining a different region of the image. It will prove useful to have each of the hidden nodes within a collection share a common group of weights. The idea being that different regions within the image can share the same kind of information. In other words, every pattern that's relevant towards understanding the image could appear anywhere within the image. Perhaps the simplest way to see how this parameter sharing will help our neural network classify objects is through a higher resolution image example. Say you have an image and you want your network to say it's an image containing a cat. It doesn't matter where the cat is, it's still an image with a cat. If your network has to learn about kittens in the left corner and kittens in the right corner independently, that's a lot of work that it has to do. Instead, we tell the network explicitly that objects and images are largely the same, whether they're on the left or the right of the picture, and this is partially accomplished through weight sharing. All of these ideas will motivate so-called convolutional layers, which we present in the next video.
A convolutional neural network is a special kind of neural network in that it can remember spatial information. The neural networks that you've seen so far only look at individual inputs, but convolutional neural networks can look at an image as a whole, or in patches, and analyze groups of pixels at a time. The key to preserving this spatial information is something called the convolutional layer. A convolutional layer applies a series of different image filters, also known as convolutional kernels, to an input image. The resulting filtered images have different appearances. The filters may have extracted features like the edges of objects in that image, or the colors that distinguish the different classes of images. In the case of classifying digits, for example, a CNN should learn to identify spatial patterns like the curves and lines that make up the number 6, as distinct from another digit. Later layers in a model will learn how to combine different color and spatial features to produce an output like a class label. Before we get into defining and training a complete CNN, in the next couple videos, you'll learn a bit more about the filters that define a convolutional layer, how they're defined, and how they can transform an input image. This will be important foundational knowledge that will come up again as you get to training a CNN and even visualizing the inner workings of a trained CNN. When we talk about spatial patterns in an image, we're often talking about one of two things, color or shape, and I want to focus on shape for a moment. Shape can also be thought of as patterns of intensity in an image. Intensity is a measure of light and dark similar to brightness, and we can often use this knowledge to detect the shape of objects in an image. For example, say you're trying to distinguish a person from a background in an image. You can look at the contrast that occurs where the person ends and the background begins to define a shape boundary that separates the two. You can often identify the edges of an object by looking at abrupt changes in intensity, which happen when an image changes from a very dark to light area. In the next few videos, you'll be using and creating specific image filters that look at groups of pixels and detect big changes in intensity in an image. These filters produce an output that shows various edges and shapes. So let's take a closer look at these filters and see what role they play in a convolutional neural network. In image processing, filters are used to filter out unwanted or irrelevant information in an image, or to amplify features like object boundaries or other distinguishing traits. High-pass filters are used to make an image appear sharper and enhance high-frequency parts of an image, which are areas where the levels of intensity in neighboring pixels rapidly change, like from very dark to very light pixels. And since we're looking at patterns of intensity, the filters we'll be working with will be operating on grayscale images that represent this information and display patterns of lightness and darkness in a simple format. Let's take a closer look at this panda image as an example. What do you think will happen if we apply a high-pass filter? Well, where there's no change or little change in intensity in the original picture, such as in these large areas of dark and light, a high-pass filter will block these areas out and turn the pixels black. But in these areas where a pixel is way brighter than its immediate neighbors, the high-pass filter will enhance this change and create a line. You can see that this has the effect of emphasizing edges. Edges are just areas in an image where the intensity changes very quickly, and these edges often indicate object boundaries. Now let's see how exactly a filter like this works. The filters I'll be talking about are in the form of matrices, often called convolution kernels, which are just grids of numbers that modify an image. Here's an example of a high-pass filter that does edge detection. It's a 3x3 kernel whose elements all sum to 0. It's important that, for edge detection, all of the elements sum to 0, because this filter is computing the difference or change between neighboring pixels. Differences are calculated by subtracting pixel values from one another, in this case subtracting the value of the pixels that surround a center pixel. And if these kernel values did not add up to 0, that would mean that this calculated difference will be either positively or negatively weighted, which will have the effect of brightening or darkening the entire filtered image, respectively. To apply this filter, an input image, f of xy, is convolved with this kernel, which I'll call k. This is called kernel convolution, and convolution is represented by an asterisk, not to be mistaken for multiplication. Kernel convolution is an important operation in computer vision applications, and it's the basis for convolutional neural networks. It involves taking a kernel, which is our small grid of numbers, and passing it over an image, pixel by pixel, transforming it based on what these numbers are. And we'll see that by changing these numbers, we can create many different effects from edge detection to blurring an image. I'll walk through an example using this 3x3 edge detection filter. To better see the pixel operations, I'll zoom in on this panda right by its ear to see the grayscale pixel values. First, for every pixel in this grayscale image, we put our kernel over it so that the pixel is in the center of the kernel. And I'm just choosing this pixel as an example. Then we look at the 3x3 grid of pixels centered around that one pixel. We then take the numbers in our kernel and multiply them with their corresponding pixel in pairs. So this pixel in the top left corner, 120, is multiplied by the kernel corner, 0. And next to that, we multiply the value 140 by -1, and then next another 120 by 0. And we do that for all 9 pixel kernel value pairs. Notice that the center pixel, with a value of 220, will be multiplied by 4, the center kernel value. Finally, these values are all summed up to get a new pixel value, 60. This value means a very small edge has been detected, which we can see by looking at this 3x3 area in the image. It changes from light at the bottom to a little darker on top, but it changes very gradually. These multipliers in our kernel are often called weights because they determine how important or how weighty a pixel is in forming a new output image. In this case, for edge detection, the center pixel is the most important, followed by its closest pixels on the top and bottom and to its left and right, which are negative weights that increase the contrast in the image. The corners are the farthest away from the center pixel, and in this example, we don't give them any weight. So this weighted sum becomes the value for the corresponding pixel at this same location, xy, in the output image. And you do this for every pixel position in the original image until you have a complete output image that's about the same size as the input image with new filtered pixel values. The only thing you need to consider other than this weighted sum is what to do at the edges and corners of your image, since the kernel cannot be nicely laid over 3x3 pixel values everywhere. Next, let's get a little more practice with these kinds of high-pass filters, then get into coding our own.
Consider this image of a dog. A single region in this image may have many different patterns that we want to detect. Consider this region, for instance. This region has teeth, some whiskers, and a tongue. In that case, to understand this image, we need filters for detecting all 3 of these characteristics, one for each of teeth, whiskers, and tongue. Recall the case of a single convolutional filter. Adding another filter is probably exactly what you'd expect, where we just populate an additional collection of nodes in the convolutional layer. This collection has its own shared set of weights that differ from the weights for the blue nodes above them. In fact, it's common to have tens to hundreds of these collections in a convolutional layer, each corresponding to their own filter. Let's now execute some code to see what these collections look like. After all, each is formatted in the same way as an image, namely as a matrix of values. We'll be visualizing the output of a Jupyter notebook. If you like, you can follow along with the link below. So, say we're working with an image of UDACITY's self-driving car as input. Let's use 4 filters, each 4 pixels high and 4 pixels wide. Recall, each filter will be convolved across the height and width of the image to produce an entire collection of nodes in the convolutional layer. In this case, since we have 4 filters, we'll have 4 collections of nodes. In practice, we'll refer to each of these 4 collections as either feature maps or as activation maps. When we visualize these feature maps, we see that they look like filtered images. That is, we've taken all of the complicated, dense information in the original image, and in each of these 4 cases, outputted a much simpler image with less information. By peeking at the structure of the filters, you can see that the first 2 filters discover vertical edges, where the last 2 detect horizontal edges in the image. Remember that lighter values in a feature map mean that the pattern in the filter was detected in the image. So, can you match the lighter regions in each feature map with their corresponding areas in the original image? In this activation map, for instance, we can see a clear white line defining the right edge of the car. This is because all of the corresponding regions in the car image closely resemble the filter, where we have a vertical line of dark pixels to the left of a vertical line of lighter pixels. If you think about it, you'll notice that edges in images appear as a line of lighter pixels next to a line of darker pixels. This image, for instance, contains many regions that would be discovered or detected by one of the 4 filters we defined before. Filters that function as edge detectors are very important in CNNs, and we'll revisit them later. So now we know how to understand convolutional layers that have a grayscale image as input. But what about color images? Well, we've seen that grayscale images are interpreted by the computer as a 2D array with height and width. Color images are interpreted by the computer as a 3D array with height, width, and depth. In the case of RGB images, the depth is 3. This 3D array is best conceptualized as a stack of 3 two-dimensional matrices, where we have matrices corresponding to the red, green, and blue channels of the image. So how do we perform a convolution on a color image? As was the case with grayscale images, we still move a filter horizontally and vertically across the image, only now the filter is itself three-dimensional to have a value for each color channel at each horizontal and vertical location in the image array. Just as we think of the color image as a stack of 3 two-dimensional matrices, you can also think of the filter as a stack of 3 two-dimensional matrices. Both the color image and the filter have red, green, and blue channels. Now, to obtain the values of the nodes in the feature map corresponding to this filter, we do pretty much the same thing we did before, only now our sum is over 3 times as many terms. We emphasize that here we've depicted the calculation of the value of a single node in a convolutional layer for one filter on a color image. If we wanted to picture the case of a color image with multiple filters, instead of having a single 3D array, which corresponds to one filter, we would define multiple 3D arrays, each defining a filter. Here we've depicted 3 filters. Each is a 3D array that you can think of as a stack of 3 2D arrays. Here's where it starts to get really cool. You can think about each of the feature maps in a convolutional layer along the same lines as an image channel and stack them to get a 3D array. Then we can use this 3D array as input to still another convolutional layer to discover patterns within the patterns that we discovered in the first convolutional layer. We can then do this again to discover patterns within patterns within patterns. Remember that in some sense, convolutional layers aren't too different from the dense layers that you saw in the previous section. Dense layers are fully connected, meaning that the nodes are connected to every node in the previous layer. Convolutional layers are locally connected, where their nodes are connected to only a small subset of the previous layer's nodes. Convolutional layers also had this added parameter sharing. But in both cases, with convolutional and dense layers, inference works the same way. Both have weights and biases that are initially randomly generated. So in the case of CNNs, where the weights take the form of convolutional filters, those filters are randomly generated, and so are the patterns that they're initially designed to detect. As with MLPs, when we construct a CNN, we will always specify a loss function. In the case of multi-class classification, this will be categorical cross-entropy loss. Then, as we train the model through backpropagation, the filters are updated at each epoch to take on values that minimize the loss function. In other words, the CNN determines what kind of patterns it needs to detect based on the loss function. We'll visualize these patterns later and see that, for instance, if our dataset contains dogs, the CNN is able to, on its own, learn filters that look like dogs. So, with CNNs, to emphasize, we won't specify the values of the filters or tell the CNN what kind of patterns it needs to detect. These will be learned from the data. We've seen that you can control the behavior of a convolutional layer by specifying the number of filters and the size of each filter. For instance, to increase the number of nodes in a convolutional layer, you could increase the number of filters. To increase the size of the detected patterns, you could increase the size of your filter. But there are even more hyperparameters that you can tune. One of these hyperparameters is referred to as the stride of the convolution. The stride is just the amount by which the filter slides over the image. In the example in the previous video, the stride was 1, and we moved the convolution window horizontally and vertically across the image 1 pixel at a time. A stride of 1 makes the convolutional layer roughly the same width and height as the input image. In this animation, we've drawn the purple convolutional layer as stacked feature maps. If we instead make the stride equal to 2, the convolutional layer is about half the width and height of the image. I say roughly because it depends on what you do at the edge of your image. To see how the treatment of the edges will matter, consider our toy example of a 5x5 grayscale image. Say we have a different filter now with a height and width of 2. Say the stride is also 2. Then, as before, we start with the filter in the top left corner of the image and calculate the value for the first node in the convolutional layer. We then move the filter 2 units to the right and do the same. But when we move the filter 2 more units to the right, the filter extends outside the image. What do we do now? Do we still want to keep the corresponding convolutional node? For now, let's just populate the places where the filter extends outside with a question mark and proceed as planned. So now, how do we deal with these nodes where the filter extended outside the image? We could, as a first option, just get rid of them. Note that if we choose this option, it's possible that our convolutional layer has no information about some regions of the image. This is the case here for the right and bottom edges of the image. As a second option, we could plan ahead for this case by padding the image with zeros to give the filter more space to move. Now, when we populate the convolutional layer, we get contributions from every region in the image. We're now ready to introduce you to the second and final type of layer that we'll need to introduce before building our own convolutional neural networks. These so-called pooling layers often take convolutional layers as input. Recall that a convolutional layer is a stack of feature maps where we have one feature map for each filter. A complicated dataset with many different object categories will require a large number of filters, each responsible for finding a pattern in the image. More filters means a bigger stack, which means that the dimensionality of our convolutional layers can get quite large. Higher dimensionality means we'll need to use more parameters, which can lead to overfitting. Thus, we need a method for reducing this dimensionality. This is the role of pooling layers within a convolutional neural network. We'll focus on 2 different types of pooling layers. The first type is a max pooling layer. Max pooling layers will take a stack of feature maps as input. Here, we've enlarged and visualized all 3 of the feature maps. As with convolutional layers, we'll define a window size and stride. In this case, we'll use a window size of 2 and a stride of 2. To construct the max pooling layer, we'll work with each feature map separately. Let's begin with the first feature map. We start with our window in the top left corner of the image. The value of the corresponding node in the max pooling layer is calculated by just taking the maximum of the pixels contained in the window. In this case, we had a 1, 9, 5, and 4 in our window, so 9 was the maximum. If we continue this process and do it for all of our feature maps, the output is a stack with the same number of feature maps, but each feature map has been reduced in width and height. In this case, the width and height are half of that of the previous convolutional layer.
In this lesson, we've investigated 2 new types of layers for neural networks. We began with convolutional layers, which detect regional patterns in an image using a series of image filters. We've seen how, typically, a ReLU activation function is applied to the output of these filters to standardize their output values. Then you learned about max pooling layers, which appear after convolutional layers to reduce the dimensionality of our input arrays. These new layers, along with fully connected layers that should be familiar, are often the only layers that you'll find in a CNN. In this video, we'll discuss how to arrange these layers to design a complete CNN architecture. We'll focus again on CNNs for image classification. In this case, our CNN must accept an image array as input. Now, if we're going to work with messy real-world images, there's a complication that we haven't yet discussed. If I go online and collect thousands or millions of images, well, it's pretty much guaranteed that they'll all be different sizes. Similar to MLPs, the CNNs we'll discuss will require a fixed size input. So we'll have to pick an image size and resize all of our images to that same size before doing anything else. This is considered to be another pre-processing step alongside normalization and conversion to a tensor data type. It's very common to resize each image to be a square, with the spatial dimensions equal to a power of 2, or else a number that's divisible by a large power of 2. In the next few videos, we'll work with a dataset composed of images that have all been resized to 32 by 32 pixels. Recall that any image is interpreted by the computer as a three-dimensional array. Color images had some height and width in pixels, along with red, green, and blue color channels, corresponding to a depth of 3. Grayscale images, while technically two-dimensional, can also be thought of as having their own width and height and a depth of 1. For both of these cases, with color or grayscale images, the input array will always be much taller and wider than it is deep. Our CNN architecture will be designed with the goal of taking that array and gradually making it much deeper than it is taller wide. Convolutional layers will be used to make the array deeper as it passes through the network, and max pooling layers will be used to decrease the XY dimensions. As the network gets deeper, it's actually extracting more and more complex patterns and features that help identify the content and the objects in an image. And it's actually discarding some spatial information about features like a smooth background and so on that do not help identify the image. To see how this works, next let's go over a complete image classification CNN in detail. Say we want to classify an input image. There are a few ways we could go about this using a deep learning architecture. Consider following the input layer with a sequence of convolutional layers. This stack will discover hierarchies of spatial patterns in the image. The first layer of filters looks at patterns in the input image, the second looks at patterns in the previous convolutional layer, and so on. Each of the convolutional layers requires us to specify a number of hyperparameters. The first and second inputs to define a convolutional layer are simply the depth of the input and the desired depth of the output. For example, the input depth of a color image will be 3 for the RGB channels, and we might want to produce 16 different filtered images in this convolutional layer. Next, we define the size of the filters that define a convolutional layer. These are often square and range from a size of 2 by 2 at the smallest to up to 7 by 7 or so for very large images. Here, I'll choose to use 3 by 3 filters. The stride is generally set to 1, and many frameworks will have this as the default value, so you may not need to input this value. As for padding, you may get better results if you set your padding such that a convolutional layer will have the same width and height as its input from the previous layer. In the case of a 3 by 3 filter, which can almost center itself perfectly on an image, but misses the border pixels by 1, this padding will be equal to 1. And you can read a bit more about different cases for padding below. When deciding the depth or number of filters in a convolutional layer, often we'll have the number of filters increase in sequence. So the first convolutional layer might have 16 filters. The second will see that depth as input and produce a layer with a depth of 32. The third will have a depth of 64, and so on. After each convolutional layer, we'll apply a ReLU activation function. If we follow this process, we have a method for gradually increasing the depth of our array without modifying the height and width. The input, just like all of the layers in this sequence, has a height and width of 32. But the depth increases from an input layer's depth of 3 to 16 to 32 to 64. Recall that, yes, we wanted to increase the depth, but we also wanted to decrease the height and width and discard some spatial information. This is where max pooling layers will come in. They generally follow every 1 or 2 convolutional layers in the sequence. Here's one such example with a max pooling layer after each convolutional layer. To define a max pooling layer, you only need to define the filter size and stride. The most common setting will use filters of size 2 with a stride of 2. This has the effect of making the XY dimensions half of what they were from the previous layer. In this way, the combination of convolutional and max pooling layers accomplishes our goal of attaining an array that's quite deep, but small in the x and y dimensions. Next, let's talk about finally connecting this output to a fully connected layer and see what exactly is happening to an input as it moves through these layers. The job of a convolutional neural network is to discover patterns contained in an image. A sequence of layers is responsible for this discovery. The layers in a CNN convert an input image array into a representation that encodes only the content of the image. This is often called a feature-level representation of an image, or a feature vector. It may be helpful to think about it like this. Take two input images that are both images of a car. Both are very different, and if I was to frame these pictures, the detail would be what makes them stylistically interesting. But for an image classifier, it only wants to know that these are both images of cars. And when you look at how these images are transformed as they move through several layers of a CNN, the exact original pixel values matter less and less. The two transformed outputs should start to look much more similar to one another, moving closer towards the idea that both are a car, rather than the details about what the cars look like. Later layers in a CNN have discarded information about style and texture, and instead are pushed towards answering questions about general shape and about the presence of unique patterns, like are there wheels in the image? Are there eyes in the image? What about furry legs or tails? Once we get to a representation where the content of an image has been distilled like this, we can flatten the array into a feature vector and feed it to one or more fully connected layers to determine what object is contained in the image. For instance, if wheels were found after the last max pooling layer, the feature vector will be able to reflect that, and the fully connected layer will transform that information to predict that a car is present in the image with higher probability. If there were eyes, furry legs, and a tail, then the output layer would take that information and deduce that a dog is likely present in the image. But of course, to emphasize, all of this understanding in the model is not pre-specified by us. It is learned by the model during training and through backpropagation that updates the weights that define the filters and the weights in the fully connected layers. This architecture that we're specifying here just gives the model a structure that will allow it to train better, so it has the potential to classify objects with greater accuracy. Next, I'll show you how to start defining a CNN architecture for image classification, and you'll get to practice coding on your own. CIFAR-10 is a popular dataset of 60,000 tiny images, each depicting an object from one of 10 classes. You can see that each image is truly tiny, only 32 pixels high and wide. These are color images, so they're interpreted by the computer as arrays with a depth of 3 for RGB color channels. Because these are color images, and there are a lot of them, the first thing I'm going to show you is an option to use a GPU for training. A GPU is essentially something that allows you to do data processing in parallel, and so it may prove useful to speed up your training time. Here you can see I'm loading in my usual libraries, and then PyTorch gives us a way to check if a GPU device is available. Torch.CUDA is available will return a Boolean variable, true or false, whether or not a GPU is available. We'll store this, and then later, if we do have a GPU available, we'll be able to move our data and our model to that device for faster training. For now, I'm just going to visualize some data and present this problem, and so I'm using my laptop. And when I run this cell, you can see that I'm training on CPU. Later, when I do try to develop a solution and train a model, I'll switch to GPU. And in general, this is a good thing to know how to use. Next, I'm going to load in my data as usual. CIFAR, much like MNIST, is available in the Torch Vision datasets library. I'm going to define my training and my test data by calling datasets.cifar10. I'll also transform this data into a tensor data type and normalize the RGB values so that the pixel values are in a range from about 0 to 1. Finally, I can load in my transformed data in batches using PyTorch's data loader class. These lines of code should look very similar to the MNIST code, in which we loaded in data, transformed it into a tensor data type, and separated the data into training, validation, and test sets. Also, down here, I'm specifying the 10 image classes that I'm reading in. All CIFAR-10 images will fall into one of these categories. The data may take a moment to load in, but once you load it in, you can visualize a batch of that data. Here, I've defined a helper function, which will basically unnormalize the images and convert them from a tensor image type to a NumPy image type for visualization. Then I'm just going to load in and display a batch of images. And here we can verify that these images look pretty much how we would expect. We have images of cats, frogs, deer, and automobiles. We can even choose to view an image in more detail. Here I'm displaying the red, green, and blue color channels as grayscale values for one single image. And we should again see that the brightest pixel values are close to the value 1, and darker ones closer to 0. Next, you'll want to define and train a CNN to classify these images. You're also welcome to try out an MLP approach, see how both work, and compare the results. I'll be assuming that you want to define a CNN architecture, so I've provided links to the documentation for convolutional and max pooling layers in PyTorch. Here's also a simple diagram showing how an input image might pass through a couple of these layers. Then, if you scroll down, you can see that I've defined one example convolutional layer for you. I've defined it in the init function of our network. To define a convolutional layer, I use nn.conv2d and I pass in some parameters. For our first convolutional layer, this will be the number of inputs seen as the depth of the input image. Recall that our inputs are 32 by 32 images with a depth of 3 for RGB color channels. So I've defined that input and I've specified that this should output a convolutional layer with a depth of 16. That means this layer should take in our image and produce 16 filtered images as output. I've also specified that I'm using filters that are 3 by 3 in size. And to keep my output layer the same XY size as my input image, I'll add 1 pixel of padding on the border. I've also defined one max pooling layer named Pool. This has a kernel size and stride size of 2, which means that any input it's applied to, it will downsample its XY dimensions by a factor of 2. Then in the forward function, we can see how all of these things fit together. For an input image X, I first pass it into our first convolutional layer, and I apply a ReLU activation function. This output will be passed to a final pooling layer, resulting in a downsampled transformed X, which I'll return. To complete this model, it will be up to you to add multiple convolutional and pooling layers, and finally flatten and apply a fully connected layer for producing the desired number of class score outputs. After defining a complete CNN, you can instantiate it and even move it to GPU if it's available. Next, it'll be up to you to specify an appropriate loss and optimization function for this training task. And finally, I've provided a training loop for you. You may want to increase the number of epochs you train your final model for, but this loop will keep track of the training and validation loss as you go. If your validation loss decreases over an epoch, your model will be saved. Then you'll be able to test your trained network and see how it performs on each type of test image. The biggest challenge will be defining a complete CNN, and as always, I encourage you to do your research before you define your model, so that you can make an informed decision as you go. Try to solve this challenge on your own, and if you want to check your work, next, I'll go over one possible solution. Okay, now that you've tried to define and train a classifier of your own, I'll show you a solution that I created. After loading in my data and processing it, I defined a complete CNN. I've kept my initial convolutional layer, conv1, that sees our input image and outputs a stack of 16 feature maps. And I'm defining all my convolutional layers first, defining 2 more, each of which doubles the depth of the output until we get to a layer with a depth of 64. So we're starting with an image depth of 3, then moving to 16, then 32, and finally 64. Each of these layers uses a convolutional kernel of size 3 by 3 and has a padding of 1. You can also see that I've kept my one max pooling layer, which will downsample any XY size by 2. I've also included a dropout layer with a probability of 0.25 to prevent overfitting. Finally, I also have a couple fully connected layers. This first layer will be responsible for taking as input my final downsized stack of feature maps. I know that my original input image, which is 32 by 32 by 3, is getting squished in the X and Y dimension and stretched in the depth dimension as it moves through each convolutional and pooling layer. In the forward function, you can see that I apply a pooling layer after each convolutional layer. So this image will reduce in size to 16 by 16, then 8 by 8, and finally 4 by 4 after the last pooling layer. And the third convolutional layer will have produced a depth of 64. And that's how I get these values, 4 by 4 for my final XY size, and 64 for my depth. That's the number of inputs that this first fully connected layer should see. Then I'm having it produce 500 outputs. These 500 outputs will feed as input into my final classification layer, which will see these as inputs and produce 10 class scores as outputs. So let's see how all these layers are used in the forward function. First, I'm adding a sequence of convolutional and pooling layers in sequence. I'm passing our input image into our first convolutional layer, applying an activation function, then a pooling layer. I'm doing the same thing for our second and third convolutional layers. Finally, this resultant x I'm going to flatten into a vector shape. This will allow me to pass it as input into a fully connected layer. In between this flattening layer and each fully connected layer, I'm adding a dropout layer to prevent overfitting. But then I'm passing my flattened image input x into my first fully connected layer. As with all my hidden layers, I'm applying a ReLU activation function. Finally, one more dropout layer and my last fully connected layer. The resultant x should be a list of 10 class scores. Finally, I instantiate this model and I move it to GPU. And below you can see that I've printed out each of the layers in my init function to make sure they're as I expect. This shows me the number of inputs and outputs for each layer, the kernel size, the stride, and the padding, and they all check out. So just to summarize, for every convolutional layer that I defined, I apply a ReLU function and a max pooling layer right after that. After that series of layers, I flatten that representation and pass it to my fully connected layer. Adding some dropout, I'm finally passing it so that it produces 10 class scores. Okay, so I have my complete model, and then I'm moving on to training. I'm going to use a standard cross-entropy loss, which is useful for classification tasks like this, and stochastic gradient descent. Then I'm actually training the network, and I decided on training for 30 epochs. I decided on this value after watching the training and validation loss decrease over time. I can see that I might have stopped training even earlier, around epoch 20, which is where the validation loss stopped decreasing. I saved my model here, the one that got the best validation loss, and then I loaded and tested it out. And I can see when I test this that I get an overall accuracy of about 70%. And that's not bad. It's much better than guessing, for example. And if you've given this task an honest attempt, I can say congratulations on getting this far. You've really learned a lot about programming your own neural networks. Of course, we can see that it does better on some classes than others, and it's always interesting to think about why that might be the case. In general, it seems like my model does better on vehicles rather than animals. It's probably because animals really vary in color and size, and so I might be able to improve this model if I had more images in that particular dataset. It might also help to add another convolutional layer and see if I could suss out more complex patterns in these images. And here I'm just further visualizing which images it gets right or wrong. There's plenty of room to tinker with and optimize the CNN further, and I encourage you to do this. It's a great learning experience. I should mention that in 2015, there was an online competition where data scientists competed to classify images in this database. The winning architecture was a CNN, and it achieved over 95% test accuracy. It took about 90 hours to train on a GPU, which I do not encourage in this classroom, but it does demonstrate that good accuracy is not a trivial task.
When we design an algorithm to classify objects in images, we have to deal with a lot of irrelevant information. We really only want our algorithm to determine if an object is present in the image or not. The size of the object doesn't matter, neither does the angle, or if I move it all the way to the right side of the image. It's still an image with an avocado. In other words, we can say that we want our algorithm to learn an invariant representation of the image. We don't want our model to change its prediction based on the size of the object. This is called scale invariance. Likewise, we don't want the angle of the object to matter. This is called rotation invariance. If I shift the image a little to the left or to the right, well, it's still an image with an avocado. And this is called translation invariance. CNNs do have some built-in translation invariance. To see this, you'll need to first recall how we calculate max pooling layers. Remember that at each window location, we took the maximum of the pixels contained in the window. This maximum value can occur anywhere within the window. The value of the max pooling node would be the same if we translated the image a little to the left, to the right, up, down, as long as the maximum value stays within the window. The effect of applying many max pooling layers in a sequence, each one following a convolutional layer, is that we could translate the object quite far to the left, to the top of the image, to the bottom of the image, and still our network will be able to make sense of it all. This is truly a non-trivial problem. Recall that the computer only sees a matrix of pixels. And transforming an object's scale, rotation, or position in the image has a huge effect on the pixel values. We, as humans, can see the difference in images quite clearly. But how do you think you'd do if you were just given the corresponding array of numbers? Thankfully, there's a technique that works well for making our algorithms more statistically invariant. But it will feel a little bit like cheating. The idea is this. If you want your CNN to be rotation invariant, well, then you can just add some images to your training set, created by doing random rotations on your training images. If you want more translation invariance, you can also just add new images, created by doing random translations of your training images. When we do this, we say that we have expanded the training set by augmenting the data. Data augmentation will also help us to avoid overfitting. This is because the model is seeing many new images. Thus, it should be better at generalizing, and we should get better performance on the test dataset. Let's augment the training data in the CFAR10 dataset from the previous video and see if we can improve our test accuracy. We'll be using a Jupyter notebook that you can download below.
To perform image augmentation in PyTorch, you can use the help of a built-in image transformation library. Here you can scroll through all the common transforms available in the transforms library. You can see transforms that shift around the image from left to right, or that crop the image randomly. In our case, we want our dataset to be a little more rotation and scale invariant, and so we can choose random transforms that change the scale and how much an image is rotated. I'm going to briefly show you how to do this in code, and then you can choose whether or not to use it in your own work. I'm going to augment our data in the same step that I'm loading it in. Basically, I want to add to our composite transform. Where you've previously just seen conversion to tensors and normalization, you can put other types of transforms as well. This transformation randomly flips an image along its horizontal axis, and this code randomly rotates an image by 10 degrees. I apply this transform as usual when I form my training and test data. And that's all you need to do to give your images some geometric variation. After transforming my data, I've gone through the same visualization steps. And we can see by looking at the borders of some of these images that some of our images have been rotated slightly right or left within 10 degrees. Then to see if data augmentation actually improved the performance of our model, I use the same convolutional neural network and loop that I did before. I trained the model over 30 epochs using our augmented training data. In this case, it seemed that the training and validation loss took a little longer to decrease, but may have reached a smaller minimum. I saved this augmented model, and when I tested it, I got 1% more accuracy in general. This is a minor increase in test accuracy, but these small performance improvements can add up and are something worthwhile if you're really trying to find the best model for a task. Generally, in this course, your job will be to design a model so that it can reach a high accuracy. But in addition to that, choices about data augmentation and loss and optimization functions can take that even further, so this is a useful skill to have.
ImageNet is a database of over 10 million hand-labeled images drawn from 1,000 different image categories. Since 2010, the ImageNet project has held the ImageNet Large-Scale Visual Recognition Competition, an annual competition where teams try to build the best CNN for object recognition and classification. The first breakthrough was in 2012. The network, called AlexNet, was developed by a team at the University of Toronto. Using the best GPUs available in 2012, the AlexNet team trained the network in about a week. AlexNet pioneered the use of the ReLU activation function and dropout as a technique for avoiding overfitting. In 2014, two different groups nearly tied in the ImageNet competition. One of those networks was called VGGNet, often referred to as just VGG, and it came from the Visual Geometry group at Oxford University. VGG has two versions, termed VGG16 and VGG19, with 16 and 19 total layers, respectively. Both versions have a simple and elegant architecture, which is just a long sequence of 3x3 convolutions broken up by 2x2 pooling layers and finished with 3 fully connected layers. VGG pioneered the exclusive use of small 3x3 convolution windows, to contrast AlexNet's much larger 11x11 windows. In 2015, the ImageNet winner was a network from Microsoft Research called ResNet. ResNet is kind of like VGG, in that the same structure is repeated again and again for layer after layer. Also like VGG, ResNet has different versions that vary in their number of layers, the largest having a groundbreaking 152 layers. Previous researchers tried to make their CNNs this deep, but they ran into a problem where as they were adding layers, performance increased up to a point, after which performance quickly declined. This is partially due to what's known as the vanishing gradients problem, which arises when we go to train the network through backpropagation. The main idea is that the gradient signal has to be pushed through the entire network. The deeper the network becomes, the more likely that the signal gets weakened before it gets where it needs to go. The ResNet team added connections to their very deep CNN that skip layers, so the gradient signal has a shorter route to travel. ResNet achieves superhuman performance in classifying images in the ImageNet database. We've seen that CNNs achieve state-of-the-art and sometimes superhuman performance in object classification tasks. We've explored some techniques for building CNN architectures, and we've gotten some good performance on toy datasets. But at the end of the day, we don't really have a strong understanding of how these CNNs discover patterns in raw image pixels. If you've already taken the time to train your own CNNs, you've noticed that some architectures work while some just don't. And if it's not clear to you why that's the case, it's probably not truly clear to the experts either. Earlier in this lesson, I mentioned visualizing the activation maps in convolutional layers as one technique for digging deeper into understanding how a CNN is working. There are many implementations of this online. This is one of them, and as you can see, it's designed to pass your webcam's video through a trained CNN in real time. If you'd like to play around with this, you're encouraged to check out the links below. Another technique designed for understanding CNNs involves taking the filters from our convolutional layers and constructing images that maximize their activations. You can start with an image containing random noise and then gradually amend the pixels, at each step changing them to values that make the filter more highly activated. When you do this, you'll notice that the first few layers are pretty general. The first layer might include color or edge detectors, where the second layer detects circles or stripes. The filters later in the network are activated by much more complicated patterns. Researchers at Google got creative with this. They designed a technique called deep dreams, where they replace the starting image with a picture. Say we have a picture of a tree, but you can use a picture of anything here. Then you could investigate one of the more interesting filters, maybe one that looks like it's used for detecting a building. When you follow the same technique, where the only thing you've changed is the starting array of pixels, you end up creating an image that looks like some sort of tree or building hybrid. If you'd like to code this yourself in Keras, you're encouraged to pursue this in the links below. There are many other techniques for visualizing what a CNN learns. We've only scratched the surface with this, but you're definitely encouraged to explore more in this area. The idea is that if we can understand more of what a CNN learns, we can help it to perform even better.
So far, you've seen how to create two kinds of neural networks for image classification. And you've seen how convolutional neural networks follow a series of steps to classify an image. Just to recap, a CNN first takes in an input image, then puts that image through several convolutional and pooling layers. The result is a set of feature maps reduced in size from the original image that, through a training process, have learned to distill information about the content in the original image. We then flatten these maps, creating a feature vector that we can then pass to a series of fully connected linear layers to produce a probability distribution of class scores. From this, we can extract the predicted class for the input image. So, in short, an image comes in and a predicted class label comes out. You've learned the foundational concepts behind CNNs, and in later lessons, you'll learn about techniques that leverage existing architectures and even more techniques for improving the performance of a model. You should also know that CNNs are not restricted to the task of image classification. They can be applied to any task with a fixed number of outputs, such as regression tasks that look at points on a face or detect human poses. The applications of CNNs are very far-reaching, and after seeing just a few, I hope you're excited to learn even more. You've seen how to define and train your own CNNs with a number of specified layers and hyperparameters. And you've also seen examples of some state-of-the-art CNN architectures, like VGG and ResNet. These are the result of careful experimentation with many architectures and extensive hyperparameter tuning. They've been trained on the very large ImageNet database, which has 1,000 object classes. This training data is so large and the models have so many parameters that training models like these often takes weeks, even on multiple GPUs. So it would be ideal if we could find a way to use what these models have already learned and apply that knowledge to a new task. For example, say that you have some images you want to classify like those in the CFAR dataset. Instead of constructing a CNN from scratch, can we instead take the knowledge from a trained CNN like ResNet and use it to help classify this set of images? Yes, we can, and this is best accomplished through a technique called transfer learning. Transfer learning is all about how to use a pre-trained network and apply it to a task of your own design, transferring what it's learned from one task to another. There are a few ways to implement transfer learning, and your approach will depend on how similar a dataset is to the dataset that a pre-trained network has seen. In other words, how transferable can certain knowledge be? In this lesson, we'll answer this question and go over different strategies for transfer learning. And you'll learn how to implement transfer learning in code, using a pre-trained network to help classify different sets of images. Let's take our example of the VGG network. You may be wondering, how can I take this CNN that's been trained to classify 1,000 ImageNet images and apply this to a new problem? What if I wanted to classify images of different flower types, like sunflowers versus daisies, roses, and so on? Well, VGG has learned to distinguish between the 1,000 different categories that are present in ImageNet. Most of those categories are animals, fruits and vegetables, or everyday objects. As VGG trained, each of its convolutional layers learned to extract some information about the shapes and colors that distinguish these different objects. In fact, we know that the convolutional filters in a trained CNN are arranged in a kind of hierarchy. The filters in the first layer often detect edges or blobs of color. The second layer might detect circles, stripes, and rectangles. These are still very general features that are useful in analyzing any image in almost any dataset. The filters in the final convolutional layers are much more specific. If there were birds in the training dataset, there are filters that can detect birds. If there were cars or bicycles, there are filters to detect wheels, and so on. We'll see then that it's useful to remove the final layers of the network that are very specific to the training dataset while keeping the earlier layers. In this way, you can use the convolutional and pooling layers in a pre-trained network, like VGG, as a feature extractor that identifies shape and color-based features in your set of flower images. Then, after an image has passed through this pre-trained feature extractor, we can add one or two more linear layers at the end, which can act as a final classifier. These last layers take in the features from an image, and we can train only these final layers to customize this network for a new task. So even if the image database that you're interested in for flower images has no overlap with the ImageNet categories, it's still possible to use the knowledge from a pre-trained CNN. This is one technique for transfer learning, but your method will depend on both the size of your dataset and the level of similarity it shares with the ImageNet database. For instance, this technique of adding some final trainable classifier layers will work well if your dataset is relatively small and has distinct shape features that are similar to those found in the ImageNet database. If your dataset is very large and different than ImageNet, you may take a different approach. Let's go over one more approach to transfer learning before we implement this in code. How might you use transfer learning if the data you want to work with is very large and somewhat different than that found in the ImageNet database? As an example, I should mention that one of UDACITY's founders, Sebastian Thrun, along with a team at Stanford, recently used transfer learning to develop a CNN to diagnose skin cancer. The CNN classifies lesions as either benign or malignant and achieves performance on par with dermatologists for diagnosing some forms of skin cancer. To construct his model, he used a transfer learning approach with the Inception architecture, pre-trained on the ImageNet database. As a first step, he removed the final densely connected classification layer and added a new fully connected layer. This is similar to the approach that I outlined before, adding a new classification layer with an output size that you define. In this case, this layer has an output value for each type of disease class. As for all of the other layers in the network, their parameters were initialized with their pre-trained values. Then, during training, the parameters were further optimized to fit the database of skin lesions. So, instead of using the pre-trained model as a fixed feature extractor, Sebastian and his team used it as a starting point and then trained the entire network, modifying all the weights such that they were tuned to the medical image classification task. In this case, the model truly benefited from the head start that it was given from pre-training on ImageNet, and this is just another kind of transfer learning. This technique is called fine-tuning because it requires slightly changing or tuning all the existing parameters in a pre-trained network. Fine-tuning often works best if the dataset you're interested in is quite large. Transfer learning is an extremely useful technique, but you should apply it differently based on how big and how similar your dataset is to the data that a pre-trained model has seen. As always, you're encouraged to experiment with different methods. And you'll find more guidance on how to use transfer learning in a variety of scenarios in the text below.
Okay, so let's implement transfer learning in code. In this notebook, I'm going to be using a pre-trained VGG16 network, whose architecture is pictured here, and I'll apply what it's learned to a totally new task. So we know that this model is made of a series of convolutional and pooling layers, and at the end it has 3 fully connected layers that act as a final classifier. In this notebook, we'll be using a pre-trained model that was trained for a very long time to reach a high accuracy in classifying images in the ImageNet dataset. This dataset has 1,000 image classes, and so the final output layer produces 1,000 class scores. But in this notebook, I'll show you how to change this last layer and tune this classification portion of the model to apply it to the task of flower classification. And I'll show you our flower dataset in a moment. It includes 5 different classes of flowers: sunflowers, tulips, roses, dandelions, and daisies. To customize the VGG model for this task, my plan will be to freeze or lock the weights in the convolutional and pooling layers. This portion of the network will act as a fixed feature extractor that all our training images will go through. Then I'm going to replace the final layer of the classification portion with a new fully connected layer, one that produces 5 class scores instead of 1,000 as output. After replacing this last layer, I'm going to allow all 3 of these fully connected layers to train. This means that I'll be fine-tuning the weights in 2 of the linear layers and newly training the weights in this last layer. So let's get started with this task. First, I'm going to load in my usual libraries and check if a GPU device is available. For now, since I'm going through this exercise, I'm using my laptop CPU. Then I'm going to load in my data as usual. This time, my data is in training and test directories. Each subdirectory represents one particular flower class. This structure makes it easy to load in this data using PyTorch's image folder class. This class just assumes that images are in their correctly labeled folders, so all sunflowers are in a sunflowers folder, for example. Now I know that VGG expects to see 224 by 224 square images as input, so I'll resize all of my images using a data transform and load it in. And I'll just load in training and test data for now. You can choose to separate out a validation set should you want to. And you can see we only have about 3,000 training images and even fewer test images. This is a lot smaller than, say, something like our MNIST dataset. So it will be interesting to see how transfer learning works for such a small dataset. And here I'm using the data loader class to load in our data in batches. Finally, I'm going to visualize a batch of this data. Here I see a variety of flowers and their respective labels. And we can see actually the variety in these images. Some flowers are very close up, while others are really far away. So we can tell that this task will be more challenging than if flowers were carefully centered and pre-processed. After loading the data, next comes defining the model. Now, the first step in working with a pre-trained model is knowing how to look at the structure that already exists. Here I'm going to load in the VGG16 model from PyTorch's model library, which contains many commonly used models. I want this model to be pre-trained, and I'm calling it by name and storing it in this variable. Once it's loaded in, I'll print it out to see all the layers. Here I can see the entire VGG network. First, there's a sequence of layers that's called features, a series of convolutional and max pooling layers. Then I have another group of layers down here called classifier, and this is where our 3 fully connected linear layers are. I can also see things like how many inputs and outputs each of these layers have. And now I can refer to any of these layers, groups of layers, or individual layers by name. For example, I can type VGG16 .features to get this whole group of layers. Or to refer to this last linear layer, I can refer to VGG16's classifier section and the value 6. For example, here I can access that last linear layer and print out how many in features and out features it has. And we can see that these values line up with what we printed out before. Now that you know how to read in a pre-trained model, next I'm going to show you how to freeze the weights in the feature layers and replace this last layer with a new linear layer suited to our flower classification task. So when we left off, I loaded in the VGG model with pre-trained weights, and now I want to do two things. First, I want to freeze the weights in the features layers, so all the pre-trained convolutional weights will not change during training. Then this part of the VGG network will act as a fixed feature extractor that will operate on any input image in the same way. Next, I want to replace the last linear layer with a layer that outputs 5 class scores, and I'll train the 3 fully connected layers. So let's scroll down and address the first task, freezing some pre-trained weights. To freeze the convolutional weights, I'm going to iterate through every parameter in the list of VGG features parameters. Recall that features is just the name of the group that encompasses all of these convolutional and pooling layers. And I'm going to say for every weight, the required grad property is false. PyTorch during training automatically keeps track of the gradient of the training loss with respect to the model weights. But if this is set to false, these weights will be left alone and not considered in those gradient calculations. In other words, by setting this parameter property to false, we're freezing these weights and they'll stay at their pre-trained values. Next, I want you to change the last layer of this model, and I think you know enough to try this task on your own. All you need to do is grab this final fully connected layer by name and number, then set it equal to a new linear layer with the correct number of inputs and 5 outputs. To define just one layer, you'll use nn.linear, much like you would in the init function of a net class. So I'll leave this as a challenge for you to complete. I'll also add one more challenge. I'm going to leave this training loop empty. You've seen a number of examples of the training loop, and by using a reference or from memory, I want you to code up an epic and batch loop that iterates just through the training data. I also want you to record the training loss as you go and print it out. Next, I'll show you how to add a final layer and train the complete model. So we've loaded in a pre-trained VGG16 model and frozen our features parameters. Our next task was to replace the last layer of the model so that instead of outputting 1,000 classes, it outputted 5 values for our 5 flower classes. And this actually only takes a couple lines of code. First, I need some information about the layer that I want to change, so I'm going to get it by name, VGG classifier 6. From printing out our model architecture, we know that the classifier contains 3 final fully connected layers, and 6 points to the last linear layer specifically. Now I know I need to define a new linear layer that takes in as input the same number of in features as the existing last layer. So I'm saving this number of inputs as n inputs. Then I'm defining a new last layer. I'm defining a linear layer as usual using our nn library. I'm defining this layer to take in those inputs and produce as many outputs as we have classes. In this case, this length should be 5. Then again, I'm going to reference this last layer that I want to replace and set it equal to this last layer that I just defined. This effectively replaces the old layer with the new layer. Now I should have a complete VGG16 model, and I'll move this whole model to GPU if available. Finally, I'm just going to print out the number of out features in this layer, just to check that I've done this correctly. And we can see that this produces 5 outputs, which is exactly what I expect. The next detail here is to prepare this whole model for training. I'm going to define loss and optimization functions as usual, only this time you'll notice that in the optimizer, I'm actually only passing in the parameters for the classifier. These classifier parameters are the only ones that I want to change during training. Then we get to the training loop. I suggest training on GPU to speed this process up since these networks still contain a lot of parameters, even in just the fully connected layers. And I'm only going to train for 2 epochs. Since this model is pre-trained, I should only need to train for a little while to tune this model to our flower classification task. So in our training loop, I'm keeping track of the loss. My first step is moving any data to GPU and then zeroing out any accumulated gradients. I'm then passing our image data into the VGG16 network. This produces an output of class scores. Here I'm calculating the cross-entropy loss and performing a single optimization step to change the weights of our network. This step is only attached to the last few layers of our VGG model. The rest of the weights are frozen. And here I'm just updating the training loss and printing it out every 20 batches. I can see that the loss starts out kind of small and decreases in kind of a wiggly fashion. Sometimes the loss moves up before it moves down again. But let's see how this performs after just 2 epochs of training. Here I'm iterating over our test data and I'm checking how our model does on our 5 classes. After only 2 epochs of training, our model gets 74% accuracy on our images. So even though our dataset was small, I've managed to transfer the learnings from the VGG network to this very specific flower classification task. Let's take a look at what this looks like visually. Here are some correctly and incorrectly classified images of flowers. Now, we know that transfer learning worked because even though VGG was initially trained to recognize 1,000 different image types, the way it distinguished those images by finding color and geometric patterns translated into distinguishing images of flowers as well. And you can see that some of the images this model fails on are even difficult for us to identify. There are many models that you can try to implement transfer learning with, and you can even try training for a longer amount of time or fine-tuning entire models. Take a look at the documentation on available pre-trained models and experiment with creating your own applications. You could even extend this example to create something like a weed versus flower application for gardeners. To me, the excitement is really in the variety of data that's out there, data that you can train your models to learn from. So let your imagination be your limit. Hello! So you've learned a lot about CNNs, and in this lesson, I want to talk about a detail that's been happening behind the scenes when we build and train neural networks in PyTorch, and that's weight initialization. Weight initialization happens right when a model is created, before it sees any training data, and it generally only happens one time when a model is first created. Weight initialization is all about how you can instantiate a model, like a CNN, so that its weights, the model parameters, are starting off with the best initial values for a given task. You might think of it this way. Any neuron in a model has some weights and biases that operate on some input values and transform them into desired outputs. It's how you might transform an input image into some class scores. And a model is trying to learn the best weights to map inputs to outputs and, say, most accurately classify some given images. When we did transfer learning, we basically initialized a network with the best pre-trained weights that we know are good values for image classification. But for a non-pre-trained model, how should we initialize the weights? We could start, for example, by saying all the weights are going to be 0, and we'll train them until they're shifted up or down. Or we could start out with large weight values, or even some random values, and see what happens. These are the questions that we'll be exploring in this notebook. Now, in this notebook, I'm going to demonstrate the effect of different weight initialization strategies. We'll discuss how you might decide on initial weights and what indicates good initial behavior during training. As usual, this code will be provided for you in our public GitHub repo, so you can work through it too and see how all of this works. The plan is this. We want to define one kind of model, a simple MLP, and we'll initialize the weights of this model with different values and compare how the training losses decrease over the first epoch or 2 of training. So same models, different initial weights. Here's an example where we plotted the training loss over 100 batches for 2 different initialization methods. These are just examples. Some initialization strategies may offer some really big improvements to how the loss decreases, and others may offer small improvements, such as here. It's very hard to tell the difference. But big or small, we can learn from all of these differences. So what we're going to do is define a simple MLP for classifying images in the fashion MNIST dataset. In the first couple cells, I'm going to load in this data with a batch size of 100. The images in the fashion MNIST dataset fall into one of 10 classes. You have t-shirts, shirts, sneakers, bags, ankle boots, and so on. And here's what a few of those images look like with their respective labels. And you may have seen this before. It's just a dataset of grayscale images of clothing types, very similar to the MNIST dataset. But this classification task is a little more challenging than just handwritten digits. A simple dataset like this one is often used to test network performance because the dataset is simple to use and its training behavior is fairly well understood. We know, for example, that we should be able to get the training loss to reliably decrease. So I load in and look at my data as usual, then we get to the model definition. And here's a little diagram of the MLP I'm planning to build. This MLP has an input layer, 2 hidden layers whose size I've specified, and a final output layer that outputs 10 class scores for our 10 clothing types. The hidden layers will have 256 and 128 nodes, respectively. Again, we just want to keep it simple so that we can focus on how weight initialization affects the performance of such a model. And if you scroll down a bit, you can see how I've defined that model here. I have a flattened input x that I pass to a fully connected layer, and I apply a ReLU activation function to each of my hidden layers. I add some dropout in between, and I have my final fully connected layer, which produces 10 class scores. Then, to actually train this model, I've put that code in a helpers.py file, which you can find by clicking on this Jupyter icon here. The purpose of this notebook is not to train the model until it performs well on the classification task, but rather we just want to see how well the models train given different initial weights. So let's see what's in the helpers.py file. Here's our main helper function getLossAck, which takes in a model and a training and validation loader. In here, I've defined the length of time to train a model, choosing 2 epochs. And I've also defined a loss and optimization function in here. I'm using cross entropy and an atom optimizer, which is one of my go-tos, but feel free to change this to stochastic gradient descent and see how it performs. Then in this function, I'm actually going to train this model for 2 epochs and record the training loss as I go. This loss is going to be recorded in a list called loss batch. After a model has trained for 2 epochs, I then see how it performs on our validation dataset. I compare the predicted and the correct class and see which ones match. Finally, I return the list of training loss over time and that validation accuracy. Then you'll see another helper function, compare init weights, which takes in a list of models. For each model in our list, it will record the training loss and the validation accuracy over 2 epochs. And there's some code to visualize this loss and compare at least 2 models. Okay, so you can take a look at the helper code and understand how all these things work, but there's no need to change anything about the code that I've shown you so far. Now that I've introduced you to these resources and this notebook, in the next few videos, I'm going to demonstrate how to set your weights appropriately and compare that behavior. So we have the general layout of our MLP, and we're training this model to classify 10 types of clothing in the Fashion MNIST dataset. And we really just want to look at how a model trains when it's given different initial weights. So I want to start off with a simple example for initializing weights. Kind of the simplest idea for setting your model weights is to just set them as a small constant value, say setting them all to be 0 or all to 1. Consistency seems like it could be a good solution because you might think that you don't want to start out by giving more weight to one node than any other. There are a few ways to initialize the weights of a network, and in this case, I'm going to actually pass in a constant weight variable. This will give me the ability to pass in a constant weight when I instantiate a model. The next thing I want to do is actually use this constant weight. Inside the init function of our model, I'm going to check if a constant weight has been passed in. Let's say I've passed in a constant weight of 0, then we enter this if statement. This looks at every module or layer in our model. Then it says, okay, let's check the layer type. For every linear layer, I'm going to set the parameter weights to a constant value using nn.init.constant. This takes in the weights we want to set from our module and a constant weight value, which we passed in. And I'm doing the exact same thing for our module bias, only I'm setting the bias to 0. So all I had to do to set the weights is to specify how I want to initialize each linear layer and then use the nn.init library to help set those values. This library includes a lot of common initialization schemes that we'll go over. Okay, next I actually need to instantiate 2 different kinds of models with 2 different constant weights. Here I'm going to create one model 0 with a constant weight of 0. And I'll create another model 1 with a constant weight of all 1s. I'm going to create these models, then using my helper functions, I'm actually going to compare these 2 models and how they perform over 2 epochs. So I'll turn these into a list, all 0s and all 1s, giving a title to each model. And then I'm going to compare the initial weights using the helpers function. This cell may take a few moments to run as these models go through 2 epochs of training. And here's the resultant plot. You can see that a model that starts out with all 1s as weights starts out with an extremely high initial loss. Usually for something with cross entropy loss, I'm expecting a value in the single digits. You can also see that when a model is initialized with all 0s, this line just sort of remains flat over time and doesn't change. The loss never really decreases. So what exactly is happening here? Let's talk a bit about our model that starts out with a constant weight of 0. In this case, every single hidden node is going to respond to the inputs it sees in the exact same way. It'll multiply all of these inputs by a constant weight of 0 and then add all of them up. This behavior repeats in the second layer where all the weights are 0, and again in the third, producing a series of class scores. Now in any training process, these class scores will not be very accurate at first, But that's okay as long as you can learn from any mistakes. But in the case of all zero initial weights, when you go to calculate the cross-entropy loss and use backpropagation to identify sources of error, it all of a sudden becomes very hard to see which weights, which nodes, are responsible for making any errors. Because the weights were all zero in the hidden layers, all the gradients that tell us how the error changes with respect to each weight are also all the same and can't tell us anything. We have a really hard time finding out which weights should be updated and by how much. And something similar happens if the weights are all initialized as ones. When the weights are all ones, then again you're going to have your input pixel values multiplied by 1 and summed in a hidden node. Again, the hidden layer calculations are going to be the same as inputs move forward through the MLP layers, and when we try to identify sources of error, we can't really. So after 2 epochs, I'm also recording the validation accuracy of these two models. We can see about 9.7 and 10.2 accuracy for the all zeros and all ones initialization models. And that means that these networks are getting like 1 out of 10 classes correct. And for a 10 class problem, as our fashion MNIST task is, that's the equivalent of guessing 1 class randomly out of 10. So this is really bad. In fact, the zeros model is not even randomly guessing, it's just guessing the same class over and over again. I should note that initializing with all ones seems particularly bad, and this is because ones are really too high of a starting value. So the backpropagation algorithm has an especially hard time bringing those values down and getting to the minimum of the loss. So these constant weights are basically just performing really poorly, but it's still helpful to see this behavior through a critical lens. Again, because our weights are all the same, that means the activations of all our units in the hidden layers are also all the same, and so the backprop algorithm struggles to minimize the loss. Using constant initial weights essentially sets up backpropagation to fail, because it's not designed to deal with consistency. Backprop is designed to look at how different weight values affect the training loss. So how might we change our initial weighting scheme so that we set up the backpropagation algorithm to succeed and better differentiate between the effect of different weights? I want you to think about this question, and then we'll talk about a few more effective and common initialization schemes. Weight initialization is really about giving models the best chance to learn when training. And since many models rely on iteratively improving by looking at the mistakes they've made, we want them to start out making more informative mistakes, ones that are instructive and provide information about how exactly a model can improve. We found that this was not the case when we initialized with constant weight values, so it might make sense to take a totally different approach. Instead of setting everything to all zeros or all ones, what if we want to have all of our weights initialized as unique numbers? The best way to do this is to randomly grab a bunch of unique numbers, which we can do by sampling from a probability distribution. A good solution for getting these random weights is to sample from a uniform distribution. A uniform distribution has equal probability of picking any number from within a range. We'll be picking values from a continuous distribution, so the chance of picking the exact same number is very low. First, I'll show you what these values might look like by using a helper function that displays a set of random values as a histogram. Here I'm using NumPy's random.uniform function to pick random numbers from a uniform distribution. This function takes in a low and a high bound on the range of random values to generate. And here I'm specifying that it should generate 1,000 random values in a range from -3 to +3. And here's the resulting histogram. A histogram is made of many rectangles whose height is proportional to the frequency of a certain value. In this case, our histogram is actually creating 500 buckets for each of our 1,000 generated values. And for a uniform distribution, we should see that most buckets then contain 2 generated values, which we can see by this line 2 about here. A few buckets have 0, 1, or up to 10 values in them, but this is just a little bit of randomness. In general, we should see that these values are fairly uniformly distributed along this range. By picking the initial weights of a model from a distribution like this, we're incorporating some randomness that should help our model train. And we can still set some constraints on which values our weights take. Now that we've seen a uniform distribution, let's see how well our model trains if it's initialized with uniform weights, where I'll set the low value to be 0 and the high value to be 1. And here I'll show you one other way, besides in our net class code, to initialize the weights of a network. To define weights outside of the model definition, you can define a function that assigns weights by the type of network layer, then apply those weights to an initialized model using model.applyFn, which applies a function to each model layer. So here I'm defining a function weights init uniform. This will be applied to every single module in our model. and here I'm checking for any linear layers in our model. For the weights in each linear layer, I'm going to apply a uniform distribution with a low range of 0 and a high of 1. And here I'm setting the bias to a constant value of 0. Just like nn.init, there are a number of distributions that you can call upon to initialize the weights of a network in this way. Then there's one more step. To actually initialize a model with these weights, I'm going to instantiate a new model. I'm going to call it model uniform, and I'm going to set it equal to a default net. Notice I'm not passing in any constant weight value here. Then to apply my uniform weights, I'm going to call apply weights init uniform on this model. Apply will recursively call my initialization function and apply uniform weights to every linear layer. This will also print out some details about that model. Finally, I'm creating a model list of just length 1, and I want to see how this uniform model performs. Here we can see that the loss still starts out fairly high, but it's decreasing fairly reliably. And after training for 2 epochs, our model gets around 33% accuracy, which is much better than just guessing, so we know that we're on the right track. Now earlier, I did mention that the value of 1 is actually a bit too high of a good starting weight value. So choosing weights from a uniform range of values between 0 and 1 is actually not the best range to choose from. You may be wondering, how can I select a better range? Well, we know that for fully connected layers, each node will see every input value, multiply it by a model weight, and then add the weighted values together. In the case of Fashion MNIST, each hidden node in the first layer is seeing 784 input values. The next layer is seeing 256 input values, then 128 as input. Because the model weights act as multipliers for all the inputs, it makes sense that the weights should be somehow related to the number of inputs that each node is going to see. In fact, the relationship is an inverse one. The more inputs a certain node sees, the smaller its weight should be. So let's see what exact kind of range we should try. A general rule for setting the weights in a neural network is to set them to be close to 0 without being too small. More specifically, we should start with weights in the range of -y to y, where y equals 1 over square root n, and n is the number of inputs to a given neuron. So this rule is basically saying 2 things. The weights should be centered around 0, and their range should be quite small and inversely related to the number of input nodes for a given layer. So let's see if this holds true, and let's first create a centered baseline to compare with. Let's center our uniform range over 0 by shifting it from 0 to 1 to -5 to 0.5. Here I'm defining a whole new initialization function, weights init uniform center. Then for every linear layer in our network, I'm going to initialize the weights of that layer using a uniform distribution with a range of negative to positive 0.5. Then I'm creating a new model, model centered, and applying these centered weights to that model. Then I'm going to do the same thing only for our general rule, which uses a value of 1 over square root n. I'm going to have to reference the number of inputs to a given layer. So here I prepared an initialization function, and I'm looking at every linear layer. Now I just have to define y. I can get the number of input features from a specific layer by calling m.inFeatures, and I'm storing that as a variable n. Then I'm calculating y as 1 over the square root of n. Finally, I'm initializing the weights of each linear layer with a uniform distribution that's centered around this value y. Then I'm creating another new model and applying these initial weights to it. Finally, I'm going to compare the behavior of these 2 models, model centered and model rule. I'm giving each a descriptive name and using my compare init weights function to see their behavior over time. So first off, we can see on the y-axis that our loss values are orders of magnitude smaller than what we've seen previously. And this behavior is really promising. Not only is the loss decreasing for both of these models, but it seems to do so very quickly for our uniform weights that follow the general rule. After only 2 epochs, we get a fairly high validation accuracy, almost 86% for using our general rule. And this should start to give you some intuition for why starting out with the right initial weights can really help your training process. Now, there's really one more kind of distribution that I want to take a look at before we wrap up. Since the uniform distribution has the same chance of picking any value in a range, what if we used a distribution that had a higher chance of picking numbers closer to 0? This is the normal distribution, which we'll look at next. Now I'm going to go over using a normal distribution for selecting initial model weights. So again, we'll first visualize what this looks like using NumPy and a histogram. This time I'm using np.random.normal. And this, instead of taking in a low and a high range of values like the uniform distribution, takes in a mean and a standard deviation. If a mean and standard deviation are not specified, as they weren't here, the defaults are 0 and a standard deviation of 1. So I'm telling it for a mean of 0 and a standard deviation of 1 to create 1,000 values. Now the mean should just be the average of all these values, the center value. And the standard deviation represents the spread of values around that mean. And you can see here what a normal distribution looks like for a mean of 0 and a standard deviation of 1. Most of the values are concentrated in this range. Again, we're using histograms, so we've bucketed 1,000 values into 500 buckets. In the uniform case, the values were pretty evenly distributed along the range, and they fell about 2 values to a bucket. Here, a normal distribution has most values collected near the mean, 0. And the histogram itself looks like a kind of curve that shows how values fall within a standard deviation of the mean. So if we select our initial model weight values from this kind of distribution, we'll get random values that are generally closer to 0 than if we selected from a uniform distribution. And picking small weight values initially may offer some benefits. In fact, I'm going to leave this as an exercise for you, since you've seen a number of examples of weight initialization already. I want you to define an initialization function, then initialize the weights in every layer of our model by sampling from a normal distribution. The distribution should still follow our general rule. It should have a mean of 0 and a standard deviation that's equal to 1 over the square root of n. Once you complete this function, I want you to compare a few different models. Compare our weights with uniform initialization and normal initialization. Finally, I want you to create a third model, one without any explicit weight initialization. Take a look at how these 3 models compare, and next I'll show you my implementation. Alright, here's my solution. I created a function that initializes the weights of our model using values taken from a normal distribution. Again, just another function that we can apply to the module weights. And here I'm defining a distribution with a mean of 0 and a standard deviation of 1 over square root n, where n are the number of inputs to a given layer. So the range that these weights cover should change based on the number of inputs to a linear layer. And as usual, I have a bias of 0. Then I'm creating 2 models to compare. The first, model uniform rule, I'm initializing using our function from above, weights init uniform rule. Then I'm creating another model that uses the function I defined right here, with weights from a normal distribution. For me, it's easiest to create new models right before I compare them. This way I know I haven't accidentally trained one of them for a couple more epochs than another one. After I've initialized my 2 models, I'm comparing them by creating a model list and using my compare init weights function. Here we can see that the model initialized with weights from a normal distribution and from a uniform distribution both behave kind of similarly. Please note how low the starting loss value is here. This similar behavior is likely because our network is so small. A larger neural network will pick more weight values from each of these distributions, magnifying the effect of both initialization styles. So if the normal distribution shows a small improvement here, you could imagine that this could be magnified in a larger model. I'd also like to point out really how far we've come. If we scroll up all the way to our constant weight values, we can see that we've really improved. We've gone from pretty bad constant weights to adding some randomness using a uniform distribution. This allows our model to make more informative mistakes that it can better learn from. Finally, we went over the general rule for selecting weights from a range, which depends on the number of inputs a layer sees. And now we've seen that selecting weights from a uniform or a normal distribution can help us reach a high accuracy pretty quickly as we train. Now let's test out one more model, and that's one without any explicit weight initialization. So here I'm simply instantiating a model, not passing in anything and not applying any initial weights. I'm passing this model alone with a title into our comparison function. Now you can actually see that the default behavior is quite good. In fact, it looks really similar to our model with initial weights taken from a uniform distribution. And this is because every type of PyTorch layer has a default weight initialization that happens behind the scenes. In fact, we can see this default initialization by looking at the module source code. Here's the source code for a linear layer in PyTorch. Here in the reset parameters function, we can see that every linear layer is actually initialized with weights taken from a uniform distribution. In fact, even the bias has some random range. But I'd caution you to be careful about this default initialization. It will often be the case that weights taken from something like a normal distribution instead can get us better results. So it may still be useful, especially if you're trying to train the best models, to initialize the weights of a model according to the rules that you define. And this is not the end of your learning path here. You're encouraged to look at the different types of common initialization distributions in the documentation. And as you continue to learn in the classroom, you'll also see more resources for learning about and practicing weight initialization.
You've learned how CNNs will take an input image and, through a series of layers, transform that input into an output that's much smaller in the x and y dimensions, but much greater in depth. Along the way, the CNN is discarding spatial information from the input image and isolating high-level information about its content. Some of this structure can also be thought of as a kind of data compression, compressing from an image into something like a feature vector, which is basically a feature map produced after an input has gone through a series of layers, squished into a vector shape. And this is part of what makes up something called an autoencoder, which is what you'll learn about in this lesson. An autoencoder has two main components: an encoder that compresses some input data, and a decoder that reconstructs data from the compressed representation. You might be wondering, why is this kind of structure even useful? And it ends up being useful in a number of cases. Autoencoders are used in a traditional data compression sense in that they can learn to reduce the dimensionality of any input. Then anyone can use a compressed representation to share it or view it and so on faster than they could with the original input. You might think of something like a JPEG or MP3 file type, which contain explicit rules for compressing images and audio. The difference is that an autoencoder learns efficient data compression and decompression functions, instead of having them designed and coded by a human. Autoencoders have shown the most promise in image denoising techniques and in filling in missing data. This structure will also come up again as you learn about generative models that can take in an image and transform it into a related space, such as from grayscale to color or from low to high resolution images. The encoder and decoder here are both built with neural networks. Generally, the whole network is trained by minimizing the difference between the input and output. In this way, the middle layer will be a compressed representation of the input data, from which you can reconstruct the original data. The key aspect of an autoencoder is its ability to compress an image such that its content is still maintained. Then later, you may be able to use this compressed representation to generate something else. In this lesson, I'll show you how to build autoencoders in PyTorch. I'll start with a simple example where we'll compress images. Then, since this is image data, we'll improve it by using convolutional layers.
In this notebook, we'll be defining and training an autoencoder. So as we talked about before, an autoencoder is basically just a model where we pass in some original data, for instance an image, and then we compress it down to a smaller size. This mapping from an original to a compressed image is learned. An autoencoder will try to compress this image and then reconstruct the original image from the compressed representation. In this example, we'll be working with MNIST images, where each image is a 28 by 28 by 1 array with a total number of 784 pixels. Using an autoencoder, we can compress this down into a smaller matrix or vector with a smaller number of values. This compressed representation could be useful if we wanted to take up less space on our hard drive or share a small data file over a social network or with a friend. Compressed data is often cheaper to store in data centers and faster to share across Wi-Fi connected devices. So what we're really interested in here is this compressed representation and this more efficient way of storing our original image. Once we have our compressed representation, we can pass it through a decoder to reconstruct our original image. In practice, autoencoders really aren't that good at traditional image compression when compared to something like JPEGs. But you'll find that their two-part structure of an encoder and decoder will be really useful. And autoencoders have found use in denoising images, which we'll get into in a later notebook. So here, I'm going to get you started in implementing an autoencoder in PyTorch, and you're actually going to build the network yourself. The idea is that we define our encoder and decoder as neural networks. Then we train this complete autoencoder by passing in an original image and getting back as output a reconstructed image. We can then compare the original with the reconstruction. And we want the original and reconstructed image to be as close as possible. So our loss will actually be comparing these pixel values and measuring the difference between the original and reconstructed images. Once this whole network is trained, we should have a working encoder and decoder portion of a network. And we'll be able to use either part to either compress or decompress a certain image. So first things first, I'm importing some of the libraries that we need, everything we need to load in and start working with our data. Then I'm going to load in training and test MNIST data. I'll also transform this data into a tensor data type. Next, I'm going to batch up this data and use PyTorch's data loader class. You'll notice that I'm only defining train and test loaders here, and that's because, in this case, I really just want to get my training loss as low as possible. This is not a typical classification task, and validation sets are really most useful when you're trying to predict a quantity like a class. Next, I'm going to visualize just one of our images. Again, this is a 28 by 28 by 1 tensor, where 1 is the depth of the color channel. This indicates a grayscale image. So this is an example of original data that we're going to be passing through a network, and it's what we're going to be trying to compress and then reconstruct. Next, we want to define the autoencoder network, and here's a diagram of the network that we're going to build. In this simple example, we'll make an autoencoder out of linear layers. Before we pass anything to our model, we're going to flatten our input images from 28 by 28 into 784 long vectors. We'll pass this flattened input into our encoder. Then the encoder will just be one linear layer that sees our input and produces a compressed representation. The size of this representation will be a size that we specify. This will be a parameter that you pass in code called the encoding dim. For example, we may specify that we want a compressed representation with 32 values. Then, this compressed representation will be fed as input into the decoder. The decoder is responsible for forming a reconstructed image, and so its job is to essentially reverse the encoder operation. This decoder will also be made of one linear layer that will upsample or increase the dimension of the compressed representation. We want this layer to output a vector of length 784. Later, we'll reshape this vector output into a 28 by 28 reconstructed image, and then we'll be able to compare these two. So in the code, you should define these two layers, making sure to produce an encoded compressed vector of this encoding dim size. You'll define these layers in the init function and apply them to an input in the forward function of this autoencoder. Now in this forward function, you'll want to apply a ReLU activation function to every hidden layer, except for the final layer. The final output layer will have a sigmoid activation function to scale its values to be grayscale pixel values between 0 and 1. After defining the model, you can instantiate it and afterwards train the network. Try to create this autoencoder on your own, and next I'll walk you through an example solution and show you how this model trains. Your task here was to define the linear layers to make up a simple autoencoder. The encoder will be responsible for compressing an input image, then the last layer will use that compressed representation to produce a reconstructed output image. If you want to get more complicated with this, you could stack up more and more linear layers, as many layers as you want, as long as you have a midpoint where the outputs represent your compressed representation. In this case, no matter how many layers you define, you want the output to be 784 units to match our original input image vector. This way we can compare the reconstructed output directly with the input values. So here's my solution. In this example, I've defined the encoder and decoder as being made of one linear layer each. The encoder sees our 784 pixel inputs and produces a specified number of outputs. This output is a compressed representation that is encoding dim units long. And in this example, this value is 32. So this layer is going from 784 inputs to 32. Then I just reverse this process in the decoder portion. Here I've created one linear layer that sees these 32 values as input and transforms them back into the larger 784 value long image vector. In the forward function, I've applied a ReLU activation to the encoder layer and a sigmoid to scale the values that have been output by the decoder. The X that's returned will contain 784 normalized grayscale pixel values. And here I've instantiated the model with an encoding dim of 32. Next comes training. To train your network, you have to define appropriate loss and optimization functions, and I'm going to help with this bit. Now, this is not our usual classification task, so we're actually going to be using a different kind of loss. We're using a mean squared error rather than cross entropy. MSE loss is a good loss to use when comparing pixel quantities rather than class probabilities. I'll also use an atom optimizer rather than gradient descent, simply because it's been proven to work better in these scenarios. Okay, then in the training loop, the epochs and looping through batches of data should look pretty familiar. The main thing to note here is that we are only using the images from the train loader. We're actually not interested in any labels, only in original images and their reconstructions. Here I have to flatten these images and then pass those vectors to our model. Our model returns reconstructed image outputs. Then finally, we're comparing the input images and this output reconstructed image. And so our loss is actually telling us how good of a reconstructed image our model has produced. After all of this, later down in the notebook, I've also provided some code for you to test out your model by giving it some test images and visualizing the reconstructed images. All right, next I'm going to talk about how your training loss might look over time and show you some reconstructed images. All right, so you've been given a chance to define and train an autoencoder of your own, and I want to show you what training looked like for my simple model. I decided to train for around 20 epochs. I looked at the trends in training loss and saw that the biggest decreases happened at the start of training, and then minor decreases around epoch 14 or so. So if I trained for longer than 20 epochs, I'm not sure I would have seen much of an improvement. But this loss is only one way to check how well your model is doing. For a classification model, recall, we would often look at classification accuracy, but here the task is a little different. This whole time, we're comparing original input images to their reconstructions, so a better way to see how your encoder is doing is to look directly at those reconstructions. Here I'm loading in a batch of test data, and I care only about the images. I then flatten those test images and pass them to our model to get some reconstructions. Finally, I resize this output so that it's reshaped into a 28 by 28 image. And this code displays 10 original images and their 10 reconstructions underneath them. And you can check out the result. For the most part, these reconstructions look pretty good, almost identical to the original images in some cases. But there do seem to be some weird blurry artifacts around the edges and curves of some digits. You can experiment with adding more linear layers to this model, but next, since we know that most image analysis tasks are better done by convolutional layers, let's see how we might create a good convolutional autoencoder.
Now that you've seen how to build an autoencoder out of linear layers, let's improve on this model using convolutional layers. Convolutional layers give us a way to preserve spatial information, and so, generally, they're part of a better and more elegant solution for encoding and decoding images. The encoder portion of an autoencoder is something that you've seen before in our lesson on CNNs. It's typically made of a series of convolutional and max pooling layers that downsample the spatial dimensions of an input image. So, you know roughly how to get from an input image to a compressed representation already. The decoder is something we haven't really seen before. How can we go from a compressed representation to a reconstructed image? In the simple code example, you've seen that you can just define a linear layer to transform any number of inputs into your desired output size, and so you could easily reverse the encoder steps. Here, with an input image instead of a vector, there are a couple of approaches you might take, but the end goal is the same. You want to reverse the downsampling process that happened in the encoder. You want to increase the spatial dimensions of a compressed input to produce a reconstructed image that has the same shape as the original input. So, instead of downsampling using max pooling, you could imagine trying to upsample an image by unpooling the pixel values in an input. You could use an interpolation technique like nearest neighbors or another kind of linear interpolation. Nearest neighbors expands a given area by copying over a single pixel value from an input image to, say, a 2x2 area in the larger output image. If you've ever tried to enlarge a low-resolution image, this kind of upsampling is usually what happens. But interpolation is a fairly crude way to upsample an image. In the case of nearest neighbors, we're just copying over existing values. But a realistic larger image is likely to have more variety in pixel values, and so there may be a better way to upsample this image. So you could also try to learn how to best upsample an image. If we want our network to learn how to upsample, we can use a transposed convolutional layer. This layer does not use a predefined interpolation method. Instead, it has learnable parameters. You'll sometimes hear these referred to as deconvolutional layers, but it's not strictly undoing a convolution step. I find it most helpful to think of transposed convolution as a way to upsample existing input values using filter weights in a way that's similar to traditional convolution. Before we use this in code, let's get into the math behind a transposed convolutional layer. To understand how a transposed convolutional layer works, let's briefly revisit the convolution operation. Imagine that we have an input image that's 4x4 pixels, small but good for an example, and we want to produce an output filtered image that's the same size. This is our usual case, and we've seen that we can use a 3x3 kernel and a padding of 1 to get this result. Convolution tells us to multiply each pixel value in the input image by the weights of the overlaid kernel, and then add them all up to get the resultant output pixel value. We typically have a stride of 1 to do this for every pixel in the input image. But what if we had a stride of 2? Well, our kernel would move to the right and down by 2 pixels at a time instead of 1, and the output would be a 2x2 filtered image. The filter is moving 2 pixels for every 1 pixel in the output image, and it turns out that the stride value is roughly the ratio of the input to output dimensions. In this way, a convolutional operation can actually downsample an image. Now keep this stride value of 2 in mind as I show you how transpose convolution reverses this process. It can take a single pixel from a 2x2 image, place a 3x3 kernel over it, then multiply that 1 pixel value by the kernel weights to get a resultant 3x3 pixel area. Say I do this with the first pixel, and I get a 3x3 output area with some center. Then I try to do the same thing for the second pixel. I'll assume that my stride is 2 in the output, so the center of the generated area will be 2 to the right of the center of this 3x3 area. Now transpose convolution will produce another 3x3 area, one that overlaps with the initial one. In the case of overlap, these values will just be summed together. If I do this for all 4 of the input pixels, I will get a 5x5 resultant area. There are some options to add or subtract padding from this output, but in the most common case, I will use a 2x2 filter and a stride of 2 to double the x and y dimensions of an input. The weights in the kernel here are learned, much like in a convolutional layer, only this time the purpose is to learn effective upsampling. Next, I'll show you how to define and train a convolutional autoencoder that utilizes transpose convolutional layers.
In this notebook, you'll be implementing an autoencoder with convolutional layers. Convolutional layers are meant to work with spatial data like images, and where we saw some blurriness and small noise in our simple autoencoder reconstructed images, I'm hoping to get a little better performance here. So, just like last time, we're just importing our packages and modules and getting the MNIST data. Right here, I'm just taking a quick look at our data to make sure it looks like what I expect. Next up, let's define a convolutional autoencoder. Here's a diagram of what our network is going to look like. This is essentially going from input to output. And the diagram is really turned on its head from what you've seen before, so that the input is at the bottom and the output at the top. So each of these horizontal bars represents a layer in this autoencoder, and the width of the bar indicates how large in the x and y dimension this layer is. So we're starting with an original image, and that's just 28 by 28 by 1. So this is our input layer, and then we have a convolutional layer that increases the depth to 16. So we're left with a convolutional layer that has dimensions 28 by 28 by 16. This layer is not changing the width or the height, but we're changing the depth from 1 to 16. Next, there's a max pooling layer. Our typical max pooling layer with a stride and kernel size of 2 will downsample the input such that the x and y dimensions are reduced by a factor of 2. So in this case, we're going from 28 by 28 to 14 by 14, and the depth stays the same. Along these same lines, we have another convolutional layer that's 14 by 14 by 4. In this case, we're reducing the depth from 16 to 4 in the interest of making a better compressed representation. Finally, one more max pooling layer, which brings us to a compressed representation that's 7 by 7 by 4 in dimension. This representation contains 196 values total, which is just 25% the size of our initial input, a pretty good size reduction, though you could add another layer and go even smaller if you want. So this completes the encoder part, and then we proceed to the decoder. The decoder's main job is to go from the 7 by 7 by 4 compressed representation back to the size of a reconstructed output image. Our goal is to get the reconstruction and the original image as close as possible. There are basically 2 ways to do this, using what are called transpose convolutional layers, or upsampling with some kind of scaling and interpolation technique, and I'll show you examples of both approaches. So first we're going to try transpose convolutional layers. With transpose convolution, there's a kernel in this layer that's looking at the layer below, and using a larger stride to multiply existing pixel values by some weights and increase the spatial size of the output. In this case, we'll be using transpose convolutions with a kernel size and a stride of 2, so that they double the x and y dimensions of the input that they see. You can kind of think of them as doing both a convolution and unpooling operation at once. You can read more about this behavior here, and in fact PyTorch has some pretty good documentation on conv transpose 2D. If we look at the documentation, we can see that we can define a transpose convolutional layer in the same way that we define convolutional layers. It takes in a number of in channels, out channels, and a kernel size. We'll also have to be careful to define the stride. Okay, so following our diagram, I want you to complete the class conv autoencoder. I've left most of this for you to fill in, but I have shown you how to define a transpose convolutional layer. This particular layer sees 4 inputs and produces 16 outputs. It also has a kernel size of 2 and a stride of 2, so it will upsample the spatial dimensions of anything it sees by a factor of 2. Later, when we get to training, you'll see the same loss and optimization functions as in the simple autoencoder case. Now this model has more parameters, so I'd advise training for fewer epochs at first, especially if you're just trying to see how the loss decreases over time. Then, when you think you have a good model, you should train it for around 20 or 30 epochs at least, and then you can test it out on our usual test data. Next, if you want to check your work or see a potential solution to this task, you're welcome to check out my solution video. Alright, so we wanted to make a convolutional autoencoder with an encoder made of convolutional and max pooling layers, and a decoder made of only transposed convolutional layers. And here's my solution. I've split up the encoder and decoder portion of the code. In the init function, for my encoder, I've defined 2 convolutional layers. The first sees a grayscale image with depth 1 and produces 16 feature maps. Here I'm using a 3x3 kernel, and to keep the outputs the same XY size as the inputs, I'm padding it with 1 pixel. Then the next layer does something similar, only it decreases the depth from 16 to 4 feature maps. Finally, I've defined a max pooling layer with a stride and kernel size of 2, which I'll place after each of my convolutional layers to reduce the spatial size of the output. Then I have the decoder. The decoder's job is to essentially undo the learned downsampling that happened in the encoder portion of this model. If we look back at our diagram, we can see that we want each transposed convolutional layer to upsample an image and unpool it, as well as modify the depth of our output, going from a compressed depth of 4 to 16, then back to 1. This brings us to the size of a reconstructed image, 28 by 28 by 1. And here I do just that. I move from a depth of 4 to 16 to 16 to 1, each time increasing the spatial dimension by 2 by having a kernel and stride size of 2. Now with this last layer, we'll be able to actually train this model by comparing the original input images and their reconstructions. Okay, then I'm just putting everything together in the forward function. I have my series of convolutional and pooling layers in the encoder portion, and I have my transposed convolutional layers in the decoder portion. You'll notice that I'm applying a ReLU activation function to every single hidden layer, with the exception of the output layer. To this layer, I've applied a sigmoid activation function, which scales the output so that I'll have grayscale pixel values in a range from 0 to 1. Next comes training. Since this is a regression task, which compares pixel quantities rather than class probabilities, I'm using a mean squared error loss that's better suited for comparing quantities. And I'm using the same atom optimizer as before. Then, in my training loop, I'm iterating through my training set of images. The MNIST data contains images and their correct class labels, but I don't care about labels in this case. Instead, I'm just putting the images into the model, which produces some reconstructed output images. Then, my loss compares these reconstructed images with the originals. Ideally, these will be almost indistinguishable. I recorded the training loss after each of my 30 epochs, and it decreased from about 0.55 to about 0.16. Then I viewed the results. Here I'm displaying 10 original images in the top row and their reconstructions in the bottom. And a lot of these reconstructions look really good. This model no longer has the blurriness that our simple linear model had. Instead, though, it does give us some kind of blocky artifacts, and it seems to struggle with curved areas. These blocky checkerboard-like patterns could be due to how transposed convolutional layers tend to overlap and produce a grid-like pattern. So I've also included a notebook with an alternative solution, which I'll show you next. Alright, in this notebook, I'm reading in my data again, and I'm starting out with the same convolutional structure. The encoder is made of a series of convolutional and max pooling layers, and our compressed representation is the same, a 7x7x4 output. What's changing is how I make this decoder portion. Instead of just including transposed convolutional layers, I'm combining nearest neighbor interpolation with normal convolutional layers. And nearest neighbor interpolation is just an upsampling method that copies over pixel values from, say, a 2x2 area to a 4x4 area. So after the 7x7x4 compressed representation is created by the encoder, I upsample that by a factor of 2 to get a 14x14x4 tensor. Then I put it through a convolutional layer to increase the depth to 16. Then one more upsample to get to the size I want, 28 by 28. And one more convolutional layer to get us to the size of a reconstructed output, 28 by 28 by 1. So basically, I replaced one transpose convolutional layer with an upsample function and a convolutional layer. The convolutional layer changes the depth of an input and acts as a series of image filters that can learn to cleverly transform the layers in between upsampling functions. Okay, so if I go down to my autoencoder code, I can see my two convolutional layers and pooling layer that define my encoder. Then my decoder layers are just the two convolutional layers that go from 4 to 16 to 16 to 1 in depth. The biggest change is in the forward function, where I have my encoder layers, and the decoder looks a little different. After the compressed representation, I call f.upsample. In some versions of PyTorch, this may be called interpolate, but it's the same function. I pass in my input x, and I scale it up by a factor of 2, using nearest neighbor interpolation. Then I pass this upsampled x into a convolutional layer. Again, for each hidden layer, I'm applying a ReLU activation function and a sigmoid to the very last output. Okay, so I defined this model, and I trained it for the exact same length as I did before. Here you can see the loss starts out a little lower at about 0.32 and decreases to a lower value as well. And here are the original and then reconstructed images underneath. And I think these look really good. These images are a bit smoother and they look really close to the original version. Now, both the transpose convolutional layers and this upsampling approach work for this task, and I'd like you to keep in mind that many tasks have multiple solutions. In fact, the best deep learning researchers and learners have investigated a number of options for solutions, different architectures that might offer certain benefits or trade-offs. And next, I want to give you a free-form challenge for you to try out a solution of your own design. Knowing what you know now about convolutional autoencoders, I'm going to challenge you to make a denoising autoencoder. As we know, autoencoders don't excel at compressing images, but they can learn pretty well how to denoise them, given a noisy and non-noisy set to learn from. The idea is this: given an input set of noisy data and a target set of data that's the non-noisy image data, the encoder can learn to distill important information from the noisy image, and the decoder can learn to produce a non-noisy reconstruction. After this is trained, this whole autoencoder should be able to denoise new test data. So in this notebook, I've given you the usual code to load in and visualize your MNIST data. Then later, I'm going to add this kind of speckle noise to this data. This way, you'll have a set of noisy images for an encoder to see and a set of target images that are without noise. It will be up to you to define a conv denoiser architecture. The architecture will be very similar to the ones we've gone through, only denoising is a bit of a harder problem. What I'd encourage you to do is actually increase the depths of our convolutional layers, so something like starting with a depth of 32 for the depths instead of 16. I'd also say that it could be useful to add one more convolutional layer to both the encoder and decoder. Basically, more and deeper layers will give you more parameters to recognize patterns with. Now, I've given you our usual training loop, but I've changed some things so that I'm adding some noise to our images. In here, I'm reading in our images from the training set, and I'm adding some noise, creating some noisy images. Then I pass these noisy images to our model as input, so this is what the encoder will see. But my loss is going to be comparing our reconstructed images with our originals, our target non-noisy images. Then you can check out the reconstructions as well. This denoising application is really pretty interesting because the autoencoder is having to learn something about the content of quite a noisy image, and then it learns how to transform it into a non-noisy version. Now, in this case, I've provided a solution notebook, but I'm not going to walk you through the answer. You're encouraged to try this out and explore on your own before you look at the existing code. I'd even encourage you to try to test out the limits of just how much noise you can add to these images. You could imagine using a similar approach for doing something like denoising audio signals and removing static from sound. Go ahead and experiment with this code, and when you're ready, move on to the next lesson.
So far in the software engineering section, you practice writing clean and maintainable code. Then in object-oriented programming, you built a Python package. In this final software engineering lesson, you're going to use your new skills to build an actual application, a data dashboard. A data dashboard is a collection of visualizations that help you track key metrics and trends. Creating dashboards is a common task for both data analysts and data scientists. Making a web dashboard from scratch, however, requires a wide set of tools, including HTML, JavaScript, CSS, Linux, some object-oriented programming, and for this particular dashboard that you're going to make, Python. At Udacity, we have an entire Nanodegree dedicated to learning these skills called Full Stack Web Developer. Because making a web app is its own career path that takes months to learn, this lesson will give a relatively quick and high-level overview of web development. We'll also provide you with a template to make building and deploying the application easier. You'll even be able to reuse this template to build your own data dashboards outside of this course. By the end of the lesson, you'll have deployed a public-facing web app accessible via the internet. Throughout the lesson, you'll be introduced to each part of the application piece by piece. You'll start with the basic building blocks of a web app: HTML, CSS, and JavaScript. Then you'll practice using two libraries that make web development easier. The first library is called Bootstrap, and you can use it to quickly build the design and layout of your app. The second library is called Plotly, which uses JavaScript to make visualizations. At this point in the lesson, you'll have a functioning web page that includes data visualizations. However, the web page will only be on your local computer, not the internet. The last part of the lesson focuses on getting the application ready for the internet. You'll work with a Python web framework called Flask, which takes care of the application logic happening behind the scenes. And finally, you'll put all of these tools together and deploy your web app to a website that anyone can access. In the major web browsers like Firefox or Chrome, you can actually see the messages and files getting transmitted between you and the server. In Chrome, go to the View menu, then select Developer and Developer Tools. That's what I have open here. Then click up here on the Network tab and visit a website. I'm going to visit the Udacity homepage. So these are all the files that your browser requests when going to a web page. If you click on a file, for example, here, you'll see request method get, which is your browser saying, get me this file or information from the server. The reason I'm showing you all of this is so that you can physically see how the web actually works and what is going on. As you practice coding with Flask, it can be helpful to understand the basics of how the internet works between a browser and a server. Before going into the details of how to build the application, let's talk about the different components of a web app. A web app essentially has two parts: the front end, which is what we see when navigating a website, and the back end, which are all the processes and data working behind the scenes. When you open a web page, you're looking at the front end. You can think of the page as having three parts. The first part is content, which includes text, images, videos, and forms. You control this content with a language called HTML. The second part is the design, like the colors, font styles, and layout, all of which you manage using another language called CSS. And the third part includes all of the animations and interactivities such as fade-ins, slideshows, and pop-ups. The code to make this happen is written in a language called JavaScript. The back end is responsible for running the web app, but you don't actually see the back end when looking at a web page. The back end includes the server where the website files are stored. When you type in a web address and hit enter, you're actually asking the server to send you the HTML, CSS, and JavaScript files that make up the front end of your web app. A web app might also have a database as part of the back end. The code that controls the server and communicates with the database is all part of the back end. You can code the back end in a variety of languages, including PHP, Java, and Ruby. Because you're already familiar with Python, we're going to use Python for this lesson. In the next part of the lesson, you'll code the front end. You'll start working with the three languages needed to code a web page: HTML, CSS, and JavaScript. As a reminder, HTML controls the content, CSS is in charge of style, and JavaScript takes care of interactivity. I want to emphasize that this part of the lesson will be a brief overview of these three languages. In reality, it can take a few weeks, if not months, to really learn them. You could code the front end of a data dashboard, including visualizations, using only these three languages and nothing else. However, you are an intelligent, busy data scientist, and there's no reason to do everything from scratch. Once you've seen the basics of how to build a web page, I'll introduce you to a front-end framework called Bootstrap. Bootstrap helps you make professional-looking websites rather quickly because a lot of the CSS is taken care of for you. Finally, you'll work with a JavaScript library called Plotly. Plotly makes adding data visualizations relatively easy, although it does take some time to get used to the syntax. With all of this in mind, let's start building the front end. Before you start coding, I wanted to show you what you're going to build in this lesson. This is a web app that uses data from the World Bank and outputs a few visualizations. Let me show you what it looks like. I've used a few libraries to help me put this together, including Bootstrap to organize the front end and Plotly for the visualizations. In the lesson, you'll build this up one piece at a time, and then afterwards you can customize this to make it your own. Let's start with the first piece of building this, HTML. Here on the left is a document with HTML code, and on the right, this is what the HTML looks like when opening the file in a browser like Chrome, Firefox, or Safari. I'm actually using a workspace in the classroom where I can write HTML and then instantly see what it looks like. You'll be using this same workspace to practice writing code. At the end of this video, I'll show you how to open this file locally on your computer as well. HTML is organized into elements that divide up the document into sections. Think of an element as a generic idea, such as a paragraph with all of its text. All of these brackets are called tags. So if I say the head element, I'm referring to lines 4, 5, and 6 of the code containing all of the information about the head. If I say the head tag, I'm referring to the actual HTML syntax with the word surrounded by brackets. At the top, the first tag declares the document type. It says that this is an HTML document. Then comes the HTML element where all the HTML code is written. Notice how that HTML element has two parts, a tag that has a left angle bracket, then HTML, and then a right angle bracket, and another tag that looks similar but also has a slash. These are called opening and closing tags respectively. In this case, the opening tag tells a browser that HTML code is about to start, and the closing tag tells the browser that the HTML code ends. Everything in between the start and end HTML tag is HTML code. Both head and body have opening tags as well as closing tags. Everything inside the head tag belongs to the head element, and everything inside the body tag belongs to the body element. The head element contains a title with opening and closing tags. The title of the page usually shows up in a browser tab, and the body element contains the bulk of the HTML code that you actually see when looking at a web page. You put your website content inside of body elements. There are all types of elements that can go inside the body of an HTML document, including header elements, link elements, paragraph elements, and image elements. These elements define your website content. In this case, I have a header followed by a link, then a paragraph, and finally an image. Notice how all of these elements have opening tags and closing tags, except for the image element. Image elements don't require closing tags, so image elements are an exception to the rule. I formatted the document with tabs so that it's easy to see the hierarchical structure of an HTML document, and I recommend that you do the same. However, you do not have to format your HTML at all. The nesting tag structure determines how HTML gets rendered in a browser, not the formatting of the HTML document itself. I could remove the tabs, and I'll do that now, and the document would render exactly the same way. But I'm going to put it back as the way it was. There are many more HTML elements than the ones in this example. These include elements for making lists, forms, and tables. I'll provide a link below the video where you can learn more. It's common to think of HTML as a tree structure. The first node is an HTML tag, and then the head and body tags split off from there. The head tag can contain a title tag, as well as a few other tags like meta and style tags, which we haven't discussed yet. The body will contain headers, paragraphs, images, links, etc. And within some of those tags, you can actually have other tags. For example, in a paragraph tag, you can have an image as well as a link. Now, take a moment to practice writing your own HTML document. You can use a workspace in the next part of the classroom. The workspace automatically saves your work as you type and also refreshes the rendering of your code. I'll add an extra link so you can see what I mean. Here I'm adding a link to the Udacity website, and you can see on the right-hand side that it renders as I type. As an alternative, you can open any text editor to write your code and then save the document with the .html extension, just like here where it says index.html. Here's an example. On my desktop, I have a folder, and inside the folder, I have the index.html and the photo.jpg files. If I open index.html with the text editor, you can see the HTML code, and I could modify it here. If I open index.html in the Chrome web browser, I can see the rendered result. Now it's your turn to write some HTML code. Let's talk about how to structure and organize HTML code. As you've already experienced yourself, each new HTML tag gets rendered one after the other. So for example, if I use a paragraph tag and then another paragraph tag, they get rendered from top to bottom. I'm going to add a couple more links and some paragraphs to this document. So you can see the links get rendered one after another, and the paragraphs get rendered one after another in the order I've written the code. There's a tag called div, short for division, that is specifically used for grouping large chunks of related content. This tag lets you pick out specific parts of your document for adding CSS styles or interactions using JavaScript. I'm going to add div tags to create a separate link section and another section around the entire bottom paragraphs. Let me expand this so you can see it better. All the div tags are doing are separating the content into separate groups. There's another tag called span that some people confuse with the div tag. A span element separates off a small piece of content, such as in the middle of a paragraph. For example, if you wanted to change the color of one word instead of an entire paragraph, you could use a span tag. I'm going to add one here so you can see what it looks like. Notice that the div and the span tag aren't actually changing anything. They're just ways to separate out HTML code. When you start styling your web page, the div and span tags will make more sense. What if you wanted to make the first paragraph bold with a larger font and then the last two paragraphs with an italic font? To change the font and font style, you'll need CSS, but we're not quite ready yet to add CSS styling. You'll need to differentiate between the first paragraph and the other paragraphs. HTML has attributes specifically for differentiating elements from each other, the ID attribute and the class attribute. IDs uniquely identify a piece of content. For example, I can use an ID in the first paragraph to add ID equals p top. As you'll see later in this lesson, you can now pick out the p top paragraph and add a bold font just to that paragraph. An ID is a unique identifier that you should only use once per HTML page. You can name IDs whatever you want, but you should only use the name once. And a tag should only have one ID, so the paragraph tag can only have that p top ID. I'll add a few other IDs to reinforce this. So for example, the middle paragraph can be p middle, and the bottom p bottom. I'm going to add IDs to the div tags as well, like ID equals link section and ID equals paragraph section. Like I said, IDs can go in any tag. Each element can have one ID, and each ID name should be unique. The idea is that you're separating out the content for different CSS styling. Classes, on the other hand, group multiple pieces of content together. So, for example, I could add a class to these two bottom paragraphs called italic text, implying that I'm going to style these two paragraphs with an italic font. You can name a class whatever you want, and you can use a class name multiple times in an HTML document in order to group pieces of content together. An element can even have more than one class. Like I could add another class called green text, implying I'm going to style this last paragraph green. I could add the same green text class to a link. Adding IDs and classes will give you more control over your website's CSS styling. They help you add style to your pages in a logical, organized way. In the next exercise, you'll get practice adding div and span tags, as well as using classes and IDs. I'm at the Google News website. The Google News website has a nice layout, doesn't it? For example, if I shrink the browser, everything adapts to a smaller screen. All of the content is divided into clear sections. This is all done with CSS styling. So I'm going to show you a little trick where you can actually remove the CSS for a website. I'm going to open something called Developer Tools, which lets you see the code that makes up a website. I'm in Chrome, and if you go to the menu bar at the top, it's under View, then Developer, and finally Developer Tools. So here in this box is the HTML for this website. I'm going to delete the head tag, which among other things contains code for the CSS styling. Now all we're left with is the HTML of the website. If I scroll down, you can see that this looks a lot like the HTML code that you've been writing. It's just HTML without any style attached to it. I wanted to show you this because behind every web page, no matter how good the page looks, it's really just HTML holding all of the content. The styling, like the column layout, colors, fonts, all of these are specified using a language called CSS. CSS stands for Cascading Style Sheets. You write CSS code to specify what each element on your page should look like. I'm going to give you a quick intro to CSS, although to build the actual web app at the end of this lesson, you'll use a front-end library that does the CSS styling for you. Here's the web page that we've been working on. There are essentially two different ways to write CSS, inline CSS and CSS written in a style sheet. With inline CSS, you specify the style inside a tag using the style attribute. For example, to change the first paragraph to a bold font, I would write style equals font weight bold. So you can see the syntax here. I say what I want to change, in this case the font weight, how I want to change it. I want it to be bold, and then I need to separate those two with a colon, and then finally I end things with a semicolon. I can add other things here, like let's say color red. So I'm adding another rule to this paragraph, and everything turns red. You can do all kinds of things to change the styling, and I'll put some references below the video so that you can see all the different things you can do. I'm going to start adding some more style rules. For example, here in the body, I'm going to say margin left 20 pixels, margin right 20 pixels. Let's see what that does. Okay, so if you've noticed, it actually squeezed in my content a little bit so it wasn't flush against the left and right side. Let's go down to the image tag here, and we're gonna make the image a little bit smaller. Okay, I'm gonna go up to the link here, and I'm going to say style text decoration none. And you can see that it took away this underline that was underneath the link here. So you can add all kinds of different styles. For example, what else did I have here? This green text here, I could style here and say color green. So you can do all sorts of things. The problem, however, with writing CSS this way is that you have to specify the CSS for each individual tag. And that's kind of tedious. It also doesn't totally take advantage of what CSS can do, which is essentially to separate the content in HTML and make the styling totally separate. I'm going to start over again from scratch with the original HTML that didn't have any styling. Okay, so an alternative way to putting the style is here with the style sheet. So I go up into the head tag and I make this new element called style. Now I can add CSS rules into the style sheet so that it's actually separated from the HTML content. The syntax in a style sheet is to first specify the element type, tag, or class that you want to style, and then you write out a rule for the style. For example, if I want to style only the paragraph with the ptop ID, I specify the ptop ID using the £, write out ptop, open squiggly bracket, close squiggly bracket, and then I write my style rule inside. In this case, I'm going to say font, weight, bold. And you can see now that the first top paragraph has a font weight of bold. Let's add some more rules just so you can see what it looks like. Okay, what if I want to style the body tag? All I have to do here is write body to represent the body tag, and then have my open and close squiggly brackets, and then I can specify whatever I want, like margin left, 20 pixels, margin right, 20 pixels. And again, that's squeezing all of the text, all of the content, so that it's not flush with the sides anymore. I can add a border, maybe add some padding so that everything isn't stuck right on the border. So you can see I'm starting to style all of this. I want to style the image so that it's not so large. Take away those underlines from the links. And then if you go down to the HTML, remember I had this class called green text. So to add style to a class, I use this dot syntax, and then the name of the class. And now I'm going to change the color to green. So you can start to see the advantages of using IDs in classes. For example, with the ID on the first paragraph, I was able to just make this first paragraph bold. And with the green text class, I could make just this part green and this part green, but just using one style rule. Writing the style this way is called an internal style sheet because it's still internal to the HTML document. To make the code even cleaner and modular, you can put the CSS into a separate file. Now, the last step is to link to the style sheet in the HTML document. You do that with the link tag. And here in the href attribute, you put the name of the file. Close everything, and now you've got your CSS styling. So now the content in the HTML document and the styling in the CSS document are completely separate. I want to mention that I know I'm showing you a lot of things at a very rapid pace, but the goal is to become proficient, not necessarily an expert. Soon, I'll present a few tools that make web development somewhat easier so that you don't have to know all of these CSS rules. But I'm giving you an introduction so that you understand what's happening behind the scenes. Next up, you'll practice writing CSS, and then we'll move on to JavaScript. Just like how Python has libraries that make Python development easier, there are libraries built on top of CSS and JavaScript that make web development much easier. From this point on in the lesson, you'll only need to write HTML, Python, and a little bit of JavaScript. But behind the scenes, libraries will be taking care of the CSS and most of the JavaScript for you. First, let me remind you of the goal. You want to get a front end that looks like this. In this video, I'm going to build up this front end for you so you can see how I did it. And then you can practice doing it yourself in the exercise. For now, in this video, I'm just going to use images for the visualizations rather than the HTML visualizations that you're going to make later in the lesson. To make this front end, I use the Bootstrap library. This is the Bootstrap homepage. The Bootstrap documentation is pretty good. There are many examples, and each example comes with code. Oftentimes, you can just copy and paste the example code from their website and then change the content to fit your needs. That's exactly what I'm going to do here. Going back to their home page, I'm going to click on their Get Started button. So here on this page, there's actually a template that you can copy and paste as a starter. That's exactly what I'm going to do here. I'm going to copy and paste their starter code template. So far it doesn't look like much. It just says hello world. But let me explain what all of this code is. First of all, you have a doc type tag like what we discussed before. And then there's the HTML tag, and it specifies in this case that the language of the website is English. In the head tag, we've got things like these meta tags and then links. So the first meta tag is just notifying the browser that the character set is UTF-8, and then the viewport meta tag is for shrinking and expanding the content for web versus mobile. Then there's a link to the Bootstrap CSS library. Then we have the title Hello World. Then the body starts where the bulk of your HTML content goes. And then we have these links to all of these JavaScript scripts. And these are linking to jQuery essentially. Bootstrap uses jQuery to do some of its animations. The essential trick to using Bootstrap is that the screen is divided into these invisible rows and 12 columns. You can have as many rows as you want. Behind the scenes, Bootstrap is going to use CSS to make the layout happen for you, and all you have to do is specify IDs and classes. All of this is spelled out pretty explicitly in the documentation for Bootstrap. I'm going to show you a quick example of what all of these rows and columns look like. So I'm going to erase this hello world here, and then I'm going to add a div and give it the class of row, and then close that div. Okay, inside of this row, I'm going to make a class called column-1 or col-1, and then we close this tag. I'm just going to write here C1. So we have this column here, C1, right? I'm going to just copy and paste this so that there are 12 of them. So hopefully this makes it clear that this row is divided into 12 evenly spaced sections. Now I'm going to make another row, and I'm just going to copy all of this again. And so now I have a second row with 12 evenly spaced columns. So you have these 12 divisions to work with, but you don't need to use all 12. For example, I can say this first one is just 4 across, and then the next one is 8. And then I'm going to erase all the rest of the ones. So now you have a row that has one column that has 4 spaces, and then one column that has 8 spaces. So for this next one, just to give another example, I'm going to give this one 7, and the next one 5. And it's still, everything adds up to 12 divisions, but you can see here on the right that the first part has 7 divisions and the second part has 5 divisions. So you can use these rows and columns to divide up the screen in any way you want to. If you go back to my web app, you can see perhaps how I've divided this up. So this section on the bottom is just one big row, and then I've divided that row into a column of width 1 and another column here of width 11. And then I've made another row within a column that has 2 columns, and then I've made another row that also has 2 columns. And I'm going to show you how this works with code as well. But let's build this up starting from the top with the navigation bar and then working our way down. I'm here back at the Bootstrap homepage. I'm going to click on documentation, and then here I'm just going to search for navbar. Okay, so on this page there are a bunch of examples of how to make a navbar. And so all I did was I saw this one, I liked it, I copied this code, and then I paste it into my HTML. Okay, I'm going to erase all of this stuff on the bottom just so that it's easier to see what we're doing. And I'm going to change the website title to Data Dashboard. Okay, so this nav bar is pretty similar to the one that I have in my web app, but the colors are a little different, the links are a little different. So all I have to do is just change those things. So to change the color, for example, this says navbar light here as a class, and I'm going to say navbar dark. This BG light stands for background. Background light, I'm going to change to background dark. So this is already looking more like the web page I have. Now, how did I know to change these classes? Well, it's all in the documentation. So it shows you that you can change the navbar color and you can change the navbar shading using these different classes. Here I put World Bank Data Dashboard, and then we also need to change these links here. So the links are actually here in this HTML list, and I'm going to say this first one is a link to the Udacity website, and so I need to change the H reference here to udacity.com. And then it has this span element in here that I don't actually want, so I'm going to delete that. Okay, so we have this first one. Did you notice as well in this list here, it says class nav item active, and I don't particularly want that. And that got rid of the white highlighting that it had. Okay, and now I wanted to link to the World Bank data. Okay, so that showed up. And now this pricing and disabled we're not actually using, so we can delete them. Here we delete pricing. Here we delete disabled. And this is looking pretty good. I'm going to expand this a little bit because that's the mobile view and this is the desktop view. So actually there is a little bit of a difference. This was right aligned on my app and here it's actually left aligned. So how can we change that? If you look it up in the documentation, you'll find that if you add a margin with margin left auto, you can actually change that. So I'm going to add that into my code. And you can see that it changed the alignment for me. And again, so the great thing about this library is that you just have to change the classes and IDs in all of your tags, and the CSS just gets taken care of for you. So let's go back to the app. Like I said before, this bottom part here is made by nesting columns and rows together. So I personally like to first write out the structure with all of the rows and columns and then fill those in. You don't have to do it. You can build it up little by little, but here's how I do it. So down here, I know that I want everything to be inside of a row. And then inside that row, I have a column of width 1, and I have another column of width 11 to fill out the rest of the space. Okay, looking back at the dashboard, this is fine. We'll be able to do this now. This part in here actually has a row here and then another row, and each of these rows has 2 columns. So let's put that in. Gonna add another row and another row. And then within that row, I'm gonna put 2 columns, each of width 6. And then I'm just gonna copy and paste this. So that's essentially the skeleton of the bottom part. So now it's just a matter of filling things in. So for this left-hand column, I am going to add links to LinkedIn and GitHub. So here in href is where, say, you would put a link to your LinkedIn profile. And then in the assets folder that you can see here on the left, I have put in a bunch of images, and I'm going to put those images into the web page. Specify an alt tag and close the link. And now let's put in GitHub, and this is where you could put in the link to your GitHub profile and the href attribute. Okay, so these images are pretty large and they're also touching each other, which is not exactly how I had it in the web app. So in the documentation, you'll see that there's a class called ImageFluid that will actually make these images shrink and expand in a nicer way. So I'm going to add that class here. Okay, and now you can see that these images grow and shrink with the size of the web page. I'm also going to add a couple of other things. For example, I put a border here on the right-hand side, which I can add with the border right class. It shows up right here. When the website's a little larger, you'll be able to see it better in a second. And I'm also just going to add an extra div here on top. And I'm going to add a class called MT-3. MT stands for margin top, and the -3 means that I want to add a margin of 3. So let's see what that looks like. Okay, it's getting better. So I also added a little bit of space between these images, and I added a little bit of margin to the left of these images, so let's do that. Here I added a little bit of top margin to this image of the GitHub icon, and I'm going to add a little bit of left margin. And then I'm going to go into the LinkedIn class here and also add in a little bit of left margin. Okay, so this is looking a lot better, right? So let's look at the web app one more time. Okay, so we have these headers up here on top, the World Bank data dashboard, top 10 world economies land use, and then we have these 4 visualizations. So let's finish that up. This is in the column 11 class. So here at the very top, I am going to add a H2 header, and I'm going to call it World Bank Data Dashboard. And then I had an H4 header below it, and I said top 10 world economies land use, and then close that tag. Now this looks a little bit different because I made this a gray color. And again, in the documentation, it talks about the classes you need to use to change the color. In this case, the class I used was called text muted. Okay, we're looking good. We're getting close. Now it's just a matter of filling in these images with the visualizations into each section. So here I specify that the image should be fluid, and then I specify the actual image. Let's see how that looks. Okay, now I'm just going to copy and paste this and put it into the next column and change the name of the file to plot2. And then I'm going to add the next image and call that plot3. Now I'm just going to copy in the code for the final image and call that plot4. And that is it. Now we have something that looks pretty similar to the web app up here. And that's how I built the front end for this web app. The only thing left is to put in actual HTML, JavaScript visualizations rather than just using images. And you're going to do that with the Plotly library. But before getting into the Plotly library, there's an exercise for you to practice using Bootstrap. JavaScript is the language that makes websites interactive. If you've ever been on a website that automatically updates content, JavaScript was doing that. Anything like a fade-in or a pop-up, those are done with JavaScript. To build the data dashboard, you won't need to actually write any JavaScript. But both the Bootstrap library that you'll use for CSS and the Plotly library that you'll use for making charts use JavaScript. So this will give you an idea of how these libraries actually work. Here's a basic toy example of JavaScript. In lines 8 through 12 of the code, I've written a function that changes the header text when I click on the image. Let's see how it works. So I go onto the page, I click the image, and you'll notice up here that the h1 tag text changed. Here are a few things of note about this code. First, the JavaScript code goes between script tags. Notice as well that I added an onClick attribute to the image tag and specified the function name. That's down here in line 28. Also, the JavaScript syntax, to me at least, is a bit funny looking. JavaScript has a relatively complex syntax when it comes to making websites interactive. In this case, I'm saying, look at the HTML document, get all the h1 elements, give me the first h1 tag, and then change its HTML. The actual onClick functionality happens because, like I showed before, I put an onClick attribute in the image tag. Thankfully, there are libraries that make working with JavaScript and front-end development easier. Here, I'll show you one library called jQuery that makes JavaScript much easier to use. First, you'll need to link to the jQuery library either by downloading the file or pointing to a web address containing the library. You can download the jQuery file from the jQuery website, or you can use a link that contains the file. For example, Google has the jQuery library on the web that you can link to. I'm going to do that. So I'm going to erase the JavaScript code that I've already written, and I'm going to link to the jQuery library. Now I'm going to make a new scripts tag and a closing tag, and then write some jQuery code here in between. This is saying, wait for the document to get ready, In other words, waiting for the document to load. Then grab the image tag, put an onClick function, and finally change the h1 tag text. Then I just need to close all of my brackets and parentheses. And you can see it works. When I click on the image, the h1 tag changes. Also, just like CSS, I can either include the code in the HTML file using a script tag, or alternatively, I can put the JavaScript into a separate file and link to that file. I'm going to do that now. So I'm going to just create a new file. Let's call it interaction.js, where JS is for JavaScript. Now I'm going to cut this JavaScript code and put it into my interaction.js file. And then here in the scripts tag, I need to specify the source, which in this case is just this interaction.js file, which is in the same folder as the HTML document. And notice that the jQuery code still works. So that's essentially JavaScript and what you can do with JavaScript. Before you move on to the JavaScript exercises, I just wanted to give you 2 more examples of some jQuery code. So currently, this document has the same code as before, where if you click on the image, the text in the h1 tag will change. Okay, so what else can we add? jQuery gives you a lot of options. So I'm going to add 2 things. One, I'm going to add a fade in when the page loads. And just as another example, I'm going to have the image fade out when I click on the h1 tag at the top. So let me code that for you. So like before, you have to get the document and wait for it to be ready. And now I want to add something to the body tag. So I have to select the body tag. And now I'm going to say hide the body tag. So it's going to hide all of the content on load. And then I want to fade in slowly. Notice as well, here I've used double quotes. Here I've used single quotes. It actually doesn't matter, but I should be consistent about it and either do double quotes or single quotes. Now I'm just going to close all of our brackets and parentheses. And do you notice now when the page loads, it has a slow fade in. Okay, and now let's add the extra click functionality where clicking on the H1 title at the top will fade out the image at the bottom. So again, you wait for the document to load and be ready. And now we want to add a click function to the H1 tag. And then we want to take the image and fade it out slowly. And then we close all our brackets again. Let's see if it worked. And there it goes. So the jQuery documentation is pretty extensive. And again, the libraries we're going to use are actually going to take care of the jQuery for you. But I at least wanted you to understand what was going on underneath the hood. So use the information in this video to help you out with the jQuery exercise coming up next. There are quite a few choices when it comes to choosing a JavaScript chart library. I chose Plotly for this lesson because it has both a JavaScript library and also a Python version. Since the backend of this web app will be in Python, you can actually use the Plotly Python library in your backend. Plotly, just so you know, is actually a company, but their charting libraries are open sourced. Since you haven't made the backend yet, for this part of the lesson, I'm going to show you the JavaScript version of the Plotly library. The syntax and ideas behind the Python and JavaScript version are quite similar. So when you end up using the Python Plotly library later in the lesson, it won't be too different. To make a plot, all you need to do is create a div element with a specific ID. So you can see here, I have a basic HTML document, and all I've done is linked to the JavaScript source file of the Plotly library. And then I've created a div down here with ID plot1 and also linked to a script called plot1.js where I'm going to write the JavaScript code to make the plot appear. I'm going to put the Plotly code into this file plot1.js. So essentially all you need to do is have some data and then tell Plotly what kind of plot you want to make. So in this case, I'm going to put some data into a couple of JavaScript lists. So this is just regular JavaScript code. I'm creating some data that has a year as one variable, and then arable land is another variable. And this is real data that I've taken from the World Bank website. Okay, and now comes the Plotly code. So I'm going to make a variable that I'm going to call a trace. And a trace is essentially a visualization, or you can think of it as a part of a visualization, like a single line or a set of points. You'll see what I mean in a second. So I'm going to specify the x variable as year, the y variable as arable land, and then I'm going to say mode lines because I want to make a line chart. And then I'm going to specify the type as a scatter plot. So this is actually essentially a dictionary that I'm making in JavaScript where I'm specifying all the parts of this visualization. So I'm going to make another list where I'm going to keep this trace and call it data. And then the last part, I just say plotly.newPlot. So I'm calling the Plotly library newPlot method. And then I say plot1 because that was the ID we used in the HTML. Insert the data, and it should work. And there we go. This is the plot I made. So this plot isn't perfect. It's missing a title, for example, and it's missing X and Y axis labels. So let's add that. I'm going to add another variable called layout. And this is going to be another dictionary with the information I want to put in, like the title. I'm going to put in this BR, which is actually HTML for a break in the line so that the title will render on two different lines. And now I'm going to specify some things about the x-axis. And this is going to be a dictionary within a dictionary because there are various options. So I'm going to say title year. I'm going to say actually that I want the tick to start at 1990. And I want the delta between the ticks to be 25. And now I'm going to specify some things about the y-axis, like the title. And then we're going to close this off. And now we're going to add layout as the third input to the newPlot method. Okay, so we made sure that the x-axis started at 1990 and that there were only 2 points, 1990 and then a delta of 25 to 2015. We added the year as the x-axis label, and then we added a y-axis label and a title. So you can see how using Plotly you can build out a chart little by little with more and more features. So let's make this visualization a little bit more complex. I have Brazil on here. I want to add Germany so that Brazil and Germany appear at the same time. So I'm going to change this variable and call it arable land 1. And then I'm going to make a country 1 variable and call it Brazil. Okay, and now I want arable land 1 as the y-axis. And I'm going to add this name here and say country 1. And that's going to be used for the legend. Okay, and now I am going to add some information about Germany. And now I need to create another trace 2, to make a line for Germany. And we're going to use the same year variable, arable land 2, specify the mode, specify the type. And now we're going to add trace 2 to the data list. And there we go. And just to give you some other ideas, you can change the mode, for example, and change it from lines to markers. And that just gives you points instead of a line. Or you could even say lines plus markers and have both of them. Okay, now let's add another plot. So all I have to do here is add another div, call it something else. We're going to call it plot2. And just for organization purposes, I'm going to put it into a different file. So let's create this new file called plot2. So in plot2, I'm going to make a bar chart to make something different. I'm just going to put the data in directly instead of using the extra variables. And again, the data is just a list of all the data points in order so that the X and Y match. And I'm going to say type is a bar chart because I want to do something different. Let's close this, create a layout. I'm going to say title, hectares, arable land per person, 2015. X-axis, let's give it a title. Y-axis, hectares per person as a title. And then we call the Plotly newPlot method. Make sure to specify the right name of the ID, put in the data, put in the layout, and we've got our second chart down here. So it's up to you to decide what kind of chart is best for your data, and you'll want to go to the Plotly website and see all of their examples so that you can make the kind of chart you're trying to make. They have a lot of examples on their website. And again, you can take the code, you can copy their example code, and then you can fill it in with your own data and change it any way you'd like. Okay, and the last thing I want to show you is putting together what you've made with the Bootstrap library and putting in these Plotly plots. So here I have the front end that you've been working with Bootstrap, and I put in a couple of extra things here. So way at the bottom, I added some extra script tags. One links to the Plotly JavaScript library, and then two other ones are linking to the Plotly code that I was just writing before. So they're linking to plot1.js and plot2.js. So the only thing left is to put the divs with the correct IDs in the spot where I want to put the visualizations. Scrolling back up here, I have this row and these two columns, right? So that is where I want my plots to show up. So I'm going to make a new div, and I'm going to say ID equals plot1, and then close the div. And I'm going to make another div and say ID equals plot2, and close the div. And let's see what we've got. Okay, so now we've combined the CSS Bootstrap front end with the JavaScript visualizations using Plotly. The one part that's still missing in terms of the front end is actually using data from, say, a CSV file or downloading data from the internet. But we'll get to that a little bit later in the lesson. So this is it essentially for the front end. There's one exercise left to do, and then you're going to start working on the back end. That's it for the front end. You should now have a web page with a few links and a couple of data visualizations. This is already something you could put in your portfolio because it shows off your data visualization skills. And if you haven't started a portfolio yet with your other Nanodegree projects, now's the perfect time. All of your files are currently in a directory in the classroom workspace or on your local computer. You should be able to open the HTML file in a local web browser and see the dashboard. Currently, if you wanted to share your dashboard with a coworker, you'd have to transfer all of these files to your coworker's computer. Then that person would have to open the HTML document locally, which is a whole lot of fuss just to show off your visualizations. It would be much nicer if your web app were on the internet. Then anyone could type a web address in a browser and see your work. But how do you get your dashboard onto the internet? For that, you'll need a backend. You're going to build a simple backend using a framework called Flask. For a data scientist, one of the biggest benefits of Flask is that the framework is written in Python. That means you can use scikit-learn, pandas, and NumPy in your backend code if you need to do any data wrangling or run machine learning algorithms. Once you've coded the backend, you'll be ready to deploy your application to a server. Deployment will be the last step to getting your application on the internet. Let's get started with building the backend and deploying the web app to a server. This is another type of Udacity workspace. It's an IDE, or Integrated Development Environment, which provides tools for writing software. It's got a file browser, a terminal, and a code editor. Here, I've set up a Flask app for you, and I'm going to give a tour of the different files. First, there's the worldbank.py file. This is the file you'll run in the terminal to start the web app. This file is importing something called app from the World Bank app folder. You'll see what this app is in a minute. When the application runs, it'll be on port 3001, as you can see here in the port attribute. What's inside this World Bank app folder? there's an init file, which means I've set this up like a Python package. And when the package is run, the init file gets run first. Here's the init file. First, I'm importing the Flask library, and then I create a variable called app, and finally import the routes file. It's a bit tricky to see how all of these lines of code work together relative to the file directory. If I'm in the workspace directory in the terminal, I start the app by running python worldbank.py. I'm going to open a terminal and run python worldbank.py. This init file is run and imports the app variable as well as the routes file. If you're not following the logic of all this, don't worry about it too much. You don't need to understand all of this to build the app itself. The actual code you'll need to change is in routes.py and the files in the templates folder. The routes.py and templates folders are where the magic happens. These are the files and folders you'll actually be working with. In routes.py, I'm importing this app variable at the top, and then I'm importing the render template method from the Flask library. Render template, as you'll see, is going to specify what HTML file should show up based on a web address. This first chunk of code says that if the user goes to the home page, like www.udacity.com or www.udacity.com/index, or whatever your web page is called, then the index.html file should render. The second example says if I go to the web page name and then type /project-1, then the project_1.html file should render. These HTML files are in the templates folder. So again, you specify the web address in @app.root, and then you specify the HTML file to serve in the render template method. The functions like index and project_1 functions can be named whatever you want. Your own computer can create a local backend server while you develop an app. So likewise, in the classroom, you can spin up a backend server to see how your web app renders. You just need to know what website to put into your browser. Actually, I already started the web app when I typed python worldbank.py. So I'm going to shut down the web app first by hitting Control-C. Okay, so first you need to know what website to put into your browser in order to see your website. For the classroom, what you'll have to do is type env and then the pipe grep work. The env command shows all the environmental variables of the workspace. What the env pipeline grep work command does is filter out the environmental variables for the ones that have work in the name of the variable. The web address is going to be this workspace ID followed by --3001, a dot, and then the workspace domain. I'll put instructions below the video as well. Now, when you execute the worldbank.py file, you'll start the server. I type python worldbank.py, and now it says the server is running on port 3001. And now, putting the correct web address in a browser, you can see the app. And here's the app. This is the index.html page. And now, if I put in project-1, I can see the project_1.html page. Going back to the workspace, I'm going to open these templates, and you can see that they're just HTML, and this was the HTML being rendered. In fact, you can change the HTML. Everything will automatically be saved in the workspace. And now you can see if you refresh the web page with your web app, then the HTML automatically updated. Next, you'll do an exercise to expand this web app and get used to all of the routes and templates. Because Flask is a Python library, you can use any other Python library in a Flask app. This makes Flask a great choice for data science because you can use data science tools like Pandas or NumPy inside your Flask app. Here's an example. I've gone to the World Bank website and downloaded data about rural population percentages for various countries over the past 50 years or so. I downloaded the data as a CSV file, clicking down here, and then I uploaded the CSV file into the workspace. I created this data folder, and then I uploaded it here. If you haven't uploaded anything to the workspace before, you just click on this plus sign, and then you can create new files, new folders, or upload a file or upload a folder. Looking at the data, you can see that it's not quite clean, and it needs some data wrangling. You can do this wrangling directly in your roots.py file. You just need to import any libraries you're going to use, like the pandas library. So I'm going to do that. Then I'm going to copy and paste some code I wrote to wrangle the data set and get the data into a form that Plotly will be able to use. I'll paste this code below the video as well so that you can study it in more detail. But essentially, all it does is filter out the data set for certain countries and get the data for just 1990 and 2015. Starting up the app, you'll see that everything still works fine. And in fact, I added a couple of print statements into my code so that you could see the results of my data wrangling. However, now my roots.py file looks a bit messy, so I'm going to refactor this code so that everything's a bit cleaner. I'm going to create a new folder and call it wrangling scripts. And then inside this folder, I'm going to create a new file and call it wrangling.py. Okay, and in wrangling.py, I'm just going to take all of this data wrangling code and cut it out of roots and put it in wrangling.py. Now I need to import pandas, and then I'm going to make all of this into a function. And the return for this function is just going to be this data variable. Okay, now returning to roots.py and looking at the workspace folders, I'm going to say from wrangling scripts dot wrangling, and then import this data wrangling function. And then I'm going to call this function and save the results in the data variable, and then just print out the results so we can see it. Now I'm going to start the app up. Okay, and you can see everything's still working, except now the roots.py file stays clean and it's easier to understand what's going on. Now, of course, you might want to do some of this wrangling outside of your web app and then upload a cleaner CSV file, but you'd still need a way to load the CSV file, which you can do with pandas. In the next part of the lesson, we're going to add Plotly so that we can actually render this data as a data visualization. This is the part where we start putting everything together. Bear with me a bit on this video because there is a lot to show. Here's a reminder of where we are so far. I have this web app with roots and HTML templates, but the templates aren't particularly interesting yet. There's also a CSV file that's imported and wrangled with pandas. This is the file that does all the wrangling. The goal is to take this wrangled data, set up a Plotly visualization, and show the visualization on the front end. Let's look at the roots.py file. My World Bank data dashboard was actually only one web page, so I only need one root. I'm going to erase this second root down here. I've got all this data here in this data variable. Let's start the web app just so we can see what that data looks like. The data is getting printed out in the roots file. It's a list of tuples where each tuple contains a country name, X values, and Y values. So how can we convert this into a visualization? You need to somehow send this data, which is sitting on the back end, and get it over to the front end. How can you do that? In the render template method, you can actually send variables to the front end. All you have to do is list them after you specify the template name. That's what I've done here by saying dataset equals data. Now the front end is going to have access to this dataset variable. Let's switch over to the index.html front end code. This index.html just has regular HTML in it, but Flask actually includes a template engine called Jinja. A template engine is a tool that lets you reuse HTML by introducing variables. Here's what I mean. The dataset variable from the back end is now available to the front end. All you have to do is wrap the variable name in curly braces like this. Now let's go to the front end. On the index.html page, all of the data is just now being printed out. So we were able to get the data from the back end and show it on the front end. In fact, with Jinja, you can write control flow statements like if and for. These can give you more control over the formatting. You just have to learn the syntax. Let me show you. Going back to index.html, I'm going to write a for loop. Let's see what this for loop looks like on the front end. Okay, so it's iterating through all of the data and printing it out line by line. You could imagine using this syntax maybe to make a table for the data, for example. The syntax is that variables are surrounded by two squiggly brackets and control statements have one squiggly bracket and then % signs. The reason why these variables and control statements need to be separated off in some way is so that the template engine knows what part is actually HTML text and what part is a variable or control statement. You can imagine why this is called a template engine. The HTML can be reused as a skeleton, and the information in the variables might change. So the next step is to figure out how to set up a Plotly visualization in the Python backend, and then send this information to the front end. Now you know how to get information from the back end of the web app to the front end of the web app. But what we really want is to pass the information from the back end to the front end with a visualization. I've written some code that sets up a Plotly visualization on the back end and sends that information to the front end. Then the front end plots the visualization. I'm going to walk you through this code, and then I'll provide similar code as part of an exercise so that you can become familiar with it. So what has changed? First, I've pip installed Plotly into my workspace using pip install Plotly. If I do that here in the terminal, nothing's going to actually happen because I've already installed it. You see here that it says requirement already satisfied. In the routes.py file, I'm importing the Plotly library, the JSON library, and graph objects from Plotly. Then I'm getting the wrangled data by calling the data wrangling function, and I'm printing out the first tuple so that you can see what the data looks like. In this visualization, I'm going to visualize the first tuple for now. That's why in the country variable, I've only grabbed the first tuple's country value and then the X values and the Y values of the first tuple. To remind you of what the data looks like, I'm just going to run this new web app for a second so that you can see the results in the terminal. Okay, so here it is. United States, 1990, 2015, and then the Y values are 24.7 and 18.383. Hopefully the code that comes next looks somewhat familiar because it's very, very similar to the JavaScript code for plotting with Plotly. Inside this graph1 variable, I'm preparing a line chart using the X values, Y values, and country name. The visualization has to be in a list, which is why you have square brackets around this go.scatter syntax. How, you might ask, did I figure out the syntax for all of this? Well, I read through Plotly's Python library documentation. Next comes the layout, which has to be in a dictionary. The syntax might be a little bit confusing, but this is just a dictionary of dictionaries. And again, I figured this out through reading the Plotly documentation. The next part of the code is setting things up for when there are multiple visualizations, although for now there's only one visualization. I'll get to multiple visualizations a little later. The IDs variable will be a list containing distinct IDs for each plot, like figure 0, figure 1, etc. And then figure JSON converts the dictionaries holding the visualizations into a form that Plotly can interpret in the JavaScript front end. Next, I send the list of IDs and the figures JSON variables to the front end in the render template method. So let's look at the index.html file for the front end. Here, I've put a link to the JavaScript Plotly library in line 6. And I've also printed out the IDs variable and figures JSON variables in paragraphs so that you can see what their values look like. That's going to be printed out to the front end. Do you remember before when you used Plotly in JavaScript and you created divs for each plot? That's what I'm doing here in line 14 by taking the first ID in the IDs list. If I had more plots, I'd need to make more divs for the other IDs like ID bracket 1, IDs bracket 2, etc. Finally, the JavaScript code below uses the figures JSON variables and IDs from the front end and then plots each visualization one at a time, iterating through the IDs, data, and layouts. But for now, I only have one visualization. This safe word here is an escape filter. Escaping just makes sure that if the figures or ID variables use any of HTML's special characters like the greater than or the less than brackets, these get interpreted correctly. I'm going to give you all of this code so you don't have to rewrite this. All you'll need to do is make a div for each visualization with the correct ID and place the div where you want the visualization to appear. Let's see what the front end looks like. So this is the index.html page, and then this is the figure ID, and then this is the value that was in figures JSON, and then here's the plot. So it worked. So far, the front end maybe isn't that well organized, and maybe it's not clear how to make multiple plots or to plot multiple lines on one plot, but that's what I'm going to show you next. Okay, so in this web app so far, we only had data for the United States, and it was one line. And so now I've done a graph where I have all of this data from different countries. So let me show you how I did this, and it's not that much code. Going back here to the workspace, all I did was change a little bit of the roots.py file. So here, what I have commented was the code before where I had graph 1, and I was just using data from the United States in the X, Y, and name parts of this list. If I go down here, what I've done now is I've made this graph 1 list, and then I'm actually iterating through the data, and for each country I have of data, I am appending part of the visualization to this graph 1 list. So you might have to stare at this code for a little bit to understand what I did, but essentially it's really similar. You still have this go.scatter part here, but the difference is that I keep appending new ones to this graph 1 list for each country in the data set. And that's all I did to get this visualization to show up like this. Next, I'm going to add in a few more visualizations and also start using Bootstrap so that the front end looks a little bit better. So for this last part, we're going to go from this into this dashboard here. So how do we go from here to here exactly? Well, the main difference is that I have made multiple charts here. So these are all just div ID 0, div ID 1, div ID 2, div ID 3, and I'm just placing them into the Bootstrap front end that you made earlier. So it might seem a little intimidating, but it's actually just putting everything together that you've already been practicing. Okay, so here is my final code, and I'm going to walk you through it so that you can see what I did. Index.html has all of the front-end code with Bootstrap. So this might be vaguely familiar because we already went through this and you practiced using Bootstrap. So this is importing all of the Bootstrap files here, and I'm also importing the script for Plotly, the Plotly library. And then going down here, this is just all of the Bootstrap front end that you were working with before, like this is the navigation bar up here. All of this code is the navigation bar. Okay, and then here is just dividing everything up into rows and columns. So there's the LinkedIn logo, there's the GitHub logo. Scrolling down, here is where the plots actually start. So nothing new here. This is the H2 tag, this is the H4 tag. Keep going down. Okay, and so this is really the only thing that's new from when we were looking at Bootstrap before. I'm just putting in here a div with an ID of the first chart. And then here I'm putting a div with the ID of the second chart, a div with an ID of the third chart, and here a div with an ID of the fourth chart. And then scrolling down, this just has the same JavaScript code from before, where we're just iterating through these variables that came from the back end to put everything on the front end. So the only thing that's really new here is just adding these divs with the IDs of the visualizations in them. That's all I've changed from when we were working on the front end earlier in the lesson. And it gives me this, which is pretty cool, right? So the next thing to talk about is actually these visualizations themselves and how I wrote the code on the back end. Okay, let's go back to roots.py. So I refactored a lot of the code to make roots.py a lot simpler. So all I'm doing here is actually in this return figures method, which comes from this wrangling scripts.wrangle data file over here, I am actually just doing all of the data wrangling and getting all of the plotly figures ready back there so that it doesn't even show up in the roots.py file. This code is exactly the same as before. It just iterates through this figures list and makes the IDs and then converts figures into JSON and then passes the variables to the front end. So the perhaps scary part that did take me a long time is the data wrangling. And for better or for worse, a data scientist usually has to do a lot of data wrangling. So what did I do? I wrote a function that cleans the CSV files in a generic way because all of the CSV files have the same format when they come from the World Bank. So I wrote this function here that just cleans everything up. And again, I'm going to give you this code and you can look through it. It's going to be an example that comes after the exercise that I'm going to give you. Okay, and now we have this return figures function, and all it does is set up the code for all 4 of the visualizations. And there's a lot of code, but if you look at it little by little, I think it's relatively interpretable, and it's similar to what I was showing in the last part of this screencast. So here we have graph 1, and this is where all of the graph 1 information is going to go. And so first I clean the data. I'm just changing the column names. I'm doing a little bit of sorting so that everything shows up in the visualization in the order I want it to. And then this is what I showed, very similar to what I did before, where I'm iterating through each country and then I'm appending the information to the graph 1 visualization. So this is all of the code. Here's the layout just for this visualization here on the left. Okay, and then for chart 2, I again am cleaning the data, and then this time I only wanted data from 2015, so the wrangling was a little bit different. And I wanted to make a bar chart, so here I put on the x-axis the countries, and then on the y-axis I put the values, and I'm using pandas and Python to do all of this. Here's the layout for number 2. And again, this is the bar chart here in the upper right. Moving down, we've got the code for chart 3, where again, I'm iterating through and building this up country by country and putting multiple lines on one visualization. And then I have the layout, and then comes the 4th chart, which is this one in the bottom right. And I am just cleaning the data again. I have to merge 2 data sets together. That's what's happening in 128. And then iterating through the countries and setting up the visualizations. This one had a little bit more wrangling to do because I had multiple CSV files. Another thing I should point out is that actually, if you look here in each graph, I have name equals country. So I have this country variable, and it was really important that I left the countries in the same order so that they kept showing up with the same colors over here. So I was using the same list of countries in the same order every time so that Plotly would automatically use the same colors in all of my visualizations. And then keep scrolling down. Okay, so once I have all of this ready, I'm appending each visualization to this figures list and then returning figures. So going back to roots, which is actually using this return figures function, it just returns all of the figures and it's ready to go. So that's how I did it. It did take me a good amount of time to do all of the wrangling, to refactor the code. And again, that's part of being a data scientist. The thing is that for this exercise at the very end of this lesson where you're going to make your own data dashboard, you can reuse a lot of my code. All you're really going to have to do is change maybe index.html to put in links to your own GitHub repo or your own GitHub account into your own LinkedIn account. And then you might want to add or take away visualizations. And in that case, you're going to want to scroll down and make sure you have enough divs for each visualization that you're going to make. Wrangling is where the bulk of your work is going to go. You're going to have to figure out how to clean your data and get it in the right format so that it works in Plotly. And that's it. Up until now, you've been developing the web app in the classroom or on your local computer. However, you can't share the app yet with other people unless you transfer all the files to someone else's computer and then have that person set up a Python environment on his or her local computer. So now it's time to deploy the app to an external server with a web address that anyone can go to see your work. There are a lot of companies that provide web servers for deploying a web app. In this video, I've chosen to use Heroku, which is considered a platform as a service. In my opinion, it's one of the easier platforms to use and doesn't require much configuration. There's also a free tier that doesn't expire. So if you have a small web app like this one that doesn't have a database, Heroku will work for our needs. I'm going to walk you through getting the app up on Heroku so that you can do it yourself. I'm going to do it from the Classroom Linux workspace. I'll also provide a list underneath the video of other services you can use to put the web app on. Okay, so this is our web app. All of the folders and files are here in the left-hand column. My first step is I'm going to make a new folder and I'm going to put all of these files into that new folder. I'm going to do this from the terminal, but you could also do this using the plus sign and also right-clicking on these folders and files here. So I open a new terminal and I'm just going to say make directory and I'll call it web app. And now I'm going to move all of these folders and files into this new web app folder. So MV is for move, -T just means I'm specifying the new directory first, and then after that, all of the files and folders that I want to move into the web app folder. And it looks like I spelled World Bank app wrong, so let me just fix that. So you can see everything moved over into this new folder. So in order to install this web app, we're going to have to specify all of the Python libraries that are needed. Now in this workspace, and probably on your local computer as well, there are a lot of extra Python libraries installed that you don't actually need for your web app. So we're going to deal with this by creating a virtual environment and just installing all of the Python libraries we need for this particular app into the virtual environment. Now, this workspace has Anaconda installed, which is a set of tools used for Python and data science. And there's actually an issue with the Anaconda installation and Python and virtual environments. So first, before doing anything, you need to run conda update Python. And this is going to take a little while. Now, if you don't have conda installed on your local computer, you wouldn't have to do this step. Okay, and when it says proceed, click yes and hit enter, and then wait for the installation to finish. Okay, now that Python is updated, you can actually make a virtual environment and then start it up. So to make a virtual environment, go into the terminal and type the following: python 3-m venv, and then the name of your virtual environment, which can be anything you want. I'm going to call it World Bank env. And now you can see there's a new folder up here on the left called World Bank env, and inside is actually a Python installation that's separate from the rest of your Python installation on your computer. The next thing is that you need to activate the virtual environment. So I'm going to type in source world bank environment /bin/activate. And you can see that the virtual environment is activated because here in the terminal, now the name of the virtual environment appears. Okay, the next step is that we're going to pip install the libraries we need for our Flask app. And so again, the reason we're creating this virtual environment is that all of these libraries are going to be installed in the virtual environment instead of the regular Python installation on your local computer. So pip install, then I'm going to list out all of the libraries I need, which in this case is Flask, Pandas, and Plotly. And then I'm actually going to add in this other library called Gunicorn, which we're going to need for deploying the web app. Okay, now from the terminal, I am going to go into the web app folder. The next step is to actually install a set of tools that Heroku provides so that you can write commands and upload your app directly from the terminal to Heroku. There's actually a web page that tells you how to install these tools on different systems. This is what it looks like here. I'll also put a link to it below the video. But on this page, it says if you're on a Linux system or Ubuntu system, which we are, then you're going to do the following. You go into terminal and you run the following command up here. And now it's installing. And just to check that everything installed, I'm going to type Heroku version. Okay, so it looks like it installed and we're good. The next thing you're going to want to do is to sign up for a Heroku account. So it's just like signing up for any other web service. If you go to the Heroku website and you click on sign up here in the top right corner, you just fill this out with your information. So once you've made a username, which is just your email address, and a password, you actually need to log in from the command line. So now that we have the Heroku tools installed, you can type Heroku login, and it says enter your login credentials email, and then it's asking after that for a password. So I'm gonna hide this from the screen while I put this information in. Okay, so now I'm logged into my Heroku account, and again, it's just a matter of putting in your email address and your password for your Heroku account. And now there's just some housekeeping to do before we can upload all of this to Heroku, to a Heroku web server. So first of all, I'm going to open worldbank.py, and I'm going to remove this app.run line because we don't need this anymore. And I also need to create a proc file, which is a file that tells Heroku what to do when starting your web app. You could do this up here by creating a new file, or you can do it in the terminal and say touch proc file. And you can see that this proc file just appeared here in the left-hand side. I'm going to double click to open it, and then I'm going to say web Gunicorn World Bank app. And so this essentially just says when starting up the web app, call the Gunicorn library and run my World Bank app, which has this app variable in it, which we've seen before. The next thing I need to do is specify all of the Python libraries that are going to be needed. So if you type pip freeze into the terminal, it's going to give you a list of all of the currently installed Python libraries. So you're going to need to put all of this information into a file called requirements.txt. So I'm going to say pip freeze, and then the greater than sign, requirements.txt, and that's going to put all of this information into a file called requirements.txt. It's important that this file is actually called requirements.txt because Heroku is going to look for this file. So you can see it just lists out all of the Python libraries that this app depends on. The next step is to initiate a Git repository. So git init, and then git add, and then I put the period here, and then I'm going to say git commit -m, and say first commit as the message. Okay, and it says that please tell me who you are. You have to configure an email address and a name. So you can actually put anything in this that you want. I'm just going to say something at example.com and git config user.name. You can put your real things in here if you want. My name's Andrew, so okay. And now let's try committing again. Git commit -m, first commit. Okay, so we made our first commit. The last step is to create a web app on Heroku. So to do that, you say Heroku create, and then the name of your web app. And this name has to be distinct. There could only be one of these names on all of Heroku. So if the first one you try doesn't work, just keep trying until you find something. So I'm going to call this DSND Udacity web app. Hit enter. Okay, so it gave me the link where I can see the web app, and then it also created a Git repository on Heroku where the files are actually going to be uploaded to and stored. And I'm also, just to double check, I'm going to say git remote-v, yeah, which shows you that Heroku automatically set up these Git repositories as remote repositories for you. So the last step is to say git push Heroku master, and that's going to push our app to that Heroku Git repository. Okay, and here it says that everything was deployed to this web address, so I'm going to click on that. And yeah, it looks like the web app deployed. So now it's officially at this web address, dsnd-udacity-webapp.herokuapp.com. So that is one way to deploy a Flask app to the web. Wow, congrats on getting your web application up and running. The best part about this web app is that you can repurpose it for future analyses and then share your results with the world. Let's recap what you've learned. First, you practice using the front-end languages HTML, CSS, and JavaScript. Then, you saw how a framework like Bootstrap makes front-end web development much easier to accomplish. Next, you made visualizations using Plotly, which is one of the most popular libraries for displaying charts on the web. And finally, you created a backend using Flask and then deployed your web app to the internet. Great work. Make sure to include the web app as part of your professional portfolio and share it with your friends, family, and colleagues. It's a nice way to show off your software engineering skills.
It's time to celebrate! You've achieved so much in this course. You've gained experience with software engineering practices that help you produce efficient, robust, and maintainable code. I can't emphasize enough how much these skills will make you stronger as a data scientist. So be sure to apply them in your daily work and your professional portfolio.
You've also gained experience with object-oriented programming and writing a Python package. You now have a sense for how packages like scikit-learn and pandas work under the hood. Use these skills to write your own packages and share your code with the world.
And finally, you've built a web application that loads a data dashboard. We encourage you to take the template code from the web development lesson and reuse it for your own purposes. It's a great way to show off your data analysis and data storytelling skills.
This course was designed to get you comfortable with writing code for real-world applications. The stronger you are at coding, the more success you'll have as a data scientist.
Definitely. Data science is powerful, but to bring its contributions to production, you often need software engineering. And although the amount of software engineering you need to know will vary across teams and companies, developing these skills will really help you with implementing your data science ideas.
Be sure to share what you've built on the Slack channel, on a personal blog, and in a GitHub repository. We're really excited to see what you build. When I was using CSV files in the web app, I downloaded them from this website. I would choose an indicator that interested me, click on it, and then go here to the CSV file and download it. However, There's another way to access the World Bank data via the World Bank API. If I go to a search engine and I put in World Bank Data API, I go here to API documentation. So in general, to find an API and an API's documentation, it's best to look for it on the web. I'm going to click here where it says API Basic Call Structure. Essentially, in order to learn to use an API, you need to read its documentation. If you haven't seen this term REST before, it refers to a software architecture for the web called Representational State Transfer. I'll put some links about REST architecture below. Most modern APIs use this type of architecture. If you scroll down, you'll see that there are a lot of examples. I'm going to paste these examples in a web browser and just see what happens. So it looks like this is returning country information for countries with income level LIC, which I assume stands for low income countries. This is an example of an XML response. So by default, it looks like the data gets returned in XML format. Going back to the API documentation, you can see here some of the options that the API has and how to format these URLs to make your query. For example, here it shows you can filter by date. You can change the format of the response to get JSON instead of XML. So going back here to the query, for example, I can say format equals JSON. And this is the same information from before, but it's just in a different format. And I personally think that JSON is easier to navigate, so I would stick with JSON instead of XML. Next over here, I'm going to click on API indicator queries because the indicator data was what I was using for my web app. But now instead of downloading individual CSV files, I can pull the data directly from the World Bank API. I'm going to scroll down and look at some of these examples. So here it says request format, right? And it gives you this example here. If you put in this URL, it's going to return all of the indicators that the World Bank has with information about all of them. In fact, this is actually only 50 of them because I know from reading the API documentation that it only gives 50 results at a time, which you can see up here, per page equals 50. So scrolling down, here is an example of getting GDP data for Brazil. So I'm going to copy that and I'm going to paste it here and see what the results are, hitting enter. Okay, so this gives me data about GDP in Brazil for various years, going all the way back to 1968. So I've already read the documentation, so I know that you can start adding options to this query, like adding more countries, or showing more results per page, or filtering by year. So let's do some of that. For example, I can add other countries to this query, like, say, the US and China, and I know how to format this because I've read it in the documentation. And I hit enter, and if I scroll down, well, it looks like we still only have Brazil, but that's because, like I said before, it'll only give you 50 results at a time. So to get more results, I have to tell it with a variable and say per page and increase the amount of results per page. So now I have 500 results per page instead of 50. And if I scroll down, we'll see that, yes, we've also got China here, and we've got the United States. So let's say I also want to return this in JSON format. So I can say format equals JSON. And this is the same data, it's just in a different format that, like I said, in my opinion, is easier to navigate. And I can filter by date as well and just get data from, say, 1990 to 2015. And so here are all of our results. It might seem like I magically know how to do all of this, but in reality, I've been reading the World Bank documentation to prepare this course and looking at a bunch of examples. As an example, how do I know what the country names are? Well, I've read in the documentation that the country names are using the 2-character ISO codes, which is an international standard for abbreviating country names. There are a couple of caveats I want to mention. First, this API does not require authentication, or in other words, it doesn't require a username, password, or any other identification. That means I can directly paste a URL into the browser and get the results back. However, that is not the case with all APIs. Many APIs require some sort of authentication, so you need to send an API request programmatically, like with Python code, including a message that includes your credentials. An API's documentation should ideally tell you how to do that. Next, you're going to practice making calls to the World Bank API using Python, and then navigate the results that you get back. This will set you up for using an API in your web app. I've made another version of the World Bank data dashboard, and this time I've used the API on the back end to get the data. You'll also notice that there's a new red button. This is actually a menu where I've created a filter where you can choose certain countries, hit submit, and then it'll filter out for just the countries that you've chosen. The reason why I've added this extra feature is just in case you already know a little bit about web development, and I'm trying to encourage you to add extra features if you want to. And it also might help you understand a little bit how the code works with the API on the back end. So what I'm going to do is I'm going to show you the code behind this version of the web app so that you can see how it works and how I've used the API to pull the data instead of using a CSV file. So here on the left, you can see all of the files that make up this version of the web app. And I'll also put this on GitHub so that you can download and take a look at it. The only files that have changed is this data.py file, which is inside of scripts, and that's where I'm doing all the data wrangling. Then there's index.html, where I've added the code that takes care of the red filter menu. And then I've had to add a little bit of extra code into roots.py to take care of the logic for all of the filtering. So let's start with the data wrangling in data.py. Don't worry too much yet about how the red filter works on the front end. I'm just going to show you what the API data wrangling code is doing. So I'm starting out with this country default dictionary where I have the country name and the 3-character ISO codes. Before, in earlier videos, I used the 2-character ISO codes. In this code, I actually use the 3-character ISO codes, but either way, it works with the API. So here I have my return figures function like before, and the difference now is that I'm inputting this list of countries. So it's the countries that I'm filtering for. And by default, I want all of the countries. So let's scroll down. Okay, so this logic here says that just in case there's no countries variable sent over, make country default the countries variable. And then I do a little bit of preparation here where I make a list of the countries with the semicolon between each country name, because that's what the API is going to expect in the URL. Then here I'm making a list of the indicators that I want to grab, because I'm going to iterate through them in a for loop and make all of the visualizations one at a time. So moving down a little bit, here's where I iterate through each indicator. So the first step is to get the URL string ready to send over to the World Bank API. Then I use the requests library down here in line 54 to get the URL, and then I receive the data back in JSON. Here in line 59, I'm iterating through the data that I got back from the World Bank API and getting it ready for Plotly. So that is the end of the for loop. So going back up, what happens is that it goes to the next indicator, prepares the URL, and then gets the data and then puts it in a data frame and appends it to this data frames variable in line 63 so that I'm getting all of the data prepared. Once the data is ready, I go and prepare each graph, each visualization one at a time, just like before in the other version of the code. So here I'm preparing graph 1. There is still some data wrangling I have to do. I do some sorting to make sure that everything's in the right order that I want. I get the country list just like I did before in the other version of my app. And here I'm preparing graph 1 for Plotly. And then I have the layout here as well. Then I'm preparing graph 2 with the second data frame that I created. And again, there's a little bit of data wrangling. And then I prepare graph 2 and the layout for 2. Graph 3, scrolling down, graph 4. And then I append all the charts and my function returns all of the figures. So the major difference here in this data.py file is that I'm using the API to get the data instead of using CSV files that I've uploaded as part of my web app. Next, let's look at index.html. So index.html is very similar to what it looked like before. The only difference is that I've added a collapsible filter, which in reality is just an HTML form that you can submit. So I didn't show you how to make a form before or how to submit a form and how all of that logic works, but I'll walk you through the code a little bit just so you have an idea of what's going on. It's a little bit beyond the scope of this course, but it shows you that if you really like doing this web development stuff, that there's more to learn and more to do, and you can keep adding more features. So scrolling down, here I have drop-down menu for filter. So all of this came from an example on the Bootstrap website. And so I have a button here, which is the red button, and then I have a drop-down menu. And you can see here I'm using Jinja, which I'll explain in a minute what I'm doing. And then there's a form. And so then this form can actually be submitted with this submit button down here. So what is all of this Jinja code doing? Essentially, I'm getting from the front end which variables were selected or submitted, and I am doing some filtering so that I know which ones should be checked based on what were submitted before. And here I'm populating the names of all the countries. This might be a little bit confusing if you're not too familiar with JavaScript and Jinja and HTML, but look at the code for a bit and see if you can figure it out. The other key to this code is down here. There's a little bit of JavaScript that I've written, actually jQuery, to take care of the filter. So for example, you can see here that this checks or unchecks the filter boxes based on the select all box. So if you go back here and you hit select all, that's what this is taking care of. Uncheck select all box when unchecking another box. So that's here when I click on something, it unchecks the select all box, and then check select all box when rechecking all of the other boxes, which you just saw. When I recheck everything, select all gets chosen. So the other part to look at is roots.py. And roots.py is very similar. In fact, if you look here from here down, it should look quite similar to what we had before. The difference is now roots.py has to take care of submitting this form. So what happens is when you submit the form, it sends out something called a request, a post request. And so when you send out this post request, I'm saying, hey, read this form and figure out which countries were selected. And then for each country that was selected, append it to this list, countries selected. And then you can see here, countries selected is sent to the front end at index.html. And that's what a lot of the Jinja code in index.html was doing. It was iterating through this countries selected variable so that it knew which checkbox should be checked and which ones shouldn't be based on the filter. So I know I'm kind of going through this quickly, but I think if you download this code yourself and take the time to look at it and figure out all the logic, it'll be really helpful for just seeing what you can do with a web app. But the main thing to think about if you're doing the advanced version of the project is what's happening in data.py. The filter thing here is really just an extra thing I made. But the main point is looking at how I've used the API in data.py to get the data and then use it to make the plots.
Hello and welcome! Today we'll be learning all about version control, and we'll be using the version control tool, Git, to help us manage different versions of our project. Now, before we dive into some of the nitty-gritty details, let me tell you a story, because who doesn't love story time? Back in the day, my brother and his best friend would play games all the time, but one of their favorite board games was a popular World War II strategy board game. The board game shows a map of the world, and you put pieces on the board and move them around. I didn't really care for the game all that much because it would take so long to play. Sometimes they'd be playing a single game for a day or more. Now, because there's a big board with lots of pieces that move around, if they had to pause the game, they would snap a picture with their phone. They'd use these pictures as save points in case anything happened to the board or the pieces, like someone bumping the table or the dog coming along and knocking the pieces everywhere. If there were a problem, they could use a picture to recreate the exact setup and jump back to that point in the game. So each of these pictures is a save point. The pictures record the time, who took the picture, and the state and location of the pieces. This idea of a save point is exactly what version control does. You don't seem all that impressed. Well, let me tell you that it's incredibly powerful, and I love having it. Because when you use version control, you create save points that save your project. This lets you have the freedom to change absolutely anything about your project and be confident that nothing will be lost. Total security and total freedom. Who wouldn't want that? And you get all of that with a version control system. Sounds pretty awesome, right? So hi, I'm Richard, and I've been using version control for years, and Git has saved me from countless sticky situations. For example, one time I'd realized I'd deleted an important image, but I was able to recover it because the project was being tracked with version control. It's an incredibly helpful tool, and you'll grow to depend on it as much as I do. You ready to get started? Awesome, let's get going. There are a number of version control systems out there, but three of the most popular are Git, Subversion, and Mercurial. Not only are there dozens and dozens of different version control systems, there are actually two different categories. There's the centralized model, and then the distributed model. In the centralized model, there's one all-powerful central computer that hosts the project. Every interaction must go through this central computer. In the distributed model, there's no central repository of information. Each developer has a complete copy of the project on their computer, which is cool because that means you can also work offline. In this course, we'll be using the version control system Git, which is a distributed version control system. Now, you might have heard of GitHub. Git and GitHub are quite different. Git is the version control tool, while GitHub is the service that hosts Git projects. To work with Git projects, you're not required to use GitHub, but it's an awesome tool and you should definitely check it out. For now, you can think of it as basically just another computer where you can upload a copy of your project. Centralized, distributed, if these don't make a lot of sense right now, that's totally fine. This is to give you a big picture idea of where things fit together. These terms are more important if you're working with a team, but you'll be working locally on your computer for the entirety of this course. Here's the outline for this course you're taking right now. Let's click on this link to get to its revision history page. This main part shows the document that we see in the normal view, but this sidebar provides all the awesome features we want. This is the history of the changes made to this document. They're organized by date and show who made the edits. Clicking on one of these will swap out the current version of the document with an older one. Let's click on the October 13th version. The main area now shows the version of the document as it appeared on October 13th. It also provides these arrows to let us jump to the edits that were made. The highlight color indicates which user made the edit. If I like this older version of the document, I can replace the current version with this older one by clicking the Restore this revision link. One last thing is that Google Docs will group lots of changes together in one larger group. If you want to see smaller sets of changes, that's what the Show More Detailed Revisions button does. When I was first learning Git, one of the hardest things for me to pick up on were all of the various terms that were used. For those of you that see a big long list of terms and zone out, don't worry. Just skim the list for big picture ideas. If you're like me and like knowing the terms that are being used, then this section's for you. These terms are the vocabulary we use to talk about version control, features of a version control system, changes we'd like to make to our code while it's in a version control system, and so on. Some terms are, well, version control system, source code manager, commit, repository, repo, checkout, working directory, staging area, the index, staging index, SHA, branching, merging, merge complex, remotes. Wow, get these things out of here. So yeah, the terminology can be a bit overwhelming. There are a number of good handouts that are on the web though, but I've created one for you that lists the most important terms along with a brief definition as a companion to this course. I highly recommend that you download this right now. Place it on your desktop, or print it out and have it on your desk. Use it as we progress through the course to review key terms. At first, the words might not make any sense because this is one of those chicken and egg scenarios. Should I learn the terminology first, or how to actually use Git? I think it's easiest if you learn Git if you have some familiarity with the terms it uses. In addition, it might be helpful for you to create your own cheat sheet. If you get stuck on a word or idea, just write it down. So if you get a handle on version control's somewhat foreign terminology, you're already a giant step towards becoming a Git master. Let's say we have a repository that is made up of these 3 files. We want to start using version control in this project, so we create a new Git repository. In a Git repository, there are 3 main areas we need to know about. First, there's the working directory. Then there's the staging index. And last is the repository. So we have these 3 distinct areas in Git. When you're first working with Git, it can be a bit hard to realize that there are these 3 distinct areas because you don't really see any visible change to the files on your computer. Git manages these 3 different areas though, and we'll be using the git shell command to interact with files and move them from section to section. Okay, so we've created this empty Git repository. We can tell it's an empty repository because the repository section is empty. Git knows about files that it hasn't seen before. Let's indicate that a file is new with a green star. Git keeps track of files by adding them to the repository. We can't move these files right into the repository though. They have to be moved to the staging index first. So we'll use Git to move the changes to the staging index. Remember that the staging index is where you can place all of the files that are about to be committed. Now let's commit them, which moves them into the repository. Now the files in their current state are safe. Let's say we then make some changes to our site's CSS file. Git sees this change and marks the file as modified. We take the same steps to move the changes in the CSS file to the staging index, and then commit them. I think you get the idea, but let's look at it one more time. Let's say the HTML and JavaScript files have changed. Remember that Git knows what files are new or changed. We'll move these changes to the staging index, and then commit them. So the process is, add a new file or modify an existing file, move the changes to the staging index, commit the changes to the repository. You got it? Okay then, what about this scenario? Let's say the HTML and CSS files have changed, and we've staged the changes. If we then decide to modify the HTML file again, what would happen if we made a commit right now? Seems like a good time for a quiz. When a commit is made, only the changes that are on the staging index are moved into the repository. If we want to include the second set of changes in the commit, then we need to stage the changes. Now that this second change to the HTML file has been staged, the 2 sets of changes to the HTML file are combined into just 1 set of changes. And then we can commit like normal to move these changes into the repository. We have all of these changes saved in our repository, but how would we access these commits? What if we want to look at this specific commit? When each commit is made, Git creates an ID for it. The ID for the commit is its SHA, the first 7 characters for what each commit's SHA might look like. At its core, Git records changes to files as commits. These commits are all saved in a repository. Everything else, things like the working directory branches and SHAs, are there to help make and reference commits. As you've seen, the terminology that version control uses is kind of cryptic at first. Hopefully you had the handout with you and reviewed it as you went through the high-level overview of how Git is used. In the next section, we're going to install and configure Git. Make sure to follow each of the steps in order so that your computer will be configured like mine. Now, configuring your terminal isn't required for Git to work correctly or to continue with this course. You can do the entire course without this step. But not only does it make it easier to use, all professionals reconfigure their terminal. the reconfiguration we'll be doing will add color to the terminal and display specific Git information. Sounds good? Let's get to it. I've downloaded the files and unzipped the directory. In the terminal, I'll type cd to make sure I'm in the home directory. Using the move command, I'll move the Udacity terminal config directory into my home directory, but I also want to rename it by adding a dot at the front. Since the terminal is in the home directory, I'll move this directory into the home directory and name it .udacity terminal config. The bash profile file also needs to be in my home directory, but this is a very common file, and if I already have this file, then I don't want to overwrite it. I'll use ls-a to check if I already have one. I already have a bash profile file, so I'll open it up in my code editor. Now that I have this file open, I just need to copy the text out of here into this file. Now just save the file and I'm done. If you don't already have a bash profile file, then you'd use the move command to move this file into your home directory, making sure to name it with a dot at the beginning. But I'm not going to run this because I already have updated my .bash profile file. Now even though I've updated my bash profile, nothing's changed with the terminal. That's because I need to restart it. So here's what your terminal should look like. Here are the configuration files that I've downloaded and unzipped. I need to move these files into the home directory. The easiest way is to right-click on the window and choose Git Bash Here from the list of options. This option shows up because I've already installed Git on this machine. In the shell, just type cd and press enter. This moves the shell to the home directory. To open this directory in Windows Explorer, type start and a period. I like being able to jump to this directory, so I'll pin this to the Quick Access menu. To do that, right-click on Quick Access and choose Pin Current Folder to Quick Access. Now let me shift these windows around to organize them better. Now that we have the home directory open, we can move the configuration files over. Select both items and drag them to the home directory window. They're in the correct location. Now they just need to be named correctly. Both files need to have a dot at the beginning of their names. Since Windows Rename feature doesn't allow that, we have to do it on the command line. We'll use the mv command to rename bash profile to .bash profile. We'll do the same thing with the folder. We'll use the mv command to rename Udacity terminal config to .udacity terminal config. To see the changes, we'll have to open a new shell. So the shell is now configured with the correct content, but I also like having a white background with black text. So I'll click in the top left corner of the app, choose Options, and then update the foreground color to black and the background color to white. Perfect, now everything's configured. Great job setting up your computer to use Git. Going through this lesson, you laid a solid foundation to start learning version control. We looked at the benefits of version control and how incredibly helpful it can be. You also looked at the terminology that version control systems use, and you did download the terminology document, right? It'll be extremely helpful to have on hand as you go through the remaining lessons. And last, you installed Git and got everything configured. Fantastic work. Really, a lot of people get bogged down with all this stuff and never actually learn version control. So congrats on getting this far. Now let's head to the next lesson to learn how to create a Git repository. In the last lesson, we looked at some of the common terms used in version control systems. You also installed Git on your computer and did some initial configuration of Git, like adding your name and email. If you skip these steps, it's probably a good idea to go back and check them out again before continuing. In this lesson, we'll be learning how to create our own Git repositories. I mean, we can't really do anything without having a repo to work with. Oh, and repo is just short for repository. Those mean exactly the same thing, so I'll be using them interchangeably. Remember to keep the list of terms nearby as a reference. We'll be looking at 3 Git commands in this lesson: git init, git clone, and git status. With git init, you'll create brand new repositories from scratch on your computer. With git clone, you'll clone or copy an existing repo from somewhere else to your local computer. You'll also learn how vitally important it is to know the status of a repo. You'll learn to check the status of a repo with the git status command. 3 simple commands, but they're starting us on our journey towards version control mastery. Let's get going with git init. In this lesson, we used git init to create our own repository. We used git clone to copy an existing repository. And we used git status to determine the status of a repository. Now, you might want to just jump right into making commits because a repository isn't very useful without them. But before we start, being able to review commits will help immensely when we start making our own. So let's learn how to review existing commits. Let me ask you a question. What did you do yesterday? Did you go to the beach? Take a walk around the block? Cook yourself some sweet and sour chicken because it's amazing? What about the day before yesterday? How about 2 weeks ago? When I was young, my parents wanted me to keep a daily journal so that I could look back on it sometime in the future and remember places I'd gone and experiences I'd encountered. Unfortunately, I wrote in it about once a year, which is terrible because the entries weren't detailed at all and just touched on high-level events. A good journal entry should have a date so you know when it occurred, a heading so you can give it a short description of that entry, and then the entry itself that has all of the information. Each time a new entry is made in the journal, it's like making a commit in the repository. And just like your journal entries, you want your commits to be frequent and descriptive, so you can see the progress of your project over time. Git automatically records the date and the content changes that have been made when a commit is created. So all you need to do is provide the descriptive heading or message for the commit. You want journal commits to be frequent so that you can see the ups and downs in life over time. Similarly, you want to make frequent commits with descriptive messages. This will make it easy to look back at the project and see how it has evolved. We're not making commits just yet, but start getting used to the idea that you should make commits often with descriptive commit messages. But how often is often, and how can you know what makes a good commit? How many files or lines of code should be included in the commit? One of the best ways to know what makes a good commit is to look at existing commits. The tools we'll be using to review a repository's history are git log and git show. With git log, you'll be able to display information about the existing commits. Git log is extremely powerful and you'll be using it all of the time. The git show command displays info about the given commit. So with this one, you provide it the commit ID, also known as the SHA, and the command displays info about just that one commit. Just 2 commands, git log and git show. Seems small, right? But this might actually be the most important lesson in the course. Learning how to display a repository's history and reviewing specific commits is useful for so many things. Are you ready? You focused? Let's look at the all-powerful git log. We're looking at the log of commits that have been made in this repository. This is one commit. Here is another. Look at all of the information that the log is displaying. It's showing the commit SHA, the person who made the commit, the date the commit was made, and the message for the commit. This is just a short description of what changes were made in this commit. Now, these are just the first 3 or so commits that can fit on the screen. There are plenty more. How do I know that? The colon here means that there are more lines of output to be displayed. If you're familiar with the command line, Git uses the less program as its pager. If you're not familiar with less or pagers, that's no problem. A pager is used to page through content. This is just the command line-y way of scrolling. Press either the J key or the down arrow to scroll down 1 line at a time. To scroll up, press the K key or the up arrow. You'll know you've reached the very last commit when the colon changes to the word end. To get out of the pager, just press the Q key. I've got 2 terminals open and both are located in the blog project. Let's run git log in this one and git log --1 line over here. The line holds the information for just one commit. It's the first 7 characters of the SHA and then the commit message. Here's the SHA for the most recent commit, and here's the same commit with the full SHA. See how the first 6 characters are the same? This commit here is this one. And here's the second commit, and here it is over here. So nothing has changed in the repo. The --1 line flag just alters the way the information is displayed. It's a pretty helpful command if you want to quickly review a repository's commits. I have a confession to make. When I first learned about the one-line flag for git log, I was really excited about it. Now I didn't have to scroll and scroll and scroll to read all of the commit messages. It worked for a couple of times, until one time I got this. Why isn't it working now? I tried restarting the terminal. That didn't do anything. I restarted my computer, and that didn't help. Finally, I actually read Git's helpful error message carefully. I had typed out online instead of one line. It says, fatal unrecognized argument, online. Online is unrecognized, which means Git doesn't know about it. This error message, or something similar, is common to run into while programming, so keep an eye out for it. Unfound or unrecognized arguments often mean a simple spelling mistake. So the moral of the story? Spelling is important. So make sure you actually spell things correctly. Also, Git will try and provide helpful feedback. Make sure you read it carefully.
The --stat flag doesn't change the output as drastically as the --one-line flag did. It just adds a new section down at the bottom of each commit. This gives us a closer look at what was changed in the commit. This section down here shows us the summary of changes. In this commit, one file was changed and 5 lines were added. But what file was changed? It lists the modified files above. The CSS file was changed. This commit modified 2 files, with a total of 91 insertions and 58 deletions. 31 of the lines were added to the CSS file, while 118 lines were either added or deleted in index.html. Let's run the git log-p command to see the commits, but also include the actual code changes, or patch, made to the files. This first part is the same as the regular git log command. Just like the --stat flag, the -p or --patch flag will add extra information below the standard commit info. This is the start of the patch output. I admit this output is a bit cryptic, so bear with me just a second because you won't really look at the top few lines most of the time, but it's good to know what they are. A diff and a patch refer to the same thing. The patch is showing the difference between the original version of the file and the changed version of the file. We're looking at the CSS file. There's the first version of the file. It shows up in a directory called A because it's the first. That's not a directory you'll actually see in the repo though. And then there's the second version. It shows up in a B directory because it's the second. These two are the same name because we're looking at 2 different versions of the same file. These could be different if the file was renamed. Yep, Git can keep track of renamed files. Pretty cool, right? Now back to the output. This line shows the hash of the first version of the file before the change and the hash after the change. These hashes are different from the commit SHA. I never really look at this line. These two are the same as these right here. They're the old and new versions of the files. We'll come back to this line in just a second. Now, this is the actual code of the CSS file. These lines here that are both in green and have the plus symbol in front of them mean that these lines have been added in this commit. Let's jump back to this line now. This is telling us where in the file the edits are made. This says that in the old or original version of the file, this code is from line 38 and then it's showing 6 lines of code. Those 6 lines are here. 1, 2, 3, 4, 5, 6. In the new or current version of the file, it starts on line 38 as well, but now there are 11 lines of code. The original 6 plus the 5 new ones. We can see all 11 lines right here. Now, this commit only has additions. What does it look like when lines are removed? Well, let's look. We need to scroll down to the next commit. Here it is. This first patch output is of the CSS file again. And here's the patch output of the HTML file. The lines that have been removed by the commit are in red and begin with the minus sign. Something to note here that's very important. Git tracks edits by lines. So if an edit is made to a line, it will show the line being removed and then added again. For example, it says main was deleted, but then here it says main was added again. The div with the class container was added, and the main element and all its code was indented so it nests correctly in the HTML file. Indenting this line changed it. So to Git,
This line with 1 indentation was removed, while this one with 2 indents was added. I know there's a lot of information in the patch output, but some of it is redundant and some of it can be ignored. The important things in the patch output are the file we're looking at, the changes, and it's sometimes helpful to know where in the file the changes were made. Awesome work! You've made it to the end of this section on reviewing existing commits. Remember that being able to display a repository's history can be especially helpful when you're first starting out. It's beneficial to know what's being stored in a commit and how to view it after the commit is made. You know, we keep talking about commits and have been reviewing all of these existing commits. I think it's time we actually make our first commit. What do you think? In the next lesson, you'll learn about making commits, viewing a file's changes before the commit is made, telling Git to not track specific files, and more. This is the lesson where we finally learn how to make commits of our very own. Are you excited? 'Cause I am. We've laid the groundwork of learning the git init command to create a new repository, the git clone command to copy an existing repository, the git log command to review existing commits, and the all-important git status command to see the status of the repository. As a side note, remember to have the download sheet with all the terms handy during this lesson, since we'll be using almost every term on that sheet. So we have these as the foundation. We'll build on top of them in this lesson with git add, git commit, and git diff. With git add, you'll add files from the working directory to the staging index. With git commit, you'll take files from the staging index and save them in the repository, which is what actually makes a commit. The git diff command is really cool and will seem pretty familiar actually, since you've already seen its output before. Git diff displays the difference between 2 versions of a file. Its output is exactly like the output of the git log-p command we used in the previous lesson. So we've got a couple new commands and one that's going to be very familiar. Now before we can use the commit or diff commands, we have to learn how to use git add. So let's get cracking. We just covered a ton of information in this lesson. We looked at using git add to stage content. We used git commit to actually commit changes to the repository. We also looked at what makes a good commit message. Then we learned about how helpful git diff can be to help us recall changes that haven't been committed yet. And last, we just looked at the git ignore file to tell Git what files it should not track. You now know how to create or clone a repo, how to make professional commits with clear, descriptive commit messages, and then how to review existing commits. With this knowledge, you can jump in and start working on any Git repository. One powerful concept we'll look at in the next lesson is branching. Branching lets you work on a project in multiple different states, and it will take your Git skills to the next level. Let's go check it out. Now that you're a pro at making commits, it's time to level up again. This leveling up is going to be an awesome step that will really give you version control superpowers. In this lesson, we'll look at git tag, git branch, git checkout, and git merge. With git tag, you'll be able to add tags to specific commits. A tag is an extra label for a commit that can indicate useful information, like this is the beta release. With git branch, you'll be able to create branches that let you develop different features of your project in parallel without getting confused as to which commits belong to which feature. That might sound a bit confusing, just hang on and we'll cover it in detail. With git checkout, you'll be able to switch between different branches and tags. Git merge is amazingly helpful because you can use it to take changes on different branches and combine them together automatically. It's an incredibly powerful feature. The commands we're covering in this lesson will help keep your project organized and speed up development. Let's start things out with the easiest command, git